Rainwear. All that is needed to make serviceable, improvised rainwear is waterproof material and waterproof tape. Plastic film from large trash bags will do. 4mm polyethylene is better. Tough, lightweight, coated fabric is best. Fabric duct tape is the best widely available tape. Figure 15.7 shows a pair of improvised rain chaps. Rain chaps are separate leg coverings, each with a loop to suspend it from one's belt and usually made large enough to be pulled on and off over the shoes and trousers. Rain chaps are better than waterproof trousers for working or walking while wearing a poncho or raincoat, because body movements cause drying air to be literally pumped under the chaps. This air keeps trousers and legs dry, and therefore warmer. Figure 15.7. Improvised rain chaps made of trash bag polyethylene and freezer tape. In the same way, a poncho or rain cape will allow plenty of air to reach the garments under them while one is working. When exercise is stopped, clothing underneath will stay dry and warm for some time. Sandals. Shoes are almost always in short supply for years following a disastrous war. Except in very cold weather, sandals can be made to serve quite well. The best sandal designs for hard work and serious walking have a strap around the heel and in front of the ankle, with no thong between the toes. Figure 15.8. Figure 15.8. A Ho Chi Minh sandal, excellent Vietnamese expedient footwear. Rubber bands cut from an inner tube have been inserted into a sole of auto tire tread. Book page 130. Such sandals also have the advantage of enabling one to wear socks and other foot insulation inside the straps. Top previous next. Clothing to protect against beta burns. If fresh and very radioactive fallout particles remain for long on the skin or extremely close to the skin, beta burns result. Any clothing that keeps fallout off the skin helps greatly. The best expedient protection is given by an outer layer of easily removable clothing similar to the improvised rainwear previously described, but fully covering the hair and neck and providing plastic trousers instead of chaps. Removable shoe coverings are highly advisable. All such protective coverings should be removed before entering a shelter, or removed in the entryway before going into the shelter room. If a person has fallout particles on clothing that he must continue to wear, he should vigorously brush his outer clothing before entering a shelter room. If fallout particles are washed off, rinsed off, or otherwise removed from the skin within a few minutes, no beta burns will result. A few days after a nuclear explosion, fallout particles are not radioactive enough to cause beta burns. In areas of heavy fallout, the danger from external doses of gamma radiation from fallout on the ground will continue much longer than will the risk of beta burns from some of these same fallout particles. The gamma rays given off by fallout particles brought into a shelter on clothing or bodies would subject shelter occupants to gamma doses so small as to be of no significance by wartime standards. Nor would shelter occupants be endangered by radiation from the body of a person who, before reaching shelter, had received a gamma dose large enough to kill him many times over. Except in science fiction stories, the body of such a person does not become radioactive. Fallout masks. For the majority of Americans in most fallout areas, means for filtering fallout particles out of the air they breathe would not be essential survival equipment. 18. Most fallout particles tiny enough to enter one's lungs would fall to earth so slowly that they would reach ground thousands of miles away from the explosions. By then, radioactive decay would make them much less dangerous, and their deposition would be spread out over much of the Earth. In past years, American endangering Soviet warheads typically were between 20 and 1 megaton. Explosions this large would inject almost all fallout particles into the stratosphere, high above rain clouds. Today, thousands of deployed Soviet ICBM warheads are between 550 and 100 kilotons. See Jane's Weapons Systems, 1987-88. Both surface bursts and air bursts of today's smaller warheads would inject most of their radioactive particles into the troposphere, from whence rainouts and snowouts would bring huge numbers of even tiny particles to Earth in hot spots, scattered across America. Persons living in dry, windy areas often wear dust masks and goggles to protect their noses and eyes from dust and sand particles. If fallout particles are mixed with dust and sand that is being blown into a shelter, Then persons in windy areas who occupy small below-ground expedient shelters should cover their noses and mouths with several thicknesses of towels or other cloth. Those who have dust masks should wear them, especially when working outside in dry, windy weather soon after fallout deposition. Other than whole-body exposure to gamma rays, the main danger to well-informed people would be from possible beta burns caused by fresh, hot fallout particles that would collect in nasal passageways, and from swallowed fallout particles. Much of the material continually eliminated from the nose and throat is swallowed. In some fallout hot spots, a secondary danger would be breathing extremely small, hot fallout particles into one's lungs, after a rainout of tiny fallout particles from fallout clouds produced by today's typical kiloton-range Soviet warheads. In some areas, hot particles would be dried and blown about by the winds within hours of their deposition in rain showers. Making a homemade dust and fallout mask is still not a high-priority survival project. In normal times, it is better to buy and store good masks and goggles. The following instructions for making a homemade mask are an improved design based on a Russian design, figure 15.9. This mask is the best of several. Figure 15.9. A Russian-type homemade fallout mask. For most Americans this will continue to be a low-priority item as long as Russian warheads are large. ORNLDWG78-11921 book page 131. Homemade types, and the following instructions for making and using it have been field tested. An individually fitted fallout mask materials needed. 1. 3 rectangular pieces of fluffy toweling, terry cloth preferred, each piece approximately 12 x 15 inches, or use 10 men's handkerchiefs. 2. Elastic. The best expedient elastic is from the waistband of a man's undershorts. 3. Clear plastic, from a photo album, billfold, plastic storm window, etc. 4. Sewing materials. Measurements. 1. Tie a string vertically around your head and face, passing it 1/2 inch in front of each of your ears and making it quite tight. 2. Tie a second string horizontally around your head, crossing your forehead 11/4 of an inch above the top of your eye sockets. These two strings should cross each other at points X and X1, over your temples. 3. Measure the distance X to X1 across your forehead and the distance X to X1 going under your chin, around your lower jaw and next to your throat, as indicated by figure 15.9. Construction. 1. Cut out 3 pieces of terry cloth, making the width of each piece equal to X to X1, the curved distance across your forehead, and the height of each piece equal to the distance X to Y plus 1/2 inch, that is, equal to half the distance X to X1, measured under your chin, plus 1/4 inch. See figure 15.9. 2. Cut the lower edge of each piece as illustrated. 3. Stitch the 3 pieces of terry cloth together, one on top of the other, thus making the mask 3 layers thick. Stitch around all 4 edges of the cloth rectangle and down the centerline. 4. Mark and cut out the eye holes, as illustrated. Make the mask's dimensions smaller for children. 5. Cut 1 rectangle of clear plastic measuring S 2 by 21/4 of an inch, and sew this plastic over the outside of the eye holes, stitching the plastic around its edges and down the centerline. 6. Fold the 3 pieces along their vertical centerline and stitch the lower side together, along the upper stitch line Y to Y1. Stitch 2 inch from the lower edge. Then sew a second row of stitches. 7. Sew on the elastic headbands, making them short enough to hold the mask tightly around your face. If the elastic is from the waistband of a man's undershorts, use a doubled elastic both over the top of your head and around the back of your head. Make these elastic pieces so short that you can just put all your fingers comfortably between the elastic and your head when the pieces are fully stretched. If using a weaker elastic, be sure to adjust the links to a tight fit, to prevent air leaks under the edges of the mask. Because of the thickness of material where the elastics are connected to the upper corners of the mask, it may be necessary to do this stitching by hand. 8. To keep fallout particles off your head and neck, sew a loose-fitting piece of bedsheet cloth, not illustrated, to the edges of the mask that fit around your face. This cloth should extend back over your head and down over your collar, over which it can be tied. Use Put on the mask by first placing it over your chin, then pulling the back elastic down to fit around the back of your head. Caution. To avoid spreading infections, each mask should be labeled and worn by only one person. Book page 132. Chapter 16. Minimum pre-crisis preparations. Your chances of surviving a nuclear attack will be improved if you make the following low-cost preparations before a serious crisis arises. Once many Americans become convinced that a nuclear attack is a near certainty, they will rush to stores and buy all available survival supplies. If you wait to prepare until a crisis does arise, you are likely to be among the majority who will have to make do with inadequate supplies of water containers, food, and materials. Furthermore, even if you have the necessary materials and instructions to make the most needed survival items, you and your family are not likely to have time to make all of them during a few days of tense crisis. The following recommendations are intended primarily for the majority who live in areas likely to be subjected to blast, fire, or extremely heavy fallout. These people should plan to evacuate to a safer area. Many citizens living outside high-risk areas, especially homeowners with yards, can and should make better pre-crisis preparations. These would include building high protection factor permanent shelters covered with earth. Shelter. Keep on hand the tools and materials your family or group will need to build or improve a high protection factor expedient shelter. 1 or more shovels, a pick if in a hard soil area, a bow saw with an extra blade, a hammer, and 4 mil polyethylene film for rainproofing your planned shelter. Also store the necessary nails, wire, etc. needed for the kind of shelter you plan to build. Keep instructions for shelter building and other survival essentials in a safe and convenient place. Ventilation cooling. Make a homemade shelter ventilating pump, a cap, of the size required for the shelter you plan to build or use. Water. Keep on hand water containers, including at least 4 30-gallon untreated polyethylene trash bags and 2 sacks or pillowcases for each person, a pliable garden hose or other tube for siphoning, and a plastic bottle of sodium hypochlorite bleach, such as Clorox, for disinfecting water and utensils. Fallout meter. Make 1 or 2 kFMs and learn how to use this simple instrument. Food. Store at least a 2-week supply of compact, non-perishable food. The balanced ration of basic dry foods described in Chapter 9, Food, satisfies requirements for adults and larger children at minimum cost. If your family includes babies or small children, be sure to store more milk powder, vegetable oil, and sugar. Continuing to breastfeed babies born during an impending crisis would greatly simplify their care should the crisis develop and worsen. For preparing and cooking basic foods. Make a 3-pipe grain mill like the one described in Chapter 9, Food, or buy a small hand-cranked grain mill, which grinds more efficiently than other expedient devices. Book page 133. Make a bucket stove as described in Chapter 9. During evacuation, the stove can be used as a container. Store some kitchen-type wooden matches in a waterproof container. Keep essential containers and utensils on hand for storing and transporting food and for cooking and serving in a shelter. Sanitation. A hose-vented 5-gallon can, with heavy plastic bags for liners, for use as a toilet. Include some smaller plastic bags and toilet paper with these supplies. Tampons. Insect screen or mosquito netting, and fly bait. See Chapter 12. Medicines. Any special medications needed by family members. Potassium iodide, a 2-Oz bottle, and a medicine dropper, for prophylactic protection of the thyroid gland against radioactive iodines. Described in the last section of Chapter 13, Survival Without Doctors. A first aid kit and a tube of antibiotic ointment. Light. Long burning candles, with small wicks, sufficient for at least 14 nights. An expedient lamp, with extra cotton string, wicks, and cooking oil as described in Chapter 11. A flashlight and extra batteries. Radio. A transistor radio with extra batteries and a metal box in which to protect it. Other essentials. Review the evacuation checklist developed primarily for persons who make no preparations before a crisis, and add items that are special requirements of your family. Book page 134. Copyright 2000 Nuclear War Survival Skills. Also see the New Expedient Shelter book. Requires the DJVU plugin. NWSS contents. Cover. Addition notes. Table of contents book order form forward. About the author acknowledgements introduction. Ch. 1. The dangers. Ch. 2. Warnings and Ch. 3. Psychologic. Ch. 4. Evacuation. Ch. 5. Shelter. Th. Ch. 6. Ventilation. Ch. 7. Protection. Ch. 8. Water. Ch. 9. Food. Ch. 10. Fallout raw. Ch. 11. Light. Ch. 12. Shelter saw. Ch. 13. Surviving. Ch. 14. Expedient. Ch. 15. Improvised. Ch. 16. Minimum pre-crisis preparations. Ch. 17. Permanent. Ch. 18. Trans-Pachi. App. Instructio. App. 8.1. Door COV. App. 8.2. Pole COV. App. 8.3. Small PO. App. 8.4. Abovegrow. App. 8.5. Abovegrow. App. 8.6. Above GR. App. B. How to mock. App. C. A. Homemade. App. D. Expedient. App. E. How to mock. App. F. Providing. Selected references. Selected index. Graphics. Nuclear War Survival Skills. Mail home. Ch. 16. Minimum pre-crisis preparations. Your chances of surviving a nuclear attack will be improved if you make the following low-cost preparations before a serious crisis arises. Once many Americans become convinced that a nuclear attack is a near certainty, they will rush to stores and buy all available survival supplies. If you wait to prepare until a crisis does arise, you are likely to be among the majority who will have to make do with inadequate supplies of water containers, food, and materials. Furthermore, even if you have the necessary materials and instructions to make the most needed survival items, you and your family are not likely to have time to make all of them during a few days of tense crisis. The following recommendations are intended primarily for the majority who live in areas likely to be subjected to blast, fire, or extremely heavy fallout. These people should plan to evacuate to a safer area. Many citizens living outside high-risk areas, especially homeowners with yards, can and should make better pre-crisis preparations. These would include building high protection factor permanent shelters covered with earth. Shelter. Keep on hand the tools and materials your family or group will need to build or improve a high protection factor expedient shelter. 1 or more shovels, a pick if in a hard soil area, a bow saw with an extra blade, a hammer, and 4mm polyethylene film for rainproofing your planned shelter. Also store the necessary nails, wire, etc. needed for the kind of shelter you plan to build. Keep instructions for shelter building and other survival essentials in a safe and convenient place. Ventilation cooling. Make a homemade shelter ventilating pump, a cap, of the size required for the shelter you plan to build or use. Water. Keep on hand water containers, including at least 4 30-gallon untreated polyethylene trash bags and 2 sacks or pillowcases for each person, a pliable garden hose or other tube for siphoning, and a plastic bottle of sodium hypochlorite bleach, such as Clorox, for disinfecting water and utensils. Fallout meter. Make 1 or 2 kFMs and learn how to use this simple instrument. Food. Store at least a 2-week supply of compact, non-perishable food. The balanced ration of basic dry foods described in Chapter 9, Food, satisfies requirements for adults and larger children at minimum cost. If your family includes babies or small children, be sure to store more milk powder, vegetable oil, and sugar. Continuing to breastfeed babies born during an impending crisis would greatly simplify their care should the crisis develop and worsen. For preparing and cooking basic foods. Make a 3-pipe grain mill like the one described in Chapter 9, Food, or buy a small hand-cranked grain mill, which grinds more efficiently than other expedient devices. Book page 133. Degree make a bucket stove as described in Chapter 9. During evacuation, the stove can be used as a container. Store some kitchen-type wooden matches in a waterproof container. Degree keep essential containers and utensils on hand for storing and transporting food and for cooking and serving in a shelter. Sanitation. A hose-vented 5-gallon can, with heavy plastic bags for liners, for use as a toilet. Include some smaller plastic bags and toilet paper with these supplies. Tampons. Insect screen or mosquito netting, and fly bait. See Chapter 12. Medicines. Degree any special medications needed by family members. Degree potassium iodide, a 2-Oz bottle, and a medicine dropper, for prophylactic protection of the thyroid gland against radioactive iodines. Described in the last section of Chapter 13, Survival Without Doctors. Degree a first aid kit and a tube of antibiotic ointment. Light. Degree long burning candles, with small wicks, sufficient for at least 14 nights. Degree an expedient lamp, with extra cotton string, wicks, and cooking oil as described in Chapter 11. Degree a flashlight and extra batteries. Radio. A transistor radio with extra batteries and a metal box in which to protect it. Other essentials. Review the evacuation checklist, developed primarily for persons who make no preparations before a crisis, and add items that are special requirements of your family. Book page 134. Copyright 2000 Nuclear War Survival Skills. Also see the new Expedient Shelter book. Requires the DJVU plugin. NWSS Contents. Cover. Addition Notes. Table of Contents Book Order Form Forward. About the Author Acknowledgements Introduction. Ch. 1. The Dangers. Ch. 2. Warnings and Ch. 3. Psychologic. Ch. 4. Evacuation. Ch. 5. Shelter. Ch. 6. Ventilation. Ch. 7. Protection. Ch. 8. Water. Ch. 9. Food. Ch. 10. Fallout raw. Ch. 11. Light. Ch. 12. Shelter saw. Ch. 13. Surviving. Ch. 14. Expedient. Ch. 15. Improvised. Ch. 16. Minimum PR. Ch. 17. Permanent family fallout shelters for dual use. Ch. 18. Trans-Pachi. App. Instructio. App. 8.1. Door COV. App. 8.2. Pole COV. App. 8.3. Small PO. App. 8.4. AboveGrow. App. 8.5. AboveGrow. App. 8.6. AboveGR. App. B. How to Mock. App. C. A. Homemade. App. D. Expedient. App. E. How to Mock. App. F. Providing. Selected references. Selected index. Graphics. Nuclear War Survival Skills. Mail Home. Ch. 17. Permanent family fallout shelters for dual use. The need having a permanent non-floatable shelters. In most localities the water table usually is below the depth of excavation needed to build or install a below-ground shelter. A dependable, high protect water degree water nay. Shelter owners who are unable or unwilling to obtain wheat from such sources can buy high-protein hard wheat at higher prices from health food stores and a few mail order companies. Nylon hammock chairs to enable the maximum number of additional people to occupy a shelter for days to months. Top previous next. The need. Having a permanent, ready-to-use, well-supplied fallout shelter would greatly improve millions of American families' chances of surviving a nuclear attack. Dual-use family shelters. Shelters that also are useful in peacetime are the ones that Americans are most likely to build in normal peacetime and to maintain for years in good condition for use in a nuclear war. The longer nuclear peace lasts, the more difficult it will be, even during a recognized crisis, to believe that the unthinkable war is about to strike us and that we should build expedient shelters and immediately take other protective actions. The life-saving potential of permanent, ready-to-use family shelters will increase with the years. Americans who decide to build permanent shelters need better instructions than can be obtained from official sources or from most contractors. This chapter brings together fallout shelter requirements, based on shelters and shelter components that have been built and tested in several states and nations. The emphasis is on permanent fallout shelters that many Americans can build for themselves. The author believes that millions of Americans can build good permanent fallout shelters or have local contractors build them if they learn the shelter requirements outlined in the following sections of this chapter and the facts about nuclear weapon effects and protective measures given in preceding chapters. Builders can use their skills and available local resources to construct permanent, dependable fallout shelters at affordable cost. Requirements for a permanent, dual-use family fallout shelter follow. A high protection factor, at affordable cost. A permanent fallout shelter should be built and can easily be built to have a high enough protection factor to prevent its occupants from receiving fatal or incapacitating radiation doses, and also from receiving doses large enough to seriously worsen their risks of developing cancer in the years following an attack. Shelters with a protection factor of 40 pf40 meet the minimum standard of protection for public shelters throughout the United States, and permanent family fallout shelters described in official pamphlets provide at least pf40 protection. In almost all fallout areas, pf40 shelters would prevent occupants from receiving fatal or incapacitating radiation doses while inside these shelters. However, in areas of heavy fallout, the occupants of pf40 shelters could receive radiation doses large enough to significantly contribute to the risk of contracting cancer years later. Furthermore, the larger the dose you receive while in a shelter, the smaller the dose you can receive after you leave shelter without being incapacitated or killed by your total dose. If you build a permanent shelter, you would be foolish to build a shelter with a PF of only 40 when additional protection is so easy to obtain. By making a shelter with a 6-inch thick concrete roof covered by 30 inches of shielding earth, and with other easily attained design features shown in Figs. 17.1 and 17.2, you can have a shelter with a protection factor of about 1000. An occupant of a PF 1000 shelter will receive a radiation dose only 1/1000th as large as he would receive if he were standing outside in an open field during the same time interval. Book page 135. Figure 17.1. Permanent family fallout shelter for dual use. Book page 136. Figure 17.2. Permanent family fallout shelter for dual use. Book page 137. To attain PF 1000 protection near the inner door of the illustrated shelter, its occupants must place containers full of water and/or other good shielding material against the door. They can do this easily and quickly if the shelter is supplied with filled water containers such as described in the water section of this chapter. The illustrated shelter room has 106 square feet of floor space, room enough for 5 adults and the survival essentials they will need for long occupancy, if shelter furnishings like those described in this chapter are provided. For each additional occupant, increase this shelter's length by 2 feet. To increase room size, increase length and not width. This retains maximum roof strength at minimum cost. Note in Figs. 17.1 and 17.2 the 12-inch thick concrete wall between the landing at the foot of the stairs and the end of the shelter room. Only a very small fraction of the radiation coming through the outer doors and down the stairs will make the 90-degree turn through the inner door, and most of this radiation will not strike shelter occupants if they place containers filled with water and other shielding material against the door. Also note the home-makeable, low-cost double-action piston pump and filter, shown in Figure 17.1, that even in a heat wave will supply adequate air through the 5-inch diameter air intake pipe, all described in Appendix E. Few survival-minded Americans, before a recognized international crisis arises, either can afford or believe that they can afford to build a permanent family fallout shelter costing around $10,000 in 1987. A small reinforced concrete, below-ground shelter of the type specified in official Federal Emergency Management Agency pamphlets costs about $100 per square foot of floor space, if built by a contractor in a typical suburban area. Those with the needed skills and time can save about half of this cost by doing their own work. Also, at many building sites where gravity drainage of the earth around a shelter's walls can be assured and hydrostatic earth pressure against the walls thus prevented, no steel reinforcement in the poured concrete or concrete block walls is needed unless required by the local building code. Caution: steel reinforcement in the walls and floor is needed in some clay soils that swell when wet and exert sufficient inward and upward pressure to crack unreinforced walls and floor slabs. Consult local builders who have learned from experience whether wall and floor reinforcement is needed in the type of soil where you plan to build. If needed, a grid of 1/2 inch rebars, spaced at 12 inches, usually is adequate. To save money on steel reinforcement, check prices in salvage yards for used rebars and substitute reinforcing materials such as junked cable and small pipes. How to safely pour a shelter's concrete roof slab without using a contractor's usual forms and equipment is indicated by Figs. 17.1 and 17.2. These drawings show 8 featuring long sheets of 3/4 inch plywood supported at their ends on shelter walls 7 feet - 6 inches apart. Preparatory to pouring the concrete, the plywood sheets should be supported along the centerline of the shelter by 4 inches by 4 inches S and other lumber, which can be used later to build seats and overhead bunks. Plywood left on the ceiling reduces condensation and heating problems in cold weather, but increases the volume of outdoor air that must be pumped through the shelter to maintain tolerable temperatures when it is occupied in hot weather. This was clearly demonstrated in the summer of 1963 when the author used SIMOCS, simulated occupants that produce heat and water vapor like people, to determine the habitability of a 6-roomlet below-ground group shelter, with a reinforced concrete roof that had been built in this manner by 6 New Jersey farm families. They had left ordinary 3/4 inch exterior plywood on the ceiling. Because the hollow concrete wall blocks and the well-drained gravel under the floor also kept heat from escaping into the surrounding soil, and because only natural ventilation was provided, the humidity became dangerously high within a few hours. Insulating a shelter's walls and ceiling can be disadvantageous, because insulation makes unavailable the heat sink of the shelter and its surrounding earth. In hot weather, insulation reduces the time during which ventilation can be stopped or restricted without disastrously overheating the occupants. Today, for such a shelter it would be better to use pressure-treated, rot-proof plywood and lumber, approved by leading building codes. For information, write to the American Plywood Association, P.O. Box 11700, Tacoma, WA 98411, inquiring about rot-proof plywood, dimensional lumber, and other material used in building the all-weather wood foundation. Most lumber yards will obtain treated plywood on order, and sell it for about 50% more than ordinary exterior-grade plywood. Big savings in shelter construction costs are made by using salvaged and/or used materials. Manufacturers of precast reinforced concrete beams and floor sections often sell rejects for very little. Book page 138. Most salvage yards have steel beams and other material that make excellent roofing for earth-covered shelters. Shortly before the Cuban Missile Crisis, when living near New York, I built for myself at modest cost a very small shelter on a well-drained hillside. I made it almost entirely of steel channels bought and cut to order at a salvage yard. Used cylindrical steel tanks with closed ends often make good low-cost permanent shelters. One of the best low-cost family shelters that I ever went into was on a hillside overlooking San Francisco Bay. It was made of a salvaged steel brewing tank that had been installed after a vertical cylindrical entrance with a door had been welded on it. The tank's exterior had been protected with a bituminous coating. Its survival-minded owner was a brilliant Hungarian refugee who, as a boy, had survived in a deep wine cellar throughout the Russian siege and shelling of Budapest. Nothing equals war experience to teach the life-saving value of shelters. Minimization of fire and carbon monoxide dangers. Many shelter designers and builders do not realize the probable extent of fires after a major nuclear attack. Nor do the big majority of them provide shelters built under or close to a house with adequate protection against the entry of deadly amounts of carbon monoxide if the house burns. Although the areas of fires resulting from a nuclear explosion generally will be about as extensive as the areas of significant blast damage, 6. On a clear day, a house up to about 8 miles from ground zero can be ignited by the thermal pulse of a 1 megaton airburst. 6. Figure 7.2 in Chapter 7 is a photograph of a car set on fire by a nuclear explosion so far away that the car was not even dented by the blast. This photograph indicates how a thermal pulse can go through window glass and ignite curtains, upholstery, or dry paper, even if flammable material outdoors is too damp to be ignited. Furthermore, fires from any cause can spread, especially in fallout areas following a nuclear attack, when firefighters may be unable or unwilling to expose themselves outdoors to radiation. Good protection against carbon monoxide is provided by a permanent earth-covered shelter, built with its entry outdoors and well separated from a house and other flammable structures, and constructed so that it can be closed gas-tight. Both the air intake and the air exhaust pipes should be installed so that they can be quickly closed airtight, as with screw-on fittings. Such closures should be kept well greased and securely attached close to where they would be used. If a shelter's entry is through a passageway from a house, a gasketed steel fire door, insulated on the shelter side, should be installed near the house end of the passageway. The shelter should be further protected by a second gas-tight door, to prevent the entry of carbon monoxide and smoke if heat from the burning house destroys the gasket on the fire door. If special fire door gaskets are not available, rubber weather stripping will serve. To lessen the risk of carbon monoxide being pumped into the shelter if the house burns and air must be pumped into the shelter while the fire still is smoldering, the air intake and pump should be at the far end of the shelter, and the air exhaust pipe and emergency exit should be near the passageway from the house. Be sure to seal electrical conduits leading from a basement to a connected shelter, so that if the house burns, carbon monoxide cannot flow through the conduits into the shelter when fresh outdoor air is not being pumped into the shelter. The author, while conducting ventilation and habitability tests of an earth-covered blast shelter connected through a tunnel to a house's basement, observed air flowing out through unsealed conduits, the reverse of such a possible life-endangering flow of carbon monoxide. When the shelter was being maintained at a slight overpressure by cranking its blower to pump in outdoor air, a little air flowed through the unsealed conduit into the basement. For ways to minimize carbon monoxide dangers arising from cooking, heating, lighting, and smoking, see following sections in this chapter. Remember that air contaminated with only 0.16% carbon monoxide can kill you in 2 to 3 hours, and 0.04% carbon monoxide causes frontal headaches and nausea in 2 to 3 hours. The Navy sets its safe allowable carbon monoxide concentration in air at 0.01%. Shelter habitability studies the effect of oxygen depletion and fire gases on occupants of shelters, by J. Muraoka. Report NCELTR 144, July 1961. Prevention of cracks and wet shelter problems. If wet basements are a problem in your locality, below-ground shelters are likely to be wet and unsatisfactory unless appropriate preventative measures are taken during their design and construction. When making plans, you should consult local builders of satisfactory basements. You also should question persons who at various times of the year have observed excavations, holes, and/or basements in your immediate vicinity, or have noted seasonal swampy places or springs. The most difficult type of shelter to keep dry for decades is one that is wholly or partially below the water table for part or all of the year. Concrete is not completely watertight. Waterproof coatings and coverings often are damaged during construction, or deteriorate with age. Book page 139. Shelter walls sometimes crack due to settling and earth movements. Metal shelters usually develop small leaks long before they become dangerously weakened. A100 occupant, below-ground shelter, built in 1984 near Dallas, Texas as a prototype blast shelter for industrial workers, was flooded when the water table rose. The poorly sealed opening of this shelter's emergency exit was below ground level, and after heavy rains was below the water table. A prudently designed shelter has the top of its emergency exit slightly above the surface of the surrounding earth, as illustrated in Figure 17.2. All underground electric conduits leading down into a shelter must be well sealed to prevent entry of water. To prevent a wholly or partially below water table shelter from becoming wet inside sooner or later, it should have a sump and an automatic sump pump to discharge water to the ground outside. If at any time you find that the sump pump is discharging an appreciable amount of water, you may have a serious wet shelter problem if electric power fails after an attack. A manually operated bilge pump and a sufficiently long discharge hose can be bought for about $20 from marine supply mail order firms, including West Marine Products, Box 5189, Santa Cruz, California 95063, and Defender Industries, Inc., P.O. Box 820, New Rochelle, New York 10802-0820. Long-established marine supply companies also are good sources of use-proven chemical toilets, first aid kits, lights, rope, etc. Shelter roof surfaces should be gently sloped, no matter how good a waterproof coating is to be applied. By making a concrete shelter roof as little as 1 inch thicker along its centerline than along its sides, so that it slopes to both sides, the prospects are improved for having an earth-covered coated roof that will not leak for decades. Figures 17.1 and 17.2 illustrate the following ways to prevent having a wet shelter. Put a layer of gravel or crushed rock in the bottom of the excavation, and install perforated drainage pipes if gravity drainage is practical. Cover the gravel or crushed rock in the floor area with a plastic vapor barrier before pouring a concrete floor. Coat the outer surfaces of roof and walls with bituminous waterproofing or other coating that has proved to be most effective in your locality. Backfill with gravel or crushed rock against the walls, to keep the soil from possibly becoming saturated. Saturated soil exerts hydrostatic pressure against walls, and may crack them and cause them to leak. In some areas it is more economical to cover a shelter's coated walls with a subsurface drainage matting, such as Encadrain, manufactured and sold by BASF Corporation, Fibers Division, Enca, North Carolina 28728. This will eliminate the costs of backfilling with gravel or crushed rock. Top previous next. Non-floatable shelters. In most localities the water table usually is below the depth of excavation needed to build or install a below-ground shelter. In some areas, however, after rainy periods the water table may rise until it is only a foot or two below the surface. Then a watertight shelter may float upward through the surrounding saturated soil, unless its weight plus the weight of its covering earth is sufficient to withstand its buoyancy. In many places swimming pools are kept full to prevent them from being cracked by uneven buoyant forces if the water table rises. Dramatic examples of floating shelters were steel blast shelters, guaranteed by contractors to be watertight, that were installed under the lawns of some Houston, Texas homes shortly after the Cuban Missile Crisis. When the water table rose after heavy rains, these shelters came up to the surface like giant mushrooms, to the frustrated dismay of their owners and the satisfaction of anti-defense newspaper feature writers. The most expensive permanent family fallout shelter described in a Federal Emergency Management Agency free handout, pamphlet H12-1, is floatable. Itis designed to be built of reinforced concrete covered by a flagstone patio only about 3 inches above the ground. Its 6-inch thick concrete roof is covered by a total thickness of only 6 inches of sand and flagstone. Like the rest of FEMA's permanent shelters, no prototype of this approximately PF-40 shelter was built, nor is there any record of anyone actually having built this shelter. In contrast, the below-ground shelter illustrated by Figs. 17.1 and 17.2 would not float even if it did not have assured gravity drainage of the surrounding soil through the perforated drain pipes in the gravel on which it rests, because this shelter is weighted down by the thick earth berm on its roof. Adequate, dependable ventilation, cooling. Book page 140. Basic facts that you need to provide adequate, dependable ventilation for a small or medium-sized shelter are given in Chapter 6, Ventilation and Cooling of Shelters. A good permanent shelter has 2 ventilation systems. Degree: the primary ventilation system of a small permanent shelter should utilize a manually operated centrifugal blower, or a homemade plywood double-action piston pump. See Appendix E. A satisfactory air pump must be capable of supplying adequate outdoor air through an air intake pipe, a filter, and an air exhaust pipe. See Figs. 17.1 and 17.2. Adequate outdoor air, for a small shelter means at least 15 cubic feet per minute per occupant for the cooler parts of the United States, and at least 30 CFM per occupant in most of the country. Most permanent shelters have centrifugal blowers that cannot deliver an adequate volume of air in hot weather for each planned occupant. For a medium-sized permanent shelter, installing 2 or more manually powered air pumps is both more dependable and more economical than providing an emergency generator and its engine to supply power to an electric blower. The Swiss, who have made the world's best and most expensive per capita preparations to survive a war, use 1 or more hand-cranked centrifugal blowers to ventilate most of their shelters. The multi-week and/or emergency ventilation system of a permanent shelter that has an emergency exit should depend on a homemade cap, made before a crisis and kept ready to use. See Appendix B, How to Make and Use a Homemade Shelter Ventilating Pump, the cap. By opening both the entrance and the emergency exit, the shelter is provided with 2 large, low-resistance openings through which a cap can pump large volumes of air with minimum work. Warning: keep screen doors and/or screen panels ready to protect all openings against the swarms of flies and mosquitoes likely to become dangerous pests in fallout areas. Use your cap to pump adequate air through screens. Insect screens greatly reduce natural ventilation, as the author first noted in Calcutta while a bedridden patient in a stifling hot ward of a hastily constructed army hospital. Because there were no fans or blowers to pump in outdoor air or circulate the air inside, window screens were opened in the daytime when malaria mosquitoes were not flying. The doctors correctly concluded that the temperature reduction when the screens were opened helped the patients more than they were endangered by the entering filthy flies. Adequate ventilation is more important than protection from flies, but with a cap and insect screens you can have both. Flies, mosquitoes, and other insects can be killed very effectively by occasionally spraying or painting screens and other alighting surfaces with water solutions of insecticides containing permethrin and sold in many farm stores. Advice on ventilation openings and fittings. Install ventilation pipes large enough to reduce resistance to airflow, thus increasing the volume of air that the shelter's pump can deliver. A shelter with a 200 CFM pump, such as the home-makeable plywood double-action piston pump described in Appendix E, should have 5-inch galvanized steel pipe. The pumps that are installed in most family shelters deliver only about 100 CFM or less. 4-inch pipe is adequate for use with pumps this small, provided that the pipes have no more than 2 right-angle turns below each gooseneck. A 90-degree L gives about as much resistance to airflow as 12 feet of straight pipe. Make and install a gooseneck with its mouth about twice the diameter of the pipe, as indicated in Figure 17.1. The purpose of such a gooseneck is to prevent more of the larger descending fallout particles from being pumped or blown into the shelter. For example, if 200 CFM of air is being pumped into a shelter through a gooseneck of 5-inch diameter pipe with its mouth also 5 inches in diameter, the velocity of the air up into the mouth of the gooseneck is about 1,440 feet per minute, and sand-like spherical particles smaller than approximately 500 microns in diameter also are sucked up 0.6. But if the 5-inch gooseneck's mouth is 10 inches across, then the upward air velocity is reduced to about 360 feet per minute, and only particles smaller than approximately 180 microns across are sucked up. Particles in the 180 to 500 micron diameter range are relatively large and fall to Earth in about 40 to 70 minutes from 35,000 feet, the base of the mushroom cloud of a 1 megaton explosion. See Figure 6.4. These particles are very dangerous because their radioactivity has had little time to decay, and should be kept out of a shelter's ventilation system. Furthermore, large particles retained in a shelter's filter restrict airflow sooner than do small ones. If an appropriately curved piece of 5-inch steel pipe cannot be found in a salvage yard or elsewhere, a good welder can use 5-inch steel pipe to make a substitute gooseneck with 2 90-degree turns. Do not use air intake hoods on a permanent shelter's pipes, because hoods are not as effective as goosenecks in preventing fallout particles from entering ventilation pipes. Book page 141. Also, pumping a given volume of air through a hood is more work than pumping the same volume through a gooseneck with equal cross-sectional areas. Never install any screen inside a gooseneck or air intake hood, because spider webs and the debris that sticks to webs will greatly reduce airflow. The author saw a gooseneck with a blast valve built inside it, spider webs and attached trash on this blast valve had consequentially reduced the volume of air that this shelter's pump could deliver. Of course, a screen is much more easily obstructed than a blast valve. Yet FEMA's widely distributed pamphlets on a permanent home fallout shelter, H12.1, and on a home blast shelter, H12.3, continue in successive editions to give detailed instructions for making an air intake hood with a screen soldered inside it. But these shelters that never have been built have much more serious weaknesses, including the likelihood that the above-ground parts of the ventilation pipes of the blast shelter would be bent over or broken off by blast wind-hurled parts of buildings and trees, even in suburbia. 350 miles per hour is the maximum velocity of the blast wind where the blast overpressure is 15 psi from a 1 megaton air burst. 6 The ventilation openings of the blast-tested expedient blast shelters described in Appendix D are much more likely to remain serviceable after being subjected to severe blast effects, because blast protector logs are placed around their openings, that are only a few inches above ground level. Prevention and control of condensation. A shelter can be watertight, yet at certain seasons of the year its walls, ceiling, and floor can be dripping wet with water condensed from entering outdoor air. This is a serious problem, except in arid parts of the West. During the winter months a shelter and its surrounding earth get cold, then especially on some spring days the dew point of entering outdoor air is higher than the temperature of the shelter's interior surfaces. As a result, condensation occurs on those surfaces that are cooler than the dew point of the pumped-through air. The most dramatic example that I have observed of the seriousness of this condensation problem was the dripping ceiling and wet walls of a reinforced concrete, family-sized shelter that I inspected on an early spring day at the Civil Defence College in Yorkshire, England. Such condensation also can occur in above-ground structures. Before World War II I had a 600-year-old bedroom in Queen's College, Oxford University. My bedroom's outer wall was made of solid limestone blocks about 15 inches thick, simply plastered and painted on the inside. On some spring days moisture condensed on the inside of the cold outer wall, ran down, and collected in little puddles on the floor. The occasional small coal fire in my adjacent study was barely sufficient to gradually evaporate the water and reduce my bedroom's humidity enough to prevent mold from forming. This often repeated occurrence proves the inadequacy of merely keeping an electric light turned on for heat to prevent condensation inside an uninsulated shelter built in a cool, frequently humid locality. Condensation and resultant 100% humid air can rust and eat away most steel pipes. Ventilation pipes should be made of galvanized steel or other materials that are undamaged by seasonal condensation and 100% humidity. In Connecticut I saw shelter ventilation pipes made of steel protected with 2 coats of marine paint. They were badly rusted only 2 years after installation. Operating a dehumidifier with automatic controls is the most practical way for most people to prevent condensation and other dampness problems in a shelter during peacetime. Almost all of the Chinese shelters that I inspected in 6 cities are dual-use shelters and typically are equipped with large dehumidifiers. A small dehumidifier adequate for a family shelter can be bought from a dependable mail-order company, such as Sears, for about $250 in 1987. To save floor space and facilitate removal of water, a dehumidifier should be installed near a shelter's ceiling. Then water from the dehumidifier can be disposed of most easily through a pipe or tube providing gravity drainage, best to the outdoors, second best to the sewer. After a nuclear attack the sewer system may become clogged and sewage may back up and flow into a below ground room having pipes that normally discharge into the sewer, and that lack check valves. If the above-mentioned ways of removing water are not possible, a sump and an automatic sump pump discharging water to the ground outdoors can solve the peacetime water disposal problem. After an attack, electric power can be expected to fail and shelter humidity will have to be controlled as much as possible by ventilation with outdoor air. A simple way to learn when to ventilate a shelter to dry it was described in a Russian article on shelter management. Keep several small cans of water in the shelter. Book page 142. They will be at about the same temperature as the shelter walls when the shelter is closed and is not being ventilated. If a filled can is exposed to outdoor air for about 10 minutes and moisture condenses on it, as a glass filled with an iced drink, sweats, on a humid summer day, do not ventilate the shelter. If no moisture condenses on the can, Ventilate. A walk-in entrance. Only a small fraction of permanent family shelters without a walk-in entrance have been kept in good condition for many years. Permanent family shelters with vertical or crawl-in entrances are found so inconvenient that the big majority of owners do not use them even for rotated food storage. In normal peacetime, most well-informed Americans concerned with protecting their families conclude that only a shelter skillfully designed for dual use justifies the cost of building and maintaining it. Significantly, Chinese civil defense has come to the same conclusion regarding Chinese permanent public shelters. Those that have been built, and that still are being built, are almost all useful both in peacetime and in wartime. If a family can use its shelter without having to go outside and be exposed to rain, snow, cold, or night problems, its dual-use shelter will be a more valuable peacetime asset than a shelter not directly connected to the house. Furthermore, a directly connected shelter can be entered more quickly in a crisis, and probably will reduce post-attack exposures to fallout radiation received by persons carrying things into the shelter, or by those moving about post-attack to protect the home. The main disadvantages of a directly connected shelter are that it usually provides poorer protection against heat, smoke and carbon monoxide if the house burns, and that it is more expensive to build than an earth-covered shelter with an outdoor walk-in entrance, such as the one illustrated in Figs. 17.1 and 17.2. An emergency exit that also provides a second large ventilation opening. Having an emergency exit in a fallout shelter is not as important as having one in a blast shelter, unless the fallout shelter is under or connected to a building. Since buildings are likely to burn, it is important to have a means of escape. However, an emergency exit makes any shelter more practical to live in than a shelter with only one large opening, especially in a heavy fallout area where it may be necessary to stay inside most of the time for weeks or months. Occupants of a shelter with only one large opening will not have adequate natural ventilation and will have to keep laboriously pumping air at least intermittently, through the air supply pipes to maintain livable temperature and/or humidity conditions. By opening both a shelter's entrance and its emergency exit, and taking measures to prevent the entry of rain, snow, and all but the smallest fallout particles, see Appendix F, natural ventilation will be adequate most of the time, except in hot, calm weather. With two large openings, a homemade cap, see Appendix B, can be used to pump enough outdoor air through the shelter, with much less work than is required to pump less air with a relatively high-pressure pump through typical ventilation pipes. Previous next. A dependable, high protection factor emergency exit. Occupants of a shelter with a dependable emergency exit will have less fear of being trapped if the main entry is blocked. If they open the exit, they also will be able to ventilate the shelter with natural ventilation through the entry and the exit, or with forced ventilation by operating a cap. To provide excellent radiation protection, a typical high PF emergency exit is filled with sand. Such an exit has a bolted-on steel plate on its bottom inside the shelter, and an easily cut, waterproof, plastic film covering over its top, which is a few inches below ground level. Obvious disadvantages of this typical sand-filled emergency exit include the difficulty of safely removing the bottom plate while sand is pressing down on it, and the impossibility of cutting the plastic film over the top of the exit without having fallout-contaminated earth fall on the person who does the cutting, and into the shelter room. Furthermore, if the earth covering the top of an emergency exit is frozen, occupants may be unable to break through it and get out. An improved design of sand-filled emergency exit was conceived by Dr. Conrad V. Chester of Oak Ridge National Laboratory and in 1986 was further improved, built, and tested in a full-scale model by the author. As shown in Figure 17.2, the sand in this 26 x 26 inch square vertical exit was supported by a piece of 3/4 inch exterior plywood, that should be of the previously mentioned rot-proof type, pressure impregnated with wood preservative. In the center of this 25-1/2 x 25-1/2 inch plywood sand support was an 8-inch diameter hole covered with 2 thicknesses of strong nylon cloth. Book page 143. The double thickness of cloth was firmly attached to the plywood by being folded over 4 3/16-inch galvanized steel rods, that were stapled to the plywood with galvanized poultry netting staples. See Figs. 17.2 and 17.3. The nylon cloth covering the hole can be easily and quickly cut with a knife, permitting sand to fall harmlessly into the shelter room. Figure 17.3. Plan of vertical emergency exit, before filling with sand. As shown in Figs. 17.2 and 17.3, the square 26 x 26 inch plywood sand support rests on a 1-1/2 inch wide rim or ledge around the 23 x 23 inch square hole in the shelter's reinforced concrete roof slab. After a shelter occupant has cut out the nylon cloth covering the hole and all but about 30 pounds of sand has fallen or been pushed by his hand down into the shelter room, he can tilt the plywood sand support up into a vertical position, and then turn it 45 degrees. The 26-inch width of the sand support permits it to be easily lifted down through the 32.5-inch long diagonal of the 23 x 23 inch square hole in the shelter's roof slab. Note the north-pointing arrow on the plywood sand support shown in Figure 17.3. Because the exit of this shelter was not made perfectly square, the sand support could be tilted most easily from its horizontal position into the vertical position if it was oriented so that its side marked N was to the north. A similar N arrow on the lower side of this sand support enabled a man below it, after the exit's lid was tied down and before the exit was filled with sand, to position the sand support for easy tilting and removal when the last of the sand was being cleared from this exit. The sand support should be cut to fit the exit after the exit is completed, because it is difficult to build an exit exactly to specified dimensions. The top of the emergency exit should be a few inches above the earth around it, to prevent rainwater on the ground from possibly running in. Securely cover the exit's top with a lid of 1/8 inch galvanized steel having a threaded plug hole, cut from a steel barrel, welded over a hole cut in the lid's center. Such a lid can be closely fitted to the top of a concrete exit by oiling it and pressing it against the concrete before the concrete begins to set. Before filling the exit with sand, while inside the exit, tie the lid down on each of its 4 sides with 9 loops of 3/32 nylon cord repeatedly tightened between 4 galvanized steel loops welded to the lower side of the lid, and 4 loops set in the shelter's walls and roof slab, as indicated in Figure 17.2. Use pliers to tighten, stretch, and hold the nylon cord while making the loops. Then after the plywood sand support is positioned in the bottom of the exit can be filled by pouring dry sand through the plug hole in the steel lid. Finally, the plug hole should be closed so that it cannot be opened, and then made waterproof. To make doubly sure that the lid will not rust, paint it with a cement paint, and then with whatever color outdoor paint you want. A shelter occupant can cut out the nylon cloth covering the hole in the sand support, remove all sand and the plywood sand support from this exit, cut the 4 tightened nylon cord multiple loops holding down the lid, push off the lid, and then climb up and step outside all in less than 5 minutes, even if damp sand has been used to fill the exit. To make removal of the sand more difficult, in his tests the author used damp sand that does not flow freely and makes it necessary to loosen it repeatedly, with one's hand and arm thrust up through the 8-inch hole in the plywood sand support. In a well-designed blast shelter, this sand-filled emergency exit will provide excellent protection against severe blast. Blast tests have proved that a 1/8 inch steel lid, the equivalent of a blast door, the size of this exit's lid will withstand blast effects of at least 50 psi. Furthermore, sand arching will transfer blast loadings on the sand outward from the slightly downward deflecting plywood sand support to its edges, and thence to the supporting reinforced concrete rim or ledge around the 23 x 23 inch hole in the shelter's roof slab. See Figure 17.2. Book page 144. A small shelter with an emergency exit near its far end has additional advantages. It can be supplied with adequate natural ventilation most of the time, with easy forced ventilation by a cap when forced ventilation is needed, and with daylight illumination. Means for attaining these advantages are described in Appendix F. Adequate storage space for essentials. As will be shown in the following sections of this chapter, about 20 square feet of shelter floor area per family member is needed for shelter furnishings and to store adequate water for a month, a year's supply of compact dry foods, cooking and sanitary equipment, blankets, tools, and other post-attack essentials. 20 square feet per family member also provides enough space per person to store winter clothing and footwear, camping equipment, and foods normally kept on hand and rotated as consumed in the course of ordinary family living. Additional space is needed if you plan to use your shelter as a workshop, or as a fallout shelter to save a few of your unprepared friends without endangering your own family. Seats, bunks, shelves. Seats and overhead bunks built like those specified in Figure 17.4 and pictured in Figure 17.5 enable more shelter occupants to sit and sleep more comfortably in less space than when using any other shelter furnishings known to the author. Note that the seat has an adjustable backrest. This backrest is similar to the fine-mesh nylon fishnet backrests tested in a prototype of an expensive blast shelter designed and furnished at Oak Ridge National Laboratory. Shelter habitability tests have proved the need for backrests. Even some young German soldiers had painfully sore backs after sitting on ordinary benches during a 2-week shelter occupancy test. Backrests should be installed in peacetime and kept ready for crisis use, rolled up against their upper attachments and covered. Then easily removable storage shelves, if needed, can be installed between benches and overhead bunks. To sit or sleep comfortably, pull the bedsheet forward and then sit on about the outer foot of the 2-foot wide seat. Although this 5-occupant shelter is illustrated with a bunk for each family member, it is. Figure 17.4. Seat with overhead bunk proportion for a shelter room with a 7 featuring or higher ceiling. A seat with a backrest should be 24 inches wide. Figure 17.5. Backrests of bedsheet cloth and 2-inch thick pads make sitting and sleeping comfortable. Book page 145. Prudent to count on stored supplies making some bunks unusable, and to realize that in a desperate crisis it might be hard to refuse shelter to an unprepared good neighbor. Note that with 4 persons seated on a 6.5-foot-long seat and 1 person on the overhead bunk, 5 persons can be quite comfortably accommodated on 25 square feet of floor space, including plenty of room for the sitter's legs. To store the most supplies in a shelter, you should install shelves after you know the heights of the items to be stored. Often the space between an overhead bunk and the ceiling can best be used by making easily removable additional shelves. Top previous next. Water. Degree water needs. Even most well-maintained shelters do not have enough water for prolonged occupancy. A permanent shelter should provide each occupant with at least 30 gallons of safe water, enough for an austere month, except in very hot weather. Degree containers. The most practical water container for shelter storage is a 5-gallon rigid plastic water can with a handle, a large diameter opening for quick filling and emptying, and a small spout for pouring small quantities. A 5-gallon water can of this type sells for about $5 in discount stores. The plastic bottles that household chlorine bleach is sold in also are good for multi-year storage of drinking water, as are glass jugs. Plastic milk jugs are not satisfactory, because after a few years they often become brittle and crack. Some shelter owners do not realize that, although a shelter can be kept dry in peacetime, except in the arid West, its air is likely to become extremely humid after a few days of crowded occupancy. Very humid air soon softens and weakens cardboard containers of food and flexible water bags. Degree disinfecting for multi-year storage. To store safe water and keep it safe for years, first disinfect the container by rinsing it with a strong solution of chlorine bleach. Then rinse it with safe water before filling it with the clear, safe water to be stored. Next, disinfect by adding household bleach that contains 5.25% sodium hypochlorite as its only active ingredient, in the quantities specified in this book's water chapter for disinfecting muddy or cloudy water. To 5 gallons, add 1 scant teaspoon of bleach. Finally, to prevent possible entry of air containing infective organisms through faulty closures, seal the container's closures with duct tape. Degree making efficient use of storage space. A 5-gallon rigid plastic water container typically measures 7x12 by 21 inches, including the height of its spout. 9 such 5-gallon containers can be placed on a 2x3-foot floor area. 27 5-gallon containers, holding 135 gallons of water, can be stored on and over 6 square feet of floor if you make a water storage stand 24x42 by 48 inches high, built quite like the seat with overhead bunk described in the seats, bunks, shelves section of this chapter. This easily movable storage stand should have 2 plywood shelves, one 24 inches and the other 48 inches from the floor. Degree using filled containers for shielding. Filled 5-gallon water containers can be moved quickly to provide additional shielding where needed to increase the protection factor of all or part of a shelter. For example, near the inner door of the shelter illustrated by Figs. 17.1 and 17.2 the protection factor is less than 1000. But if enough filled water containers are placed so as to cover the door with almost the equivalent of an 18-inch thick wall of shielding water, the PF of the part of the shelter room near the door can be raised to about PF 1000. If a shelter has 27 5-gallon cans of water stored on and under the above described 2-shelf water storage stand, then in less than 3 minutes 2 men can shield the shelter door quite adequately. All they have to do is take the 18 cans off the shelves, put 9 of them on the floor against the door and doorway, move the storage stand over the 9 door shielding cans, and place the remaining 18 cans on the stand's 2 shelves. Equally good doorway shielding can be provided by placing at least a 24-inch thickness of containers full of dense food, such as whole grain wheat or sugar, against the doorway. 2 55-gallon drums of wheat, each weighing about 400 pounds, can be quickly walked on a concrete floor and positioned so as to shield the lower part of a doorway. Heavy containers on the floor can provide a stable base on which to stack other shielding material. Degree a water well. The best solution to the water problem quite often is a well inside the shelter. In many areas the water table is less than 50 feet below the surface, and a 50-foot well, cased with 6-inch steel pipe, can be drilled and completed for about $2,000. Well drilling should be done after the shelter excavation has been dug and before the concrete shelter floor has been poured. An in-shelter well would be of vital importance not only to the occupants of a family shelter, but later on probably to nearby survivors. Book page 146. Even if only a gallon or so an hour could be bailed from a well too weak to be useful in peacetime, it would be a tremendous family asset post-attack. If infective organisms are found in water from a well drilled to provide water during and after an attack, safe water for months can be assured by merely storing a few gallons of household chlorine bleach. If enough water for worthwhile peacetime use can be pumped from a well, install a submersible electric pump, with plastic pipe in the well. Then in an emergency the pipe and the attached pump can be pulled by hand out of the well, with only a saw being needed to cut off lengths of the plastic pipe as it is pulled. After fuel casing has been cleared of pump, pipe and wires, a homemade 2-foot-long bale bucket on a nylon rope can be used to draw plenty of water. See Chapter 8, Water, for instructions. Degree local water sources. Most Americans' normal piped water would not run for months after a large nuclear attack. A month's supply of water stored in your shelter should be adequate, because, even if your area has heavy fallout, in less than a month radioactive decay will make it safe to haul water from nearby sources. An important part of your shelter preparations is to locate nearby wells, ponds, streams, and streambeds that when dry frequently have water a foot or two below the surface. The author has found that digging a water pit in an apparently dry stream often supplies enough filtered water to satisfy several families' basic needs. To keep the sides of a water pit dug in unstable ground from caving in, you should drive a circle of side-by-side stakes around the outside of your planned pit before starting to dig. With more work and materials, you and other survivors needing filtered water could dig a well like the Chinese water source shown on page 71. If you are in a fallout area, before drinking water from a water pit you should filter it through clayey soil to remove fallout particles and dissolved radioactive isotopes, as described in the water chapter. Of course it is prudent to chlorinate or boil all surface and near-surface water after it has been filtered. Food. Degree advantages of a 1-year supply. A family that expends the money and work to build and provision its own shelter should store a year's supply of long-lasting foods. If post-attack conditions enable you to continue living and making a living near your home, having a year's food supply will be a tremendous advantage. And if your area is afflicted with such dangerous, continuing fallout radiation and/or other post-attack conditions that surviving unprepared residents are soon forced to evacuate to better areas, then your and your family's chances will be better if hunger does not force you to move during the chaotic first few months after a nuclear attack. Degree costs of a 1-year food supply for a family shelter. Table 17.1 shows the wide range of 1987 costs of the basic survival foods for multi-year storage that are listed and explained on page 88. The delivered costs listed in the right-hand column include UPS shipping charges in the nearest and least expensive of UPS's 8 zones. For UPS shipping costs to the most distant points in the 48 states, add 34 cents per pound delivered. All the foods in this survival ration, if stored in moisture-proof and insect-proof containers, the non-fat milk powder should be in nitrogen-packed cans, will provide healthful nutrition for at least 10 years. The exception is the multivitamin tablets, which should be replaced every 2 or 3 years, depending on storage temperature. So a family that spends about $300 per member on such a one-year survival ration can consider that each of its members has been covered by famine insurance for $30 a year. Scurvy will be the first incapacitating, then lethal vitamin deficiency to afflict unprepared, uninformed Americans. A multivitamin tablet contains enough vitamin C to fully satisfy the daily requirement. However, a prudent shelter owner also should store vitamin C tablets that keep for years. 100-500 mg generic vitamin C tablets minus 50,000 milligrams of vitamin C in 1987 typically cost about $1.20 in a discount store. A 10 milligrams daily dose prevents scurvy. After a nuclear war in some areas, vitamin C will be worth many times its weight in gold. Degree sources of the basic foods listed in Table 17.1. Wheat. If you live in a wheat-producing area, the least expensive sources of ready-to-store wheat usually are local seed cleaning firms. 100 pounds or more of hard wheat, dried, bagged, and ready to store in moisture-proof containers, costs about 10 cents a pound. Today the wheat farmer receives about 4.5 cents a pound for truckloads, usually straight out of the field, not dry enough to store except in well-ventilated granaries, and containing trash that makes weevil infestations more likely. In some communities a few stores sell big bags of dry, cleaned hard wheat for 20 to 35 cents a pound. Book page 147. Table 17.1. A basic one-year survival ration for one adult male. Component ounces per day. Pounds per day range of 1987 costs prices in dollars per pound. FOB or picked up. Range of 1987 costs prices in dollars for a one-year supply FOB or picked up. Range of 1987 costs prices in dollars for a one-year supply delivered and in containers for multi-year storage. Whole kernel hard wheat. 16365 0.10 to 0.40 36.50 to 135.00 56 to 175. Beans. Pinto 5114 0.25 to 0.79 28.50 to 90.11 38 to 110 milk powder 2, 46 1.68 to 3.86 77.28 to 177.56 83 to 184 vegetable oil 1, 23 0.36 to 0.57 8.28 to 13.119 to 14 sugar 2, 46 0.25 to 0.30 11.50 to 13.80 16 to 20 salt, iodized 1/3 8 0.17 to 0.20 1.36 to 1.602 to 3 multivitamin tablets. Low generic, an N. Expensive brand. 1 per day 365 per year. 1.3 to 11.8 cents per tablet. 4.75 to 43.076 to 44. Total dollar costs $210 to $550. Top previous next. Shelter owners who are unable or unwilling to obtain wheat from such sources can buy high-protein hard wheat at higher prices from health food stores and a few mail-order companies. The lowest mail-order FOB price known to the author for hard Western wheat in 1990 is $3.17 for 10 pounds, in a vacuum-packed metallized plastic bag similar to the containers used for some U.S. Army combat rations. This long-lasting wheat, as well as other grains and legumes, is sold by Preparedness Products, 3855 South 500 West, Salt Lake City, Utah 84115. Another reliable mail-order source of wheat and other dry foods packaged for multi-year storage is the Survival Center, 5555 Newton Falls Road, Ravenna, Ohio 44266. Beans, like wheat, in many communities can be purchased from local farmers, co-ops or local stores at much lower delivered cost than from mail-order firms. In one small Colorado town, the co-op sold 25 pounds of pinto beans in a polyethylene bag for $1 1.25 - 45 cents a pound. Local supermarkets sell bulk pinto beans for around 60 cents a pound. Non-fat milk powder in 1990 is sold nationwide in the larger cardboard packages for around $2.85 per pound. A better buy for multi-year storage is the instant non-fat milk powder sold by Preparedness Products. This Mormon-owned firm's 1990 FOB price is $57.95 for a case of 6 nitrogen-packed cans, containing a total of 22.5 pounds. The author bought a case 3 years ago and found this non-fat instant milk powder to be excellent. At $2.58 a pound, plus UPS shipping charges, the cost is considerably less than for comparable milk powder packaged for multi-year storage and sold by other companies. Vegetable oil, sugar, salt, and multivitamin tablets are best bought at discount supermarkets. In cities, such stores often sell large plastic containers of vegetable oil as loss leaders, to attract customers, at prices as low as wholesale. Vegetable oil prices in small communities typically are much higher. For an economical survival ration, buy the lowest priced vegetable oil. Remember that one of the worst post-attack nutritional deficiencies will result from chronic shortages of fats, including oils, and that babies and little children cannot survive for a year on a diet of only grains and beans, with no oil or fat. See the food chapter. Degree cautions. Typical health food stores and most firms that specialize in survival foods sell basic foods at high prices, especially grains, beans, and milk powder. Investigate several other sources before buying. To make sure that an advertised 1-year supply of survival foods actually will keep an adult well nourished for a whole year, require the seller to inform you by mail what his 1-year supply provides a typical adult meal in: 1 calories, kcal, 2 protein, g, and 3 fat, g. Then you can use the values in the emergency recommendations column in Table 9.1 on page 84 to determine whether the advertised 1-year supply is adequate. Book page 148. Degree transitional foods. The emotional shock of suddenly being forced by war to occupy your shelter will be even worse if you have to adapt suddenly to an unaccustomed diet. It would be a good idea to occasionally practice eating only your survival rations for a day or two, and to store in your shelter a 2-week supply of canned and dry foods similar to those your family normally eats. Then it will be easier if war forces you to make the changeover. Of course, the transitional foods that you store should be rotated and replaced as needed, depending on their shelf lives. Degree. A hand-cranked grain mill. Whole kernel grains and soybeans must be processed into meal or flour for satisfactory use as principal components of a diet. If unprepared America suffers a nuclear attack, unplanned, local food reserves and/or famine relief shipments will consist mostly of unprocessed wheat, corn, and soybeans. Then a family with a manual grain mill will have a survival advantage and will be a neighborhood asset. Many health food stores at least have sources of hand-cranked grain mills. Mills with steel grinding plates are more efficient and less expensive than stone mills. A mail-order firm that still sells hand-cranked grain mills of a make that the author has bought and found to be well-made and efficient is Moses Country Health Foods, 7115 W 4th NW, Albuquerque, New Mexico 87107. It sells a serviceable Polish mill model OB hand grain mill for $35.73 FOB, plus UPS shipping charges. This mill cranks easily and grinds wheat into coarse meal or fine flour more efficiently than any of the American manual grain mills that the author has bought and used over the decades. Apparently, manual grain mills no longer are manufactured in the U.S. Before buying a grain mill, be sure to learn whether it grinds corn, our largest food reserve. In 1987, the author bought an advertised West German mill. Only after receiving it by mail order did he learn by reading the accompanying directions that it is not made for grinding corn. Cooking and heating. Degree. Safety precautions. The first rule for safe cooking and/or heating in a shelter is to do it as near as practical to the exhaust opening. If the fire is under an exhaust pipe, install a hood over the fire. Operate the shelter ventilating pump when cooking, unless a natural airflow out through the exhaust opening can be observed or felt. Keep flammable materials, especially clothing, well away from any open fire. Degree hazardous fuels. Charcoal is the most hazardous fuel to burn in confined spaces, because it gives off much carbon monoxide. In a crowded shelter there are obvious dangers in using the efficient little stoves carried by backpackers and in storing their easily vaporized and ignited fuels. Degree, canned heat. These convenient fuels are expensive. Sterno, widely used to heat small quantities of food and drink, typically retails in 7-ounce cans for what amounts to about $9 per pound. Degree wood. The safest fuel to burn in a shelter is wood, the most widely available and cheapest fuel. Furthermore, wood smoke is irritating enough to usually alert shelter occupants to sometimes accompanying carbon monoxide dangers. Scrap lumber cut into short lengths, made into bundles and stored in plastic bags, occupies minimum space and stays dry. Keep a saw and a hatchet in your shelter. Degree bucket stove. The most efficient, practical and safe stove with which to cook or heat for weeks or months in a family shelter is a bucket stove that burns either small pieces of wood or small sticks of twisted newspaper. See the food chapter. Especially if you believe that you may have to live in your shelter for months or that your normal fuel will not be available after a nuclear attack, you should make and store at least 2 bucket stoves. Degree an improved fireless cooker. To save a great deal of fuel and time, particularly with slow cooking grains and beans, make a very well insulated fireless cooker similar to the expedient one described on page 82 of the food chapter. Make a plywood box, first measuring carefully to ensure that, when completely lined with 4 inches of styrofoam, the styrofoam will fit closely around a large, lidded pot wrapped in a bath towel. An excellent fireless cooker is a war survival asset that also is useful for peacetime cooking. To boil about twice as much wheat flour meal in a given pot as can be boiled when making wheat mush, and to use the minimum amount of water and fuel, salt a batch of the flour meal, add enough water while working it to make a stiff dough, then make dough balls about 1-1/2 an inch in diameter, and roll them in flour meal. Drop the wheat balls into enough boiling water to cover them, and boil at a rolling boil for 10 minutes. Then put the boiling hot pot in a well-insulated fireless cooker for several hours. Corn balls can be made and boiled in this manner, also without the almost constant stirring required when boiling a mush made of home-ground flour meal. Book page 149. Degree a sturdy workbench. In the corner under the emergency exit build a workbench, secured to a wall, on which to cook and to which you can attach your grain mill. A bench 36 inches high, 42 inches wide, and 30 inches deep will serve. The other corner at the air exhaust end of the shelter should be the curtained-off toilet and bathing area. Degree very warm clothing, footwear, and bedding. Heating a well-ventilated shelter usually is unnecessary even in freezing weather if the occupants have these essentials for living in the cold, or if they have the materials needed to make at least as good expedient means for retaining body heat as are described in Chapter 15. The author has felt the warm hands of little Chinese children wearing padded clothing while living in their below-freezing homes, where there was scarcely enough straw, grass, and twigs to cook with. If you store plenty of strong thread and large needles in your shelter, you can make warm clothing out of blankets as some frontier settlers did to survive the sub-zero winters of Montana. Light. Degree white paint. To make a little light go a long way, paint the walls, ceiling, floor, and furnishings pure white. Degree candles. The most dependable and economical lights for a family shelter are long-burning candles. The best candle tested by the author is the 15-hour candle manufactured by the Reed Candle Company of San Antonio, Texas and sold by the millions in New Mexico each Christmas season for use in outdoor decorative luminaries. This votive type, short candle is not perfumed and has a wick supported by a small piece of metal attached to its base, so that the wick remains upright and continues to burn if the wax melts and no longer supports it. If burned in one of the candle lamps described below, this candle gives enough light to read by for 15 hours. The author has been able to find only one mail-order source of 15-hour candles like those sold by the millions in New Mexico. Preparedness Products, 3855 South 500 West, Salt Lake City, Utah 84115. A case of 144 candles sells for $49, FOB in 1990. When UPS shipping charges are added, the delivered cost is between 35 and 40 cents for each 15-hour candle, depending on the distance shipped. Persons who stock a permanent shelter should realize that after a nuclear war fats, oils, paraffin, and all other sources of light will be in extremely short supply for at least many months. Light at a delivered cost of about 2 cents per hour will be a bargain blessing. The second best shelter candle tested by the author is a standard plumber's candle, that retails for about 60 cents in many stores nationwide, and that burns for about 10 hours with a brighter flame than a votive-type candle. Two types of expedient candle lamps were proved by multi-day tests to be the most practical. The best expedient candle lamp is made of a 1-pint mason jar, identical to the cooking oil lamp pictured on page 102 of the light chapter except for the substitution of a short candle for the oil and wick. To make a stable candle base on a glass jar's rounded bottom, cover it with hot candle wax. To be able to light the candle and then put it inside the glass jar, make tongs out of an 18-inch length of coat hanger wire bent in the middle, with each of its two ends bent inward 90 degrees and cut off to make 1/4 inch long candle grippers. The second best candle lamp is made by cutting a standard aluminum pop or beer can, as illustrated. Use a sharp small knife. To make a stable base for a short candle, put enough sand across the can's rounded bottom to barely cover its center. The first candle burned will saturate and then harden the sand, making a permanent candle base or holder. Illustration of a candle holder made of aluminum pop can. Caution. Although candles are the safest non-electric lights for shelter use, they produce enough carbon monoxide to cause headaches in a poorly ventilated, long-occupied shelter. In a 2-week habitability test of a family shelter in Princeton, the father and mother did not smoke, yet they had persistent headaches. Specialists later concluded that their headaches were caused by the small amounts of carbon monoxide produced by the candles used both for light and to heat food and drink. Book page 150. Degree expedient lamps. The very economical lamp that burns cooking oil in a 1-pint glass jar is the better of the two expedient lamps pictured on page 102. For use in a shelter, however, long-burning candles, that are serviceable after decades of storage, are more practical. Among the disadvantages of expedient lamps is the fact that untreated, soft cotton string needed to make excellent wicks is no longer available in some communities, and making wire-stiffened wicks is a time-consuming chore. Degree other light sources. See the light chapter. Top previous next. Nylon hammock chairs. To enable the maximum number of additional people to occupy a shelter for days to months, nylon hammock chairs should be made before a war crisis arises, and should be kept stored for emergency use. The best field-tested model for use in shelters that are at least 7 feet wide is similar to the expedient hammock chair described on pages 120 through 124, is made of strong nylon cloth, and is 40 inches wide by 9 feet long along its center line, with each of its long sides being 8 feet minus 4 inches long. At each end is a curved hem 3 minus half an inch wide, through which a loop-ended nylon hammock rope is run, to draw the slung hammock into a boat-like, secure shape with adequate head and shoulder room. The breaking strength of a hammock rope should be at least 600 pounds. To attach the nylon ropes that support the suspended chairs to arms, a loop of nylon webbing, or of folded and stitched nylon cloth, should be sewn to each side edge of the hammock 52 inches from the end of the hammock that will serve as the top of the back of the chair. See the illustrations on page 124. Especially in permanent family shelters, support points both for the hammocks, and for the hammocks when they are converted into suspended chairs, should be made when the shelter is being built. Often overlooked sanitation and other shelter needs. Store enough soap to last your family for at least a year. After a major nuclear attack, the edible fats and oils, used in past generations to make soap, will almost all be eaten. Production of detergents is based on interdependent, vulnerable chemical industries not likely to be restored for years. A chemical toilet would help bridge the gap between modern living and surviving in a crowded shelter. For months-long occupancy, however, a more practical toilet is likely to be a 5-gallon can with a seat, a plastic trash bag for its removable liner, a piece of plastic film for its tie-on cover, and a hose to vent gases to the outdoors. See page 104. Store at least 200 large plastic trash bags. The author knows from his experiences in primitive regions that using anything other than paper in place of toilet paper or cloth is hard to get accustomed to. 100 pounds of newspaper, stored in plastic trash bags to prevent it from getting damp, takes up only about 3 cubic feet of storage space and would be useful for many purposes. Keep several thousand matches in mason jars, so that they will be sure to stay dry even if your shelter becomes very humid post-attack. Store most of your radiation monitoring instruments in your shelter, along with paper and pencils with which to keep records of radiation exposures, etc. A steel or reinforced concrete shelter should have a transistor radio with extra batteries, and a vertical pipe through which an antenna can be run up to improve reception. No one can remember all the needed survival facts and instructions given even in this one book, so keep nuclear war survival skills and other survival guidance in your shelter, and also other books that you believe may improve your family's morale and survival chances. Practice shelter living. A family that spends a weekend living in its completed small shelter will learn more about unrecognized shelter needs and more about each other than members are likely to learn if they all read civil defense information for 2 whole days. Furthermore, after this educational experience, family members old enough to have nuclear fears will know for sure that anti-defense activists are talking nonsense when they maintain that if most Americans had shelters they would become less heedful of nuclear war dangers and more likely to support aggressive leaders. Book page 151. Copyright 2000 Nuclear War Survival Skills. Also see the New Expedient Shelter book. Requires the DJVU plugin. NWSS Contents. Cover. Addition Notes. Table of Contents Book Order Form Forward. About the author Acknowledgements Introduction. Ch. 1. The Dangers. Ch. 2. Warnings and Ch. 3. Psychologic. Ch. 4. Evacuation. Ch. 5. Shelter. Ch. 6. Ventilation. Ch. 7. Protection. Ch. 8. Water. Ch. 9. Food. Ch. 10. Fallout raw. Ch. 11. Light. Ch. 12. Shelter saw. Ch. 13. Surviving. Ch. 14. Expedient. Ch. 15. Improvised. Ch. 16. Minimum PR. Ch. 17. Permanent. Ch. 18. Trans-Pacific Fallout. App. Instructio. App. 8.1. Door COV. App. 8.2. Pole COV. App. 8.3. Small PO. App. 8.4. Abovegrow. App. 8.5. Abovegrow. App. 8.6. Above GR. App. B. How to mock. App. C. A. Homemade. App. D. Expedient. App. E. How to mock. App. F. Providing. Selected references. Selected index. Graphics. Nuclear War Survival Skills. Mail Home. Ch. 18. Trans-Pacific Fallout. Potential dangers to Americans. Many strategists believe that if a nuclear war is fought in the next few decades, it probably will not involve nuclear explosions on any of our 50 states. Perhaps the first nuclear war casualties in the United States will be caused by fallout from an overseas nuclear war in which our country is not a belligerent. As the number of nations with nuclear weapons increases, especially in the Middle East, this generally unrecognized danger to Americans will worsen. Trans-Pacific War fallout, carried to an America at peace by the prevailing west-to-east winds that blow around the world, could be several hundred times more dangerous to Americans than fallout from the worst possible overseas nuclear power reactor accident, and many times more dangerous than fallout from a very improbable U.S. nuclear power reactor accident, as lethal as the disastrous Chernobyl accident was to Russians. Figure 1 is a map showing fallout from a single above-ground Chinese nuclear test explosion, a few hundred kilotons, on December 28, 1966. Figure 1. The fifth Chinese nuclear test was detonated on December 28, 1966. It involved thermonuclear material, and, according to the AEC press release, was a nuclear test in the atmosphere at their test site near Lop Nor. As indicated above, by the end of December 31, 1966, the leading edge of its fallout cloud extended as far east as the dotted line shown running from Arizona to the Great Lakes. ORNLDWG 73 4611. Book page 152. It produced fallout that by January 1, 1967 resulted in the fallout cloud covering most of the United States. This one Chinese explosion produced about 15 million curies of iodine-131, roughly the same amount as the total release of iodine-131 into the atmosphere from the Chernobyl nuclear power plant disaster. The Lawrence Livermore National Laboratory's preliminary estimate is that 10 to 50 million curies of iodine-131 were released during the several days of the Chernobyl disaster. In contrast, its estimate of the iodine-131 released during the 3 Mile Island nuclear power plant accident, the worst commercial nuclear power plant accident in American history, is about 20 curies. Figure 1 is from an Oak Ridge National Laboratory report, Trans-Pacific Fallout and Protective Countermeasures, ORNL 4900, written by the author of this book in 1970, but not published until 1973. No classified information was used in any version of this report. That summarized findings of the unclassified Trans-Pacific Fallout Seminar funded by the U.S. Atomic Energy Commission. This seminar was attended by experts who came from several research organizations and deliberated at Oak Ridge National Laboratory for 2 days in March of 1970. Later in 1970, a final draft of this report was submitted to Washington for approval before publication. It was promptly classified. Publication without censorship was not permitted until after it was declassified in its entirety in 1973. None of the recommendations in this pioneering report were acted upon, but many of them are given in this chapter. The findings and conclusions of the above-mentioned 1970 Oak Ridge National Laboratory Trans-Pacific Fallout Seminar, summarized in the 1973 report, were confirmed by a later, more comprehensive study, Assessment and Control of the Transoceanic Fallout Threat, by H. Lee and W. E. Strope, 1974. 117 pages, Report EGU 2981 of Stanford Research Institute. Fallout from the approximately 300 kiloton Chinese test explosion shown in Figure 1 caused milk from cows that fed on pastures near Oak Ridge, Tennessee and elsewhere to be contaminated with radioiodine, although not with enough to be hazardous to health. However, this milk contamination, up to 900 picocuries of radioactive iodine per liter, and the measured dose rates from the gamma rays emitted from fallout particles deposited in different parts of the United States indicate that trans-Pacific fallout from even an overseas nuclear war in which only 200 or 300 megatons would be exploded could result in tens of thousands of unprepared Americans suffering thyroid injury. Unprepared Americans do not have potassium iodide, the very effective prophylactic medication to prevent thyroid injury from radioiodine, and few could get it during the several days that it would take trans-Pacific War fallout to reach the United States. Fortunately, removal of even a cancerous thyroid rarely is fatal to people blessed with modern medical facilities. Only about 7,500 Americans, people living within a few miles of a nuclear power plant in Tennessee, have been given prophylactic potassium iodide to keep in their homes. No government organization has advised even Americans living near other nuclear facilities to buy and keep any kind of prophylactic medicine to protect their thyroids in case of a peacetime nuclear accident. As expected, official warnings and advice to the public continue, not even to mention preparations that individual Americans could make to protect themselves and their families against thyroid injury either from trans-Pacific War fallout deposited on an America at peace, or as a result of war fallout if our country is subjected to a nuclear attack. The worst danger to Americans from trans-Pacific fallout from a large nuclear war would be the whole-body gamma radiation doses that millions would receive from fallout particles deposited on the ground, on streets, on and in buildings. Protective countermeasures would include both sheltering some pregnant women and small children living in hot spot areas of abnormally high rain out of fallout, and evacuating others. Unless such unavoidably time-consuming and expensive countermeasures were taken, several thousand additional Americans might die from cancer in the following 20 or 30 years. The largest total doses would be received by people who would live normal unsheltered lives for the first month or so after fallout deposition, while the dose rates would be highest. Several thousand additional cancer deaths would be extremely difficult to detect, if caused by whole-body gamma radiation from fallout deposited nationwide, with these scattered deaths occurring over the 20 or 30 years following a Trans-Pacific War fallout disaster. For during these same decades about 15 million Americans normally would die from cancers indistinguishable from those caused by whole-body radiation from war fallout deposited on an America at peace. Book page 153. An authoritative risk estimate of getting cancer from low doses of radiation is given in Report No. 77, March 15, 1984, of the National Council on Radiation Protection and Measurement, Exposures from the Uranium Series with emphasis on radon and its daughters. The low-dose model for total excess cancer mortality is 100 cases per million people exposed to 1 rem uniform whole-body radiation. This would make the overall risk of cancer to the average individual in the population about 1 in 10,000 per rem, i.e., if 10,000 persons are exposed to a dose of 1 rem, 1,000 mrem, 1 excess fatal cancer would be expected within the lifetime of the group. Many radiation specialists have concluded from studies of the effects of extremely low doses that the above and similar conservative estimates of excess cancer deaths overestimate the number of fatalities likely to result from low radiation doses, such as would be received by millions of Americans from Trans-Pacific War fallout. To protect yourself against Trans-Pacific fallout, start by realizing that the dangers from Trans-Pacific War fallout have been increased by the continuing trend toward deployment of more accurate, smaller, more numerous nuclear weapons, because a large nuclear explosion, half a megaton, or more, injects most of its fallout particles and gases into the stratosphere, above the tops of clouds and above the altitudes at which quite prompt removal of contaminants from the atmosphere by scavenging takes place. Very small particles in the stratosphere do not reach the ground before they are blown at least several thousand miles. Most of these tiny particles remain airborne for weeks to years, are very widely dispersed, and are blown around the world several to many times before being deposited. By then the radioactivity of iodine-131, that has a half-life of only a little more than 8 days, is so greatly reduced that it is not nearly as dangerous as is radioactive iodine deposited much sooner with the fallout from smaller weapons of several hundred kilotons, or less, explosive power. Nuclear explosions smaller than about half a megaton, 500 kilotons, inject all or most of their fallout to lower altitudes within the troposphere, below the stratosphere. Most of such fallout is deposited during the radioactive cloud's first world-circling trip, when even quite rapidly decaying radioiodine still is dangerously radioactive. This greater danger from smaller nuclear weapons has been proved by numerous measurements of fallout from many nuclear test explosions, both foreign and American. The dangers from Trans-Pacific fallout produced by peacetime nuclear accidents are not nearly as serious as many Americans have been led to believe. For example, the Chernobyl nuclear power reactor accident injected as much radioactive iodine into the atmosphere as would the explosions of several kiloton-range nuclear weapons totaling perhaps as much as half a megaton in explosive power. But not nearly as much of the radioactivity caused by this reactor accident reached the United States as would reach us from several nuclear explosions in the same area, capable of injecting an equal amount of radioactivity into the atmosphere, because the cloud from the steam explosion that blew off the roof and otherwise damaged the Chernobyl reactor building may have risen quite soon to 20,000 feet or more and was partially blown eastward clear across Asia and the Pacific Ocean. However, the top of the radioactive smoke cloud over the Chernobyl power plant, that burned for days, rose only about 3,000 feet above the ground. As a result, much of the airborne Chernobyl radiation stayed at relatively low altitudes where scavenging, removal, of smoke and fallout particles and gases is most effective and rapid, due to aggregation on cloud droplets, rain out, and dry deposition. In contrast, Almost all of the fallout particles and radioactive gases from a nuclear explosion are injected much higher, to altitudes where scavenging is less effective. There, the generally prevailing west to east winds promptly start transporting very small particles and radioactive gases, that originate in the mid-latitudes of the northern hemisphere, around the world. Variable winds for days carried much of the Chernobyl radioactive material northward to Scandinavian countries, then westward and southward to other European countries. The resultant wide dispersal of this fallout allowed time for both scavenging and radioactive decay before a small fraction of these invisible radioactive clouds rose and also were blown eastward by the prevailing high-altitude winds. These west winds carried an extremely small fraction of the radioactive emissions from the burning Chernobyl plant clear across Asia and the Pacific to America. The media habitually exaggerate dangers from nuclear accidents, and exploited the Chernobyl disaster. For example, when Dr. Robert Gale, the leading bone marrow transplant specialist who helped save a few Chernobyl victims, first returned from Russia, an Associated Press article quoted him as saying, "I think we can say there are at least 50,000 to 100,000 people who have had some dose of radiation which might be of long-term concern." Book page 154. There will, unfortunately, be additional casualties. We hope the number will be small. The Rocky Mountain News headlined, 100,000 Soviets to suffer from radiation, doctor says. Mary McGrory, the syndicated liberal columnist, also misinterpreted Dr. Gale's risk estimate and misinformed her readers by writing, Dr. Gale, estimated that there could be 100,000 cases of radiation sickness. Such dramatic news items give the impression that 100,000 Russians, not just a small fraction of that number, are likely to suffer sickness or death from the Chernobyl radiation. So additional typical Americans, reading misinformation of this type and knowing very little about statistical evaluations of risks based on probabilities, have had their worst nuclear fears strengthened. The public's exaggerated fears of extremely small amounts of radiation also are worsened by the media's use without explanations of very small units of radiation measurement, including the picocurie. The picocurie is used to express the radioactive contamination of milk, water, etc., and is only 1/1,000,000th of a millionth, 1/1 trillionth, of a curie. One episode in which fears of radiation were thus worsened occurred shortly after the invisible fallout cloud from the Chernobyl disaster first reached the United States. Some listeners were frightened when a radio announcer merely stated that milk samples in Northwest Oregon showed 118 picocuries per liter of radioactive iodine. Few Americans know that they will not be advised to stop using fresh milk unless its contamination is 15,000 picocuries or more per liter as specified in the Food and Drug Administration's official, very cautious, protective action guidance, published in the Federal Register of October 22, 1982. The maximum measured radioactive contamination of milk in the United States by iodine 131 from the Chernobyl disaster was in milk produced by cows grazing on pasture in Washington, 560 picocuries per liter. The much greater potential danger from Trans-Pacific War fallout is brought out by the fact that the approximately 300 kiloton Chinese test explosion of December 28, 1966 resulted in worse iodine 131 contamination of milk produced by a cow grazing on pasture near Oak Ridge, Tennessee, 900 picocuries per liter. Even ASML overseas nuclear war with only 20 or so kiloton range nuclear explosions could cause high enough contamination of milk to result in the government's warning Americans to refrain from using fresh milk. Most Americans would heed this warning and would not drink or otherwise use fresh milk for weeks. In addition, a small overseas nuclear war possibly would cause a few American casualties years to decades later. 2 summary conclusions. 1. Trans-Pacific War fallout deposited on an America at peace surely would be a disaster, but not an overwhelming one. The economic and psychological impact probably would be more damaging than the losses of health and life. 2. Prudent individuals should make preparations to enable them to use the low-cost protective countermeasures described in this book, especially those in Chapter 13. Some of the most effective countermeasures, such as getting enough prophylactic potassium iodide to prevent thyroid damage even if war fallout dangers from explosions in the United States or overseas were to continue for a couple of months, cannot be accomplished after even an overseas nuclear war begins. Book page 155. Copyright 2000 Nuclear War Survival Skills. Also see the New Expedient Shelter book. Requires the DJVU plugin. NWSS Contents. Cover. Addition Notes. Table of Contents Book Order Form Forward. About the Author Acknowledgements Introduction. Ch. 1. The Dangers. Ch. 2. Warnings and Ch. 3. Psychologic. Ch. 4. Evacuation. Ch. 5. Shelter. Ch. 6. Ventilation. Ch. 7. Protection. Ch. 8. Water. Ch. 9. Food. Ch. 10. Fallout raw. Ch. 11. Light. Ch. 12. Shelter saw. Ch. 13. Surviving. Ch. 14. Expedient. Ch. 15. Improvised. Ch. 16. Minimum PR. Ch. 17. Permanent. Ch. 18. Trans-Pachi. App. Instructions for 6 Expedient Fallout Shelters App. 8.1. Door COV. App. 8.2. Pole COV. App. 8.3. Small PO. App. 8.4. Abovegrow. App. 8.5. Abovegrow. App. 8.6. Above GR. App. B. How to mock. App. C. A. Homemade. App. D. Expedient. App. E. How to mock. App. F. Providing. Selected references. Selected index. Graphics. Nuclear War Survival Skills. Mail Home. App. Instructions for 6 Expedient Fallout Shelters. Shelter Building Instructions. The following step-by-step instructions for building 6 types of earth-covered expedient shelters have enabled untrained families to build even the most difficult of these shelters in less than 2 days. The only families who took longer, up to 4 days, are the few who were delayed by very heavy rains. Each of these shelters has been built by several different families or groups of families. Only widely available materials and hand tools are required. They have been built under simulated crisis conditions in environments typical of large regions of the United States. Covered trench types have been built in forested clay hills of Tennessee, in a bare Colorado Valley in snowy November, in an irrigated Utah Valley in hot August. Most of the above-ground shelters were built by families in Florida, where the water table is within 18 inches of the surface. All of these test families used instructions that contain general guidance to help inexperienced persons build almost any type of earth-covered shelter. In this appendix, general instructions which apply to all types of shelters will be given first, to avoid repetition. However, if the instructions for building one type of shelter are reproduced separately, the pertinent parts of these general instructions should be given before the step-by-step instructions for building that shelter. Warning. Earth-covered shelters built of green poles can become unsafe within a few months, because of fungi and/or boring insects. In damper parts of the U.S., earth-covered shelters built of dry poles or untreated lumber can become unsafe after several months. An exception is very dry areas of the West, where some pioneers lived for years in earth-covered dugouts with pole roofs. General instructions for building an expedient shelter. 1. Read all the instructions and study the drawings before beginning work. Most families have found it helpful first to read the instructions aloud and then to discuss problems and work assignments. 2. Sharpen all tools, including picks and shovels. Dull tools waste time and energy. If no file is available, tools can be sharpened by rubbing them hard on concrete or a rough stone. 3. Wear gloves from the start. Blisters can lead to serious infections, especially if antibiotics cannot be obtained. 4. Whenever practical, select a building site that degree will not be flooded if heavy rains occur or if a large dam farther up a major valley is destroyed by a nuclear explosion. Degree is in the open and at least 50 feet away from a building or woods that might be set afire by the thermal pulse from an explosion tens of miles away. Keep well away from even a lone tree. It is hard to dig through roots. Degree has earth that is firm and stable. If the planned shelter is to be a trench type with unshored, unsupported, earth walls to make sure that the earth is firm and stable enough so that the walls will not cave in, make a thumb test by digging in 1/8 in deep hole and trying to push your bare thumb into the undisturbed earth at the bottom. If you can push your thumb no farther than 1 in, the earth should be safe enough. If the earth does not pass the thumb test, move to another location and repeat the test. Or build a below-ground shelter with shored walls, or an above-ground shelter. Degree has a sufficient depth of earth above rock or the water table for a trench to be dug to the depth required. Book page 156. To find out, try to dig a pit to the required depth before excavating the whole trench. Or, if you are quite sure there is no water table problem, try driving down a sharpened rod or pipe to the required depth in several places along the planned length of the trench. 5. If the shelter must be built on sloping ground, locate it with its length crosswise to the direction of the slope. 6. Before staking out the shelter, clear the ground of brush, weeds and tall grass over an area extending about 10 feet beyond the planned edges of the excavation. If loose earth is shoveled onto tall plants, the earth will be difficult to shovel the second time when covering the completed shelter roof. 7. Stake out the complete shelter, and then dig by removing layers of earth. 8. When digging earth that is too firm to shovel without first breaking it up, start picking, or breaking with a shovel, in a line across the center of the trench. Next, shovel out a narrow trench 6 or 8 in deep all the way across the width of the trench. Then with pick or shovel break off row after row of earth all the way across the width of the trench, as illustrated. Illustration of pickaxe chipping away a layer of dirt, ORNLDWG 78-162129. When digging a trench, to avoid having to move the excavated earth twice more to get it out of the way, first pile all earth about 8 feet away from the trench. Later, pile additional earth you are excavating at least 3 feet away. 10. Never risk a cave-in by digging into lower parts of an earth wall. It is dangerous to produce even a small overhanging section of wall or to dig a small, cave-like enlargement of a shelter. 11. When making a sandbag of a pillowcase or sack to hold earth shielding in place around the sides of shelter openings or along the edges of a shelter roof, fill it so that it will be only about 2/3 full after its opening is tied shut securely. Avoid dropping the sandbag. 12. If sufficient sandbags are not available, make earth-filled rolls. Bed sheets or any reasonably strong fabric or plastic film can be used to make these rolls as described below. To make a longer roll than the one illustrated below, several persons should make one together, standing side by side. To make an 8 in high earth-filled roll. 1. Select a piece of cloth at least as strong as a new bed sheet, 2 feet longer than the side of the opening to be protected, and 5 feet wide. 2. Place 2 feet of the width of the cloth on the ground, as illustrated. Illustration of man placing earth-filled roll. ORNLDWG 78-16213, 3. While using both hands to hold up and pull on 3 feet of the width of the cloth and pressing against the cloth with your body, have another person shovel earth onto and against the cloth. 4. While still pulling on the cloth, pull the upper part down over the earth that covers the lower part of the cloth. 157. 5. Cover the upper part of the cloth with earth so as to form an earth-filled hook near the upper edge, as illustrated. Illustration of finished earth-filled roll. ORNLDWG 78-16214, 6. If a greater thickness of rolls is needed, level the earth on top of a roll, then make another earth-filled roll on this level surface. 13. Cut and haul poles and logs more easily by doing the following. 1. Take time to sharpen your tools before starting to work no matter how rushed you feel. 2. When sawing green trees that have gummy resin or sap, oil your saw with kerosene or diesel fuel. If you don't have these, use motor oil, grease, or even soap. 3. When felling a small tree, the following method will help make a square cut, keep your saw from being pinched, and help make the tree fall in the desired direction. A. Saw the tree about 1/3 through on the side toward which you want it to fall. B. Then start sawing the opposite side, while another person pushes on the tree with a 10 ft push pole, pressing the end of the push pole against the tree about 10 feet above the ground. A push pole with a forked end or with a big nail on the end is best when you get ready to move it, or to use it for building your shelter. Make and use a measuring stick to speed up measuring and cutting poles and logs to the right lengths. 4. After a tree has been felled, trim off all limbs and knots so that the pole or log is smooth and will require no additional smoothing. Limb cut off to hook over the square cut end of the roll. ORNLDWG78-16210. 5. It usually is best first to cut the poles exactly 2 or 3 times the final length of the poles to be used in the shelter. 6. When you are ready to move the poles to the shelter site, drag them rather than trying to carry them on your shoulders. Shouldering them is more tiring, and you could injure yourself severely if you should trip. To drag a log or several poles by hand, a. Cut a stick 2 to 2-1/2 in diameter and about 3-1/3 featuring long. B. Tie a short piece of 1/4 in, or stronger, rope to the center of the stick. C. Make a lasso-like loop at the free end of the rope, so that when it is looped around the log and 2 people are pulling, see illustration, the front end of the log is raised about 6 in above the ground. The loop should be tightened around the log about 2 featuring from its end, so that the end of the log cannot hit the backs of the legs of the 2 people pulling it. Illustration of 2 men pulling a log. ORNLDWG78-16211. Caution. If you drag a log down a steep hill, one person should tie a rope to the rear end of the log, and then follow the dragger, ready to act as the brake if needed. 7. When you get the poles or logs to the location where you will build the shelter, cut them to the desired minimum diameters and specified lengths, and put all those of one specified type together. Book page 158. Be sure that the diameter of the small end of each pole of one type is at least as large as the minimum diameter specified for its type. Make and use a measuring stick, as previously described. 14. Use snow for shielding material for above-ground shelters if the earth is so deep frozen that digging is impractical. For a ridge pole shelter, see Appendix 8.5, cover the entire shelter with 5 feet of wetted or well-packed snow. For a crib-walled shelter, see Appendix 8.6, fill the cribs and then cover and surround the entire shelter with snow at least 5 feet thick. With wetted or well-packed snow 5 feet thick, the protection factor is about 50. Families have completed these winter shelters within 2 days. Several hundred pounds of snow can be moved at a time by sledding it on a piece of canvas or other strong material 6 to 8 feet wide. Attach a stick across one end of the material and tie a rope to the ends of the stick, so as to form a Y bridle on which a person can pull. To keep the occupants of a snow-covered expedient shelter dry and tolerably warm in sub-freezing weather, provide sufficient ventilation openings to maintain inside temperatures at a few degrees below freezing. See Chapter 14, Expedient Clothing. 15. Make a reliable canopy over the shelter entry. By following the instructions given in Figure A on the following page, you can make a dependable canopy that ordinary winds will neither tear nor blow down and that will not catch rainwater even if you have no waterproof material stronger than 4 mil polyethylene film. 16. Take to your shelter enough window screen or mosquito netting to cover its openings. Except in freezing cold weather, flies and mosquitoes would soon become a problem in most localities soon after an attack. 17. Work to complete 1. An expedient ventilating cooling pump, a cap, and 2. The storage of at least 15 gallons of water per person. This work should be accomplished by the time your shelter is completed. Especially in an area of heavy fallout during warm or hot weather, an earth-covered, high protection factor shelter when full of people would be useless unless adequately ventilated and cooled and provided with enough water. 18. In cold weather, restrict air flow through the shelter by hanging curtains of plastic or tightly woven fabric, or by otherwise partially obstructing its 2 openings. Always be sure to leave at least a few square inches open at the floor level of one opening and at the ceiling height of the other, to provide enough ventilation to prevent a harmful concentration of exhaled carbon dioxide. To prevent exhaled water vapor from wetting clothing and bedding and reducing its insulating value, keep the ventilation openings as wide open as possible without causing shelter temperatures to be intolerably cold. Book page 159. Figure A. A dependable canopy to keep fallout and rain out of a vertical entry. ORNLDWG77-20140R. Book page 160. Copyright 2000 Nuclear War Survival Skills. Also see the New Expedient Shelter book. Requires the DJVU plugin. NWSS Contents. Cover. Addition Notes. Table of Contents Book Order Form Forward. About the Author Acknowledgements Introduction. Ch. 1. The Dangers. Ch. 2. Warnings and Ch. 3. Psychologic. Ch. 4. Evacuation. Ch. 5. Shelter. Th. Ch. 6. Ventilation. Ch. 7. Protection. Ch. 8. Water. Ch. 9. Food. Ch. 10. Fallout raw. Ch. 11. Light. Ch. 12. Shelter saw. Ch. 13. Surviving. Ch. 14. Expedient. Ch. 15. Improvised. Ch. 16. Minimum PR. Ch. 17. Permanent. Ch. 18. Trans-Pachi. App. Instructio. App. 8.1. Door Covered Trench Shelter. App. 8.2. Pole COV. App. 8.3. Small PO. App. 8.4. Abovegrow. App. 8.5. Abovegrow. App. 8.6. Above GR. App. B. How to mock. App. C. A. Homemade. App. D. Expedient. App. E. How to mock. App. F. Providing. Selected references. Selected index. Graphics. Nuclear War Survival Skills. Mail Home. App. 8.1. Door Covered Trench Shelter. See illustration at the end of Appendix A1. Protection provided. Against fallout radiation. Protection factor 250 PF 250. A person in the open outside this shelter would receive 250 times as much fallout radiation as he would if inside. Against blast. Better protection than most homes, if built in very stable earth. Blast tests have indicated that this shelter would be undamaged up to at least the 5 psi overpressure range from large explosions. Without blast doors, the shelter's occupants could be injured at this overpressure range, although probably not fatally. Against fire. Excellent, if sufficiently distant from fires producing carbon monoxide and toxic smoke. Where practical. In a location where at least one hollow core door per occupant is available, and where the earth is very stable and a dry hole or trench 41/2 of a foot deep can be dug without difficulty. A family evacuating in a pickup truck or large station wagon can carry enough doors, with doorknobs removed. Strong boards at least 6 feet long and at least 1 full inch thick, or plywood at least 3 inch thick, also can be used to roof this 36-inch wide trench and to support its overhead earth shielding. Warning. Some doors with single thickness panels if loaded with earth will break before they bend enough to result in protective earth arching. For whom practical. For a typical family or other group with 2 or more members able to work hard for most of 36 hours. Stronger than average families with most members able to work hard have completed this type of shelter as less than 24 hours after receiving step-by-step, well-illustrated instructions. Capacity. The shelter illustrated is roofed with 3 doors and is the minimum length for 3 persons. If you have additional doors, or boards and sticks at least 3 feet long, make the entryway trenches 3 or 4 feet longer than illustrated if not pressed for time. For each additional person, add an additional door. If more than about 7 persons are to be sheltered, build 2 or more separate shelters. Building instructions. 1. Before beginning work, study the drawings and read all of the following instructions. 2. Divide the work. Check off each step when completed. 3. By the time the shelter is finished, plan to have completed 1. A ventilating pump, a cap 16 in wide and 28 in high, essential for this shelter except in cool weather, and 2. The storage of at least 15 gallons of water per occupant, see Appendix B in Chapter 8. 4. Start to assemble materials and tools that are listed for the illustrated 3-person shelter. Essential materials and tools for a 3-person shelter. Degree 3 hollow core doors. Degree a shovel, and a pick, if the earth is very hard. Degree 2 to 3 square yards per person of waterproof materials for rainproofing the roof. Use materials such as 4mm polyethylene film, shower curtains, plastic tablecloths, plastic mattress covers, or canvas. Degree 2 pieces of plastic or tightly woven cloth, each about 6-1/2 x 6-1/2 foot, to make canopies over the 2 shelter openings. Also sticks and cords or strips of cloth to support the canopies as described in Figure A of the introductory section of this appendix. Book page 161. Degree materials and tools for building a simple shelter ventilating pump. A cap 16 in wide and 28 in high. See Appendix B. Only in cold or continuously breezy, cool weather can tolerable temperatures and humidities be maintained in a crowded underground shelter without an air pump. Degree containers for storing adequate water. See Chapter 8. B. Useful materials and tools. Degree large cans, buckets, or pots with bale handles in which to carry earth and later to store drinking water or human wastes. Degree 2 pillowcases and 1 bedsheet per person to make sandbags around shelter openings and to cover trench walls. If available, large sheets of 4mm polyethylene are better than bedsheets, because they keep earth walls damp and stable. They also help keep shelter occupants dry and clean and prevent earth from falling into their eyes. Degree file, knife, pliers, hammer. Degree measuring tape, yardstick, or ruler. Degree expedient life support items. 5. To save time and work, sharpen all tools and keep them sharp. 6. Wear gloves from the start. Even tough hands can blister and become painful and infected after hours of digging. 7. Check to be sure the earth is stable and firm enough so that a trench shelter with unshored, unsupported, vertical earth walls will be safe from cave-ins. Interior doors are not strong enough to roof an earth-covered trench wider than 3 feet. As a test of the stability of earth, dig a small hole about 18 in deep. Remove all loose earth from the bottom of the hole. Then make a thumb test by pushing your bare thumb into the undisturbed surface at the bottom of the hole. If you can push your thumb into the earth no farther than 1 inch, the earth should be suitable for this type of shelter. If the earth does not pass the thumb test, move to another location and try the test again. Continue to relocate and repeat until suitable earth is found, or build a shored trench or above-ground shelter. 8. Prepare to dig a vertical walled trench 4-1/2 featuring deep and 3 feet wide. To determine the length of the trench, add together the widths of all the doors to be used for roofing it, then subtract 8 in from the sum. To avoid arithmetical errors, it is best to lay all the doors side by side on the ground. 9. Clear any brush, grass, or weeds that are more than a few inches high from the area where the trench will be dug. Also clear the ground around all sides of the trench, to a distance of about 8 feet from the sides and ends of the trench. 10. Stake out a rectangular trench 36 in wide, with its length as determined above. Also stake out the entrance at one end, as illustrated in Figure A1 at the end of Appendix AL, and the ventilation trench and opening at the other. 11. Dig the main trench, the entryway trench, and the ventilation trench. Place the excavated earth along both lengthwise sides of the trench, starting at the outside edges of the cleared space. Be sure that no earth is piled closer than 3 feet to the sides of the trench. 12. To be sure that unstable, unsafe earth is not encountered at depths below 18 in. Repeat the thumb test each time the trench is deepened an additional foot. If the earth does not pass the test, do not dig the trench any deeper, try another location. 13. To keep each trench its full width as it is dug, cut a stick 36 in long and another 18 in long. Use them repeatedly from the start to check the widths of the main trench and the entry trenches. Keeping the trench's full width will save much work and time later. 14. Carefully level and smooth the ground to a distance of 2-1/2 featuring from the sides of the trench, so that the doors will lie flat on the ground up to the edges of the trench. 15. If plenty of sheets, bedspreads, plastic, or other materials are available, cover the trench walls with them. Wall coverings should stop 1 inch from the floor of the trench to prevent their being stepped on and pulled down. Plastic wall coverings keep some types of damp earth walls from drying out and crumbling. Book page 162. 16. To be able to place an adequate thickness of shielding earth all the way to and around the entryway and ventilation hole, stack improvised sandbags around these 2 openings before placing the earth on the roof. Or use cloth or plastic material to make rolls of earth, as illustrated in the introductory section of Appendix A. 17. Shovel earth around the rolls, sandbags, or other means used to raise the level of the earth around the 2 shelter openings. Slope this earth outward, and pack it, so that rainwater on the ground cannot run into the shelter. 18. To rainproof the shelter and to prevent the roofing doors from being dampened and weakened, use available waterproof materials as follows. A. If the earth is dry, the easiest and best way to make a rainproof roof is to place the doors directly on the ground, with each of the end doors overlapping an end of the main trench by 4 or 5 in. Be sure again to level the ground surface as you place each door, so that each lies flat against the ground all the way to the edges of the trench. Next, mound dry earth over the doors. First place a few inches of earth on the doors near their ends, then mound it about 12 in. Deep above the centerline of the trench. Slope the earth to both sides so as to just cover the ends of the doors. Next, smooth off the earth mound, being careful to remove sharp stones that might puncture rainproof materials. Then place waterproof material over the smooth mound, making the buried roof, shown in Figure A1. Finally, carefully mound an additional 12 to 15 in of earth on top of the buried roof, again placing it first over the doors near their ends. The earth over the trench should be at least 2 feet thick, so that effective earth arching will support most of the weight of the earth covering and will provide considerable protection if struck by blast. B. If the earth is wet, place the waterproof material directly on top of the doors, to keep them dry and strong. To make water run off this waterproof covering and to keep water from collecting on a horizontal surface and leaking through, slope the doors toward one side of the trench by first making one side of the trench about 3 in higher than the other side. A way to raise one side without increasing the distance the doors must span is to place an earth-filled roll of bed sheets or other material along one edge of the trench. To keep the waterproof material used to cover the doors from sliding down the slope of the doors when earth is shoveled on, tuck the upper edge of the material under the higher ends of the doors. Finally, mound earth over the doors, first placing it near their ends. The mound should be at least 2 feet deep above the centerline of the roof and about 3 or 4 in deep over both ends of the doors. If more waterproof material is available than is required to make a buried roof, or to cover the doors, and to make the illustrated canopies over the 2 shelter openings, use this excess material to cover the wet ground on which the doors are placed. 19. Dig small drainage ditches around the completed shelter, to lead runoff water away. 20. To keep rain and/or sand-like fallout particles from falling into the shelter openings, build an open-sided canopy over each opening, as illustrated in Figure A, shown in the introduction section of Appendix A. 21. Install the air pump, a cap, in the shelter opening into which air is already naturally moving. 22. If the shelter has a cap, protection against radiation can be increased by placing containers of water and of heavy foods, or bags of earth, so as to partially block the openings. This would still permit adequate air to be pumped through the shelter, except in very hot weather. 23. For seats, place water and food containers, bedding, etc. along the side of the trench that is farther from the off-center entry trenches. If the trench floor is damp, covering it with a waterproof material, tree limbs, or brush will help. 24. Fill all available water containers, including pits which have been dug and lined with plastic, then roofed with available materials. If possible, disinfect all water stored in expedient containers, using 1 scant teaspoon of a chlorine bleach, such as Clorox, for each 10 gallons of water. Even if only muddy water is available, store it. If you do not have a disinfectant, it may be possible to boil water when needed. Book page 163. 25. Put at least your most useful emergency tools inside your shelter. 26. As time and materials permit, continue to improve your chances of surviving by doing as many of the following things as possible. 1. Make a homemade fallout meter, as described in Appendix C, and expedient lights. Prudent people will have made these extremely useful items well ahead of time. 2. Install screens or mosquito netting over the 2 openings, if mosquitoes or flies are a problem. Remember, however, that screen or netting reduces the air flow through a shelter even when the air is pumped through with a cap. 3. Dig a stand-up hole near the far end of the shelter. Make the hole about 15 in diameter and deep enough to permit the tallest of the shelter occupants to stand erect occasionally. Figure A1. Door-covered trench shelter. ORNLDWG 73-11769R Book page 164. Copyright 2000 Nuclear War Survival Skills. Also see the New Expedient Shelter book. Requires the DJVU plugin. NWSS Contents. Cover. Addition Notes. Table of Contents Book Order Form Forward. About the Author Acknowledgements Introduction. Ch. 1. The Dangers. Ch. 2. Warnings and Ch. 3. Psychologic. Ch. 4. Evacuation. Ch. 5. Shelter. Th. Ch. 6. Ventilation. Ch. 7. Protection. Ch. 8. Water. Ch. 9. Food. Ch. 10. Fallout raw. Ch. 11. Light. Ch. 12. Shelter saw. Ch. 13. Surviving. Ch. 14. Expedient. Ch. 15. Improvised. Ch. 16. Minimum PR. Ch. 17. Permanent. Ch. 18. Trans-Pachi. App. Instructio. App. 8.1. Door COV. App. 8.2. Pole-covered trench shelter. App. 8.3. Small PO. App. 8.4. Abovegrow. App. 8.5. Abovegrow. App. 8.6. Above GR. App. B. How to mock. App. C. A. Homemade. App. D. Expedient. App. E. How to mock. App. F. Providing. Selected references. Selected index. Graphics. Nuclear War Survival Skills. Mail Home. App. 8.2. Pole-covered trench shelter. Protection provided against fallout radiation. 16. Lay the poles side by S. Top previous next. Protection provided against fallout radiation. Protection factor 300 PF 300. A person in the open outside this shelter would receive 300 times more fallout radiation than he would if he were inside. Against blast. Quite good protection if built in stable earth. Blast tests have indicated that this shelter, if built in stable earth, would not be seriously damaged by blast effects of large explosions at least up to the 7 psi overpressure range. At 7 psi, most buildings would be demolished. Without blast doors, occupants of the shelter could be injured, although probably not fatally at this. Overpressure. Against fire. Excellent, if sufficiently distant from fires producing carbon monoxide and toxic smoke. Where practical. In wooded areas with small trees, for builders who have an axe or a bow saw, crosscut or chainsaw, and digging tools. Or in any location where the necessary poles may be obtained. In stable earth, where the water table or rock is more than 4-1/2 featuring below the surface. For whom practical. For a typical family or other group with 2 or more members able to work hard for most of 48 hours. Stronger than average families with almost all members able to work hard have completed this type of shelter as about 24 hours after receiving step-by-step, well-illustrated instructions, before traveling to the wooded building site and beginning to cut trees and haul poles. Capacity. The shelter illustrated is the minimum length recommended for 4 persons. For each additional person, add at least 2-3/4 featuring to the length of the shelter room. If more than about 10 persons are to be sheltered, build 2 or more separate shelters. Building instructions. 1. Before beginning work, Study the drawings and read all of the following instructions. Divide the work so that some people will be digging while others are cutting and hauling poles. Check off each step when completed. 2. By the time the shelter is finished, plan to have completed 1. A ventilating pump, and 2. The storage of at least 15 gallons of drinking water per occupant, see Appendix B and Chapter 8. 3. Start to assemble materials and tools. Those listed are for the illustrated 4-person shelter with a room 11 feet long. Essential materials and tools. Degree saw, bow saw or crosscut preferred, and/or axe for cutting poles to the lengths and diameters illustrated. Degree shovels, 1 for each 2 workers. Degree pick, if the ground is hard. Degree rainproof roof materials, very important in rainy, cold weather. At least 2 square yards of such material per person would be required. 3 square yards per person would be better. Shower curtains, plastic tablecloths, plastic mattress covers, canvas, and the like can be used. Also needed are 2 pieces of plastic or tightly woven cloth, each about $62 by 61.2 feet, to make canopies over the 2 shelter openings. Degree materials and tools for building a simple shelter ventilating pump. A cap 22 in wide and 36 in long. See Appendix B. Only in cold or continuously breezy, cool weather can tolerable temperatures and humidities be maintained for days in a crowded underground shelter that lacks an air pump. Book page 165. Degree containers for storing adequate water. See Chapter 8. B. Useful materials and tools. Degree large cans, buckets, and/or pots with bale handles in which to carry earth and later to store drinking water and human wastes. Degree 2 bedsheets and 2 pillowcases per person for covering cracks between roofing logs, making sandbags, and improvising bedsheet hammocks and bedsheet chairs. Degree a file. Degree a measuring tape, yardstick, or ruler. Degree rope, or strong wire, 100 feet, to make earth-retaining pole walls close to the shelter openings, as explained in Step 19, and for hammock supports, etc. Degree chainsaw, pick mattock, hammer, hatchet, pliers. Degree kerosene, turpentine, or oil to keep hand saws from sticking in gummy wood. Degree expedient life support items recommended in this book. Degree mosquito netting or window screen to cover the openings, if mosquitoes or flies are likely to be a problem. 4. To save time and work, sharpen all tools and keep them sharp. 5. Wear gloves from the start. Even tough hands can blister after hours of chopping and digging, and become painful and infected. 6. If possible, select a location for the shelter that is in the open and at least 50 feet from a building. 9R woods. Remember that on a clear day the thermal pulse, flash of heat rays, from a very large nuclear explosion may cause fires as far away as 25 miles. 7. If the site chosen is on a steep slope, locate the shelter with its length crosswise to the direction of the slope. 8. Stake out the outlines of the trench. Driving stakes is indicated in Figure 8.2. L at the end of Appendix 8.2. If more than 4 persons are to be sheltered, increase the length of the shelter room by 2 feet 9 in. For each additional person. 9. Clear the ground of saplings and tall grass within 10 feet of the staked outlines so that later the excavated earth can be easily shoveled back onto the completed shelter roof. 10. Start digging, throwing the first earth about 10 feet beyond the staked outlines of the trench. Less able members of the family should do the easier digging, near the surface. Those members who can use an axe and saw should cut and haul poles. See the introductory section of this appendix for the know-how to make this hard work easier. 11. Pile all excavated earth at least 2 feet beyond the edges of the trench, so roofing poles can be laid directly on the ground. To make sure that the trenches are dug to the specified full widths at the bottoms, cut and use 2 sticks 142 in long and the other 22 in long to check trench widths repeatedly. 12. At the far end of the shelter dig the ventilation trench emergency exit, making it 22 in wide and 40 in deep. This will help provide essential ventilation and cooling. In cold weather or when fallout is descending, canvas or plastic curtains should be hung in the 2 openings to control the airflow. 13. Make and install threshold boards, to keep the edges of earth steps and earth ledges from being broken off. In damp earth, it is best to install threshold boards before roofing the shelter. If boards are lacking, use small poles. 14. Unless the weather is cold, build a shelter ventilating pump a cap 20 in wide x 36 in high. If the weather is cold, building a cap can be safely delayed until after the shelter is completed. A cap should be made before a crisis, or, if possible, before leaving home. 15. Obtain fresh-cut green poles, or, as a second choice, sound, dry, untreated poles. Use no poles smaller in diameter than those specified in the accompanying drawings. For ease in hauling, select poles no more than 50% larger in diameter than those specified. Book page 166. Top previous next. 16. Lay the poles side by side over the trench. Alternate the large and small ends to keep the poles straight across the trench. If roof poles 9 feet long are being used to roof a 5 ft wide trench, be sure to place the roof poles so that their ends extend 2 feet farther beyond one side of the trench than beyond the other side. This will enable shelter occupants, after the stoop-in shelter is completed, to widen the shelter room 2 feet on one side. First, it can be widened to provide a 2 ft wide sleeping ledge. Later, it can be further deepened to make space for additional expedient hammocks or for double bunk beds of poles or boards built on each side of the shelter. 17. For ease and safety later when hanging expedient bedsheet hammocks and bedsheet chairs in the completed shelter, place loose loops around roof poles in the approximate locations given by the diagram on the second shelter drawing, figure 8.2.2. Make these loose loops of rope, or strong wire, or 16 in wide strips of strong cloth, such as 50 cv polyester bedsheet rolled up to form a rope. For making hammocks and seats, see Chapter 14. These are not essential, although decidedly useful. 18. Cover the cracks between the logs with cloth, leaves, clay, or any other material that will keep dirt from falling down between the cracks. Caution: do not try to rainproof this flat roof, and then simply cover it with earth. Water will seep through the loose earth cover, puddle on the flat roofing material, and leak through the joints between pieces of roofing material or through small holes. 19. Place 6 ft long poles, one on top of the other, next to the entrances. This will keep earth to be placed on top of the entryway trenches from falling into the openings. Secure these poles with wire or rope. See View AA1 in Figure 8.2. L. If wire or rope is not available, make earth-filled rolls to hold the earth nearly vertical on the trench roof next to each opening. See the introductory section of this appendix. 20. Mound earth to a center depth of about 18 in over the shelter roof, as shown in View BB1 in Figure 8.2.1. To form the surface of the future buried roof, be sure to slope both sides of the mound. Then smooth its surface and remove sharp roots and stones that might puncture thin rain-proofing materials to be placed upon it. 21. Place the waterproofing material on the buried roof. If small pieces must be used, lay them in shingle-like fashion, starting at the lower sides of the mounded earth. 22. Cover the buried roof with another 18 in of mounded earth, and smooth this final earth surface. 23. Finish the entrances by placing some shorter poles between the 2 longer poles next to each entryway. Bank and pack earth at least 6 in deep around the sides of the entrances, so that rainwater on the ground cannot run into the shelter entrances. 24. Dig surface drainage ditches around the outside of the mounded earth and around the entrances. 25. Place a piece of water-shedding material over each of the entrances, forming an open-ended canopy to keep fallout and rain from the shelter openings. See Figure A in the introductory section of Appendix A. Almost all fallout would settle on these suspended canopies, rather than falling into shelter openings, or would fall off their edges and onto the ground like sand. 26. Hang the cap from the roof of the trench opening into which outdoor air can be felt flowing, so that air will be pumped in the direction of the natural flow of air. If you have no cap, make and use a small directional fan. 27. Fill all available water containers, including pits which have been dug and lined with plastic, then roofed with available materials. If possible, disinfect all water stored in expedient containers, using 1 scant teaspoon of a chlorine bleach, such as Clorox, for each 10 gallons of water. Even if only muddy water is available, store it. If you do not have a disinfectant, it may be possible to boil water when needed. 28. Put all of your emergency tools inside your shelter. 29. As time and materials permit, continue to improve your chances of surviving by doing as many of the following things as possible. 1. Make a homemade fallout meter, as described in Appendix C, and expedient lights. Prudent people will have made these extremely useful items well ahead of time. 2. Make and hang expedient bedsheet hammocks and bedsheet chairs, following the installation diagram shown in Figure A.2.2. 3. Install screens or mosquito netting over the 2 openings, if mosquitoes or flies are a problem. Remember, however, that screen or netting reduces the air flow through a shelter even when the air is pumped through with a cap. 4. Dig a stand-up hole near the far end of the shelter. Make the hole about 15 in diameter and deep enough to permit the tallest of the shelter occupants to stand erect occasionally. Book page 167. Figure A.2.1. Pole-covered trench shelter. ORNLDWG 74-11755R. Book page 168. Fig. A.2.2. Pole-covered trench shelter ORNLDWG 74-11756R. Book page 169. Copyright 2000 Nuclear War Survival Skills. Also see the new Expedient Shelter book. Requires the DJVU plugin. NWSS Contents. Cover. Addition Notes. Table of Contents. Book Order Form. Forward. About the author. Acknowledgements. Introduction. Ch. 1. The dangers. Ch. 2. Warnings and Ch. 3. Psychologic. Ch. 4. Evacuation. Ch. 5. Shelter. Ch. 6. Ventilation. Ch. 7. Protection. Ch. 8. Water. Ch. 9. Food. Ch. 10. Fallout raw. Ch. 11. Light. Ch. 12. Shelter saw. Ch. 13. Surviving. Ch. 14. Expedient. Ch. 15. Improvised. Ch. 16. Minimum PR. Ch. 17. Permanent. Ch. 18. Trans-Pachi. App. Instructio. App. A.1. Door COV. App. A.2. Pole COV. App. A.3. Small pole shelter. App. A.4. Abovegrow. App. A.5. Abovegrow. App. A.6. Above GR. App. B. How to mock. App. C. A. Homemade. App. D. Expedient. App. E. How to mock. App. F. Providing. Selected references. Selected index. Graphics. Nuclear War Survival Skills. Mail Home. App. A.3. Small pole shelter. Protection provided against fallout radiation. 11. When digging with a top. Previous. Next. Protection provided against fallout radiation. Protection factor 1000 PF 1000, if the shelter is covered with at least 3 feet of earth. That is, a person in the open outside this shelter will receive a gamma-ray dose 1000 times greater than he will receive inside the shelter. See drawings at the end of Appendix A.3. Against blast. This shelter is excellent for preventing fatalities if it is built with strong expedient blast doors. It is still quite good if built without them. These instructions are for fallout shelters. The instructions for making blast doors and other essentials for adequate blast protection are given in Appendix D. Without blast doors, occupants are likely to suffer serious injuries above 7 psi. Against fire. Excellent, if sufficiently distant from fires that produce carbon monoxide and toxic smoke. Where practical. In wooded areas with small trees, for builders who have a saw, bow saw, crosscut, or chainsaw, and digging tools. Any location is suitable if the necessary poles may be obtained there. Try to avoid roots. For below ground, semi-buried, or above-ground construction. However, above-ground construction requires the excavation and movement of so much earth that it is not practical for two-day construction by families with only hand tools. For whom practical? For families or other groups with most members able to work hard 12 hours a day for 2 days. Most people do not realize how hard and long they can work if given a strong incentive. Capacity. The drawings and lists of materials given in these instructions are for a 12-person shelter. For each additional occupant beyond 12, add 1 foot to the length of the shelter room. This shelter requires less work and materials per occupant if its room is sized for about 24 persons, because the entrances are the same regardless of the length of the room. To make the shelter room twice as long, each of the horizontal, ladder-like braces on the floor and near the ceiling of the room can be made with 2 poles on a side, rather than 1 long pole on a side. If the room is sized for more than 24 people, management and hygiene problems become more difficult when it is occupied. For 12 people to live for many days in this shelter without serious hardship, the benches and bunks must be built with the dimensions and spacings given in the illustration. Or, materials must be available for making and suspending 12 expedient bedsheet hammocks that can be converted each day into 12 bedsheet chairs. Building instructions. 1. Study both of the 2 drawings, figure 8.3.1 and 8.3.2 at the end of Appendix 8.3, and read all of these instructions before beginning work. Check off each step when completed. 2. By the time the shelter is finished, plan to have completed 1. A ventilating pump, a cap 24 in wide and 36 in high, essential except in cold weather, and 2. The storage of at least 15 gallons of water per occupant. Book page 170. 3. Start to assemble the required materials. For building a 12-person small pole shelter, the materials are: degree green poles. No pole should have a small end of less diameter than the minimum diameter specified for its use by FIGS. 8.3.1 and 8.3.2. The table below lists the number and sizes of poles needed to build a 12-person small pole shelter. Pole length minimum diameter of small end. Number of poles required width be 6 feet 2 in, 5 in, 2 to 3 featuring 1 in, 5 in, 12 to 2 featuring 4 in, a 5 in, 12 to 10 featuring 8 in, 5 in, 7 feet, 8 feet 8 in, 5 in, 7 feet, 10 feet 6 in, 4 in, 4 to 7 featuring 2 in, 4 in, 47 feet, 5 feet 6 in, a 4 in, 12 to 6 featuring 10 in, 4 in, 3 feet, 6 feet 3 in, 4 in, 8 to 2 featuring 6 in, a 4 in, 16 to 2 featuring 3 in, 4 in, 4 to 5 featuring 2 in, 3 minus 1 half in, 8 feet, 3 feet 10 in, 3 minus 1 half in, 36 feet, 10 ftc 2 in, 12. A to be shortened to fit for cross braces. B width equals the distance measured across a single layer of poles when a sufficient number of poles are laid on the ground side by side and touching, to cover a rectangular area. C for supports during construction. Note: the above list does not include flooring materials, to be placed between the poles of the ladder-like braces on the earth floor. Degree rainproofing materials. Preferably 1/100 featuring roll, 12 feet wide, of 6 mil polyethylene. The minimum amount needed is 200 SQ. Fort. Of 4 mil polyethylene, or 200 SQ. Fort of other waterproof plastic such as tablecloths, shower curtains, and or vinyl floor covering. Also include 100 featuring. Of sticks for use in drainage ditch drains, 1/2 in diameter. Any lengths. Degree nails, wire, and, or cord. 10 pounds of 40-penny nails plus 4 pounds of 16-penny nails are ideal. However, 7 pounds of 16-penny nails can serve. Degree boards for benches and overhead bunks, if bedsheet hammocks are not to be used. Boards are desirable, but not essential. Small poles can be used instead. 2x4 in. Boards 70 feet for frames, or use 3 in diameter poles. 1x8 in. Boards 100 feet, or use 1 to 2 in diameter poles. Degree materials to build a homemade ventilating pump, a cap 24 in. Wide and 36 in. High. See Appendix B, and to store at least 15 gallons of water per occupant, see Chapter 8. 4. Desirable muscle-powered tools for building a 12-person, small pole shelter are listed below. Most builders have succeeded without having this many tools. A backhoe, chainsaws, and other mechanized equipment would be helpful, but not essential. Tools quantity. Axe, long-handle 2-bow saw, 28 in. 2 or 2-man crosscut saw, 1 pick 2 shovel, long-handle 3-claw hammer 2 file, 10 in. 1 steel tape, L0 featuring 1. Also useful. A 50 featuring steel tape and 2 hatchets. 5. To help drain the floor, locate the shelter so that the original ground level at the entrance is about 12 inches lower than the original ground level at the far end of the shelter unless the location is in a very flat area. 6. Stake out the trench for the entire shelter. Even in very firm ground, if the illustrated 12-person shelter is being built, make the excavation at the surface 9 feet 8 in. Wide and 18 feet long, 3 feet longer than the entire length of the wooden shelter. The sloping sides of the excavation are necessary, even in very firm earth, to provide adequate space for backfilling and tamping. The trench illustrated in Figure 8.3. L is 6 feet 4 in. Deep, to minimize work when providing only for excellent fallout protection. For improved blast protection, the trench should be at least 7 feet deep. 7. Check the squareness of the staked trench outline by making its diagonals equal. 8. Clear all brush, tall grass, and the like from the ground, to a distance of 10 feet all around the staked location so that later you can easily shovel loose earth back onto the roof. 9. If the ground is unstable, excavate with sides that are appropriately less steep. 10. When digging the trench for the shelter, use a measuring stick 7 feet 8 in. Long, the minimum bottom width, to repeatedly check the excavation width. Book page 171. Top previous next. 11. When digging with a shovel, pile the earth dug from near ground level about 10 featuring away from the edges of the excavation. Earth dug from 5 or 6 feet below ground level then can easily be piled on the surface only 1 to 5 feet from the edge of the excavation. 12. Finish the bottom of the excavation so that it slopes vertically 1/2 in per foot of length toward the entrance, and also slopes toward the central drain ditch. Later, sticks covered with porous fabric should be placed in the ditches, to serve like a crushed rock drain leading to a sump. 13. While some persons are excavating, others should be cutting green poles and hauling them to the site. Cut poles that have tops no smaller than the specified diameters for each type of pole, not including the bark. 14. For ease in handling poles, select wall and roof poles with top diameters no more than 50% larger than the specified minimum diameters. 15. Sort the poles by size and lay all poles of the same size together, near the excavation. 16. Before the excavation is completed, start building the ladder-like, horizontal braces of the shelter frame. Construct these braces on smooth ground near the excavation. Place 2 straight poles, each 10 feet 6 in. Long, with small end diameters of 4 in. On smooth ground, parallel and 6 feet 2 in. Apart. Hold these poles securely so that their outer sides are exactly 6 feet 2 in. Apart, by driving 2 pairs of stakes into the ground so that they just touch the outsides of the 2 long poles. Each of the 4 stakes should be located about 1 foot from the end of a pole. To keep the 10 feet 6 in poles from being rotated during the next step, nail 2 boards or small poles across them perpendicularly as temporary braces, about 4 feet apart. Then with an axe or hatchet, slightly flatten the inner sides of the 2 poles at the spots where the ends of the 6 cross brace poles will be nailed. Next, saw each cross brace pole to the length required to fit snugly into its place. Finally, toenail each cross brace pole in place, preferably with 2 40-penny nails in each end. 17. Place the lower, ladder-like horizontal brace of the main room on the floor of the completed excavation. 18. Build the frame of the main room. Near the four corners of the room, secure 4 of its wall poles in their final vertical positions by nailing, wiring, or tying temporary brace poles to the inner sides of these 4 wall poles and to the inner sides of the 2 long poles of the ladder-like horizontal brace on the bottom of the excavation. To keep the 2 pairs of vertical wall poles exactly 6 feet 2 in apart until the upper ladder-like horizontal brace is secured in its place, nail a temporary horizontal brace across each pair of vertical poles, about 1 foot below their tops. 19. To support the upper ladder-like horizontal brace, nail blocks to the inner sides of the 4 vertical wall poles, as shown in the lower right-hand corner of the pictorial view, figure 8.3.2. If you have large nails, use a block about 3 in thick and 6 in long, preferably cut from a green, 4 in diameter pole. 20. In the finished shelter, do not leave any vertical support poles under the long poles of the upper ladder-like horizontal brace. To do so would seriously reduce the usable space along the walls for benches, bunks, and occupants. 21. While some workers are building the frame of the main room, other workers should make the 4 ladder-like horizontal braces for the 2 entrances, then make the complete entrances. To keep the ladder-like horizontal braces square during construction and backfilling, nail a temporary diagonal brace across each one. 22. When the 4 wall poles and the 2 ladder-like horizontal braces of the main room are in place, put the remaining vertical wall poles in place, touching each other, until all walls are completed. When placing the wall poles, keep them vertical by alternately putting a butt and a top end uppermost. Wall poles can be held in position by backfilling and tamping about a foot of earth against their lower ends, or they can be wired in position until backfilled. 23. Be sure to use the 2 5 in diameter poles, 6 feet 2 in long, by placing one next to the top and the other next to the bottom of each of the main doorways to the room. Study the drawings. Use braces, each 2 feet 3 in long, to hold apart the top and bottom of each doorway, thus making sure that a 24 in wide air pump can swing in either doorway. 24. To prevent earth from coming through the cracks between wall poles, cover the walls with cloth, plastic, rugs, roofing, or even cardboard. If none of these are available, use sticks, twigs, or grass to cover the wider cracks. Book page 172. 25. After all horizontal bracing and vertical wall poles are in place, begin backfilling, putting earth between the walls and trench sides. Pay particular attention to the order of filling. The earth fill behind all the walls must be brought up quite evenly, so that the earth fill behind one side is no more than 12 in higher at any one time than the earth on the opposite side. Lightly tamp the earth fill in 6 in layers. A pole makes a good tamper. Do not use a mechanical tamper. 26. Next, lay the roof poles side by side, touching each other on top of the wall poles. Cover at least the larger cracks with plastic, roofing, boards, or sticks to keep earth from falling through. If the earth is sandy, cover the whole roof with some material such as bedsheets or plastic to keep sand from running through the cracks. Caution: do not try to rainproof this flat roof and simply cover it with earth. If you do, water will seep straight through the loose earth cover, puddle on the flat roofing material, and leak through the joints between pieces of roofing material or through small holes. 27. Mound earth over the shelter, piling it about 15 in deep along the centerline of the roof and sloping it toward the sides of the roof, so that the earth is only about 2 in deep over the ends of the roof poles. Preparatory to mounding earth onto the roof, place grade stakes in position so you will be able to know the locations and depths of roof poles as you cover them. Continue these slopes to 2 side drainage ditches. Smooth this mounded earth with a rake or stick and remove any sticks or rocks likely to puncture the rainproof roofing material to be laid on it. 28. Place rainproofing material on top of the smooth, mounded earth as shown in sections of the drawings in Figure 8.3. L to make a buried roof. Plastic film, such as 4mm polyethylene, is preferable. Roofing material, plastic shower curtains and tablecloths, or canvas can also be used. Be sure to overlap adjoining pieces. 29. Place the rest of the earth cover over the shelter, being sure that the corners of the shelter have at least 2-1/2 featuring of earth over them. Mound the dirt, smoothing its surface so that water will tend to run off to the surface drainage ditches, which should be dug all around the edges of the mounded earth. 30. Build the benches and overhead bunks. If boards are available, use them. If not, use small, straight poles. On each side, build a row of benches and bunks 9 feet long, centered in the shelter. In order to use the shelter space to the greatest advantage, make the heights and widths of the benches and bunks the same as the thoroughly tested heights, 14 in. And 4 feet 5 in. And widths, 16 in. And 24 in. Given by figure 8.3.2. Also be sure to space their vertical supports 3 feet apart so 2 adults can sit between each pair of vertical bunk supports. 31. Narrow the ends of the overhead bunks so that the aisle between them is about 28 in. Wide for a distance of 38 in. From each doorway. This allows room for installation and operation of an expedient air pump, a cap for prevention of dangerous overheating in warm weather. 32. Place a canopy, open on all sides, over each entrance, to minimize the entry of sand-like fallout particles or rain. 33. To improve the floor, lay small poles between the lower brace poles, so that the floor is approximately level. Or, use sticks covered with scrap boards. 34. Fill all available water containers, including pits which have been dug and lined with plastic, then roofed with available materials. If possible, disinfect all water stored in expedient containers, using 1 scant teaspoon of a chlorine bleach, such as Clorox, for each 10 gallons of water. Even if only muddy water is available, store it. If you do not have a disinfectant, it may be possible to boil water when needed. 35. Put all of your emergency tools inside your shelter. 36. As time and materials permit, continue to improve your chances of surviving by doing as many of the following things as possible. 1. Make a homemade fallout meter, as described in Appendix C, and expedient lights. Prudent people will have made these extremely useful items well ahead of time. 2. Install screens or mosquito netting over the 2 openings, if mosquitoes or flies are a problem. Remember, however, that screen or netting reduces the air flow through a shelter, even when the air is pumped through with a cap. Book page 173. Expedient ventilation and cooling. Those workers who are to work only on the shelter itself, if pushed for time, need not read this section before beginning their work. Install a cap, one that is 24 in wide and 36 in height near the top of the doorway through which you can feel air naturally flowing into the shelter room at that time. If the direction of the natural air flow changes, move the cap to the other opening. To enable the cap to efficiently pump fresh air from the outdoors all the way through the shelter, block the lower half of the doorway in which the cap is installed with a quickly removable covering, such as a plastic-covered frame made of sticks. Be sure to connect the cap's pull cord only 11 in below its hinge line. This prevents excessive arm motions which would cause unnecessary fatigue. If short of time or materials, make a small directional fan. In windy or cold weather, control the natural flow of air through the shelter by hanging adjustable curtains in the doorways at both ends, and/or by making and using trapdoors on the tops of the vertical entryways. For adjustable curtains, use pieces of plastic, each with a supporting stick attached to its upper edge. This allows for different sized openings in the doorways. 1. An opening under the lower edge of the adjustable curtain at the air intake end of the room, and 2. An opening over the top of the curtain at the air exhaust end of the room. In cold weather, this arrangement usually will provide adequate chimney-type ventilation for the shelter without using an air pump. Book page 174. Figure 8.3.1. Plan and elevation of small pole shelter, ORNLDWG 71-3428R4, book page 175. Figure 8.3.2. Pictorial view of small pole shelter, ORNLDWG 71-3429R3, book page 176. Copyright 2000 Nuclear War Survival Skills. Also see the new Expedient Shelter book. Requires the DJVU plugin. NWSS contents. Cover. Addition notes. Table of contents. Book order form. Forward. About the author. Acknowledgements. Introduction. Ch. 1. The dangers. Ch. 2. Warnings and Ch. 3. Psychologic. Ch. 4. Evacuation. Ch. 5. Shelter. Ch. 6. Ventilation. Ch. 7. Protection. Ch. 8. Water. Ch. 9. Food. Ch. 10. Fallout. Raw. Ch. 11. Light. Ch. 12. Shelter. Saw. Ch. 13. Surviving. Ch. 14. Expedient. Ch. 15. Improvised. Ch. 16. Minimum PR. Ch. 17. Permanent. Ch. 18. Transpachi. App. Instructio. App. 8.1. Door. COV. App. 8.2. Pole. COV. App. 8.3. Small PO. App. 8.4. Aboveground. Door covered shelter. App. 8.5. Abovegrow. App. 8.6. Above GR. App. B. How to mock. App. C. A. Homemade. App. D. Expedient. App. E. How to mock. App. F. Providing. Selected references. Selected index. Graphics. Nuclear war survival skills. Mail home. App. 8.4. Aboveground. Door covered shelter. Protection provided against fallout radiation. 7. Pack earth onto the part of the folded down sheet that is in the narrow top. Previous. Next. Protection provided against fallout radiation. Protection factor about 200 pf 200, if covered with 30 in of earth. A person in the open outside this shelter would receive about 200 times more fallout radiation than if he were inside. The drawing at the end of Appendix 8.4 shows the earth cover only 20 in thick, resulting in a pf of about 100. Against blast. Better protection than most homes. Blast tests have indicated that this shelter would be undamaged at least up to the 5 psi overpressure range from large explosions. Without blast doors, the shelter's occupants could be injured at this overpressure range, although probably not fatally. Against fire. Fair, if the cloth in the entries is covered with mud and if the shelter is sufficiently distant from fires producing carbon monoxide and toxic smoke. Where practical. In a location where at least one hollow core door per occupant is available, where a dry trench at least 14 inches deep can be dug without difficulty, but the water table or rock is too close to the surface for a covered trench shelter to be practical. A family evacuating in a pickup truck or large station wagon can carry enough doors, with doorknobs removed. Strong boards at least 6 feet long and at least 1 full inch thick, or plywood at least 3/4 inch thick, also can be used to roof this shelter and to support its overhead earth shielding. Warning. Some doors with single thickness panels if loaded with earth will break before they bend enough to result in protective earth arching. For whom practical. For a typical family or other group with 2 or more members able to work hard for most of 36 hours. Very little building skill is needed. An urban family of 6, with 14 and 12-year-old sons and 13 and 9-year-old daughters, completed this shelter, size for 6 persons, in 1 long working day, 13 hours and 43 minutes after receiving the step-by-step, will illustrated instructions at their Florida home 10 miles from the rural building site. This family used its pickup truck to carry them, the interior doors, and other survival items. Capacity. The shelter illustrated in Figure 8.4 is the minimum length for 4 persons. It is roofed with 6 doors. For each additional person, add another door. If more than about 7 persons are to be sheltered, build 2 or more separate shelters. Building instructions. 1. Before beginning work, study the drawing and read all of the following instructions. Divide the work so that some will be digging while others are building an air pump, storing water, etc. Check off each step when completed. 2. By the time the shelter is finished, plan to have completed a ventilating pump, a 16 in wide by 24 in high cap essential except in cold weather, and the storage of 15 gallons of water per occupant. See Appendix B in Chapter 8. 3. Start to assemble the materials and tools needed. For the illustrated 4-person shelter, these are essential materials and tools. Degree 6 doors. Boards or plywood at least 5/8 in. Thick can be used to replace one or more of the doors. Degree at least 4 double bed sheets for each of the first 4 persons, and 3 double bed sheets for each additional person to be sheltered, or enough pieces of fabric and or of plastic to cover at least as large an area as the sheets would cover. This material is for making above-ground shelter walls, to serve as sandbags. Degree rainproofing materials: plastic film, shower curtains, plastic tablecloths, mattress protectors, etc. 15 square yards for the first 4 persons and 2-1/2 square yards for each additional person. Book page 177. Degree: a shovel, 1 shovel for each 2 workers is desirable. A pick or mattock if the ground is very hard. Degree: a knife, the only essential tool for making a small shelter ventilating cap, and materials for a cap 16 in wide and 24 in high. See Appendix B. Degree: containers for storing water. See Chapter 8. B. Useful materials and tools. Degree: 2 or more buckets, large cans and or large pots with bale handles to carry earth, and later to store water or wastes. Degree: saw, or axe or hatchet, to cut a few boards or small poles. Degree: hammer and at least 15 small nails, at least 2-1/2 in long. Degree: tape measure, yardstick, or ruler. Degree: additional cloth and, or plastic equivalent in size to 2 more double bed sheets for each person. Degree: additional waterproof material, 2 more square yards per person. Degree: pillowcases, or cloth or plastic bags to serve as earth-filled sandbags. The more, the better. 4. To save time and work, sharpen all tools and keep them sharp. 5. Wear gloves from the start, to help prevent blisters and infections. 6. Select a building site where there is little or no chance of the ground being covered with water, and where the water table, groundwater level, is not likely to rise closer than 18 inches to the surface. 7. To avoid the extra work of digging among roots, select a site away from trees, if practical. 8. To lessen the dangers of fire and smoke from nearby houses or trees that might catch fire, locate your shelter as far as is practical from houses and flammable vegetation. 9. Before staking out your shelter, provide 1 door per person to roof the main room plus 1 additional door for each of the 2 entries. Be sure the door knobs have been removed. Use the 2 widest doors to roof the entries. 10. To be sure that all the walls will be in the proper positions to be roofed with the available doors, lay all the doors on the ground, touching each other and in the same relative positions they will have when used to roof the shelter. When all the roof doors are on the ground, side by side, determine the exact length of the shelter room. Note that Figure 8.4 illustrates a shelter sized for only 4 persons. 11. Stake out the shelter. 12. Make the earth-filled rolls that will form the above-ground walls of your shelter. To make walls out of the rolls. 1. Use doors as vertical forms to hold the earth-filled rolls in place until the walls are completed. These are the same doors that you will use later to roof the shelter. 2. Brace the door forms with 36 in long braces, boards or sticks, that press against the doors, as shown in Figure 8.4. Nail only the upper braces, using only very small nails. 3. After the forms for the 2 inner sides of the shelter have been finished, put parts of the long sides of bedsheets on the ground, as illustrated. Or use other equally wide, strong cloth or plastic material. About a 2 feet width of cloth should be on the ground, and the rest of each sheet should be folded up out of the way, over the outsides of the door forms. Adjacent sheets should overlap about 1 foot when making a roll that is longer than 1 sheet. 4. Shovel earth onto the parts of the sheet on the ground to the height of the rolls you are making, as shown. Note that the roll to be made on one side is 2 in higher than the roll on the other side. 5. Shape the surface of the shoveled-on earth as illustrated, to hold the hooks of cloth to be formed when the exposed sides of the sheets are folded down. 6. Fold down the upper side of each sheet while pulling on it to keep it tight and without wrinkles. It should lie on the prepared earth surface, including the small narrow trench, as illustrated in the first section of this appendix. Book page 178. Top previous next. 7. Pack earth onto the part of the folded down sheet that is in the narrow, shallow trench. Then, as shown in the sketches at the bottom of the accompanying drawing, fold back the loose edge over this small amount of packed earth to form a hook. The hook keeps the weight of the earth inside a roll from pulling the cloth out of its proper position. 8. Make a roll first on one side of the shelter, then on the other, to keep the heights of the earth on both sides of the shelter about equal. This will keep the unequal heights of earth from pushing the door forms out of their vertical positions. 9. Add additional earth on top of the rolls so that the height of the level earth surface, out to the full width of a roll, is the same as the height of the cloth-covered part of the roll that is against the door form. 10. When the roll walls have been raised to their planned heights on both sides of the shelter, remove the braces and the door forms, being careful to keep the brace nails from damaging the doors. 11. The door forms of the side walls of the shelter can be removed before building the end walls. 13. When smoothing the earth surfaces of the final tops of the roll walls on both sides, check to see that they have the same slope as the lower sides of the roof doors will have after they are placed on the roll walls. A slope is necessary so that rainwater reaching the waterproof covering to be placed over the doors will run off the lower side. Study figure 8.4. 14. After the side walls have been completed, except for their ends that form the sides of an entry, and after the door forms have been removed, use the same doors for forms to build the 222-in wide entries. 15. Use earth-filled sandbags, made of pillowcases or sacks, or the tucked-in ends of earth-filled rolls, to make the outer ends of each entryway. 16. Make the 2 doorway frames if lumber, nails, and a saw are available. Make each frame as high as the wall on each side of it, and slope the top board of each frame so that it will press flat against the door to be supported. If materials for a frame are lacking, place a single 2x4-in board or a pole about 6 featuring long across the top of the entry, in the position shown in figure 8.4 for the top of the doorway frame. 17. After carefully removing all the temporary braces from the door forms and the doors themselves, improve the slopes of the tops of all supporting walls so that the doors will be supported evenly and, without being twisted, will make contact with the smooth, sloping earth or cloth upon which they will rest. 18. If more than enough waterproof plastic or similar material is available to cover all the roof doors, also cover the tops of the walls on which the roof doors will rest. This will keep the doors from absorbing water from damp earth. 19. Dig the illustrated 14-in deep, 36-in wide trench inside the shelter. If the water table is too high to dig down 14-in, in some locations the walls can be raised to a height of 38-in by cutting turf sods and laying them on top of the walls. Another way the wall height can be increased is by making additional rolls. 20. Place the roof doors in their final positions, and cover them with waterproof material, if available. Be sure the waterproof material is folded under the higher edges of the doors to keep the material from slipping downward on the sloping doors as earth is shoveled onto the roof. 21. Extend the waterproof material on top of the doors a couple of feet beyond the lower ends of the doors if enough material is available to cover all of the roof doors. 22. When shoveling the first layer of earth onto the rainproof material protecting the doors, avoid hitting and possibly puncturing it with rocks or sharp-pointed roots in the earth. 23. To make earth arching more effective in supporting most of the earth to be placed on the roof doors, first mount earth on and near the ends of the doors. 24. Cover the roof with at least 20-in of earth. Make sure that there also is a thickness of at least 20-in of earth at the corners of both the room and entries. Book page 179. 25. To prevent surface water from running into the shelter if it rains hard, mound packed earth about 5-in high just inside the 2 entries. Rain can be kept out by a small canopy or awning that extends 2 or 3 feet in front of the outermost edge of a doorway that roofs an entry. 26. If any waterproof material remains, use it to cover the floor of the shelter. 27. If the weather is warm or hot, install a 16 in wide by 24 in high air pump, a cap. Attach its hinges to the board across the roof of the entry into which outside air is moving naturally at the time. If short of time or materials for a cap, make a small directional fan. 28. Cover all exposed combustible material with mud, earth, or other fireproof material, to reduce the chance of exposed cloth being ignited from a nuclear explosion or heat from a nearby fire. 29. Fill all available water containers, including pits which have been dug and lined with plastic, then roofed with available materials. If possible, disinfect all water stored in expedient containers, using 1 scant teaspoon of a chlorine bleach, such as Clorox, for each 10 gallons of water. Even if only muddy water is available, store it. If you do not have a disinfectant, it may be possible to boil water when needed. 30. Put at least your most useful emergency tools inside your shelter. 31. As time and materials permit, continue to improve your chances of surviving by doing as many of the following things as possible. 1. Make a homemade fallout meter, as described in Appendix C, and expedient lights. Prudent people will have made these extremely useful items well ahead of time. 2. Install screens or mosquito netting over the 2 openings, if mosquitoes or flies are a problem. Remember, however, that screen or netting reduces the air flow through a shelter even when the air is pumped through with a cap. Book page 180. Figure 8.4. Above ground, door covered shelter. ORNLDWG 748132R, book page 181. Copyright 2000 Nuclear War Survival Skills. Also see the new Expedient Shelter book. Requires the DJVU plugin. NWSS contents. Cover. Addition notes. Table of contents book order form forward. About the author acknowledgements introduction. Ch. 1. The dangers. Ch. 2. Warnings and Ch. 3. Psychologic. Ch. 4. Evacuation. Ch. 5. Shelter. Th. Ch. 6. Ventilation. Ch. 7. Protection. Ch. 8. Water. Ch. 9. Food. Ch. 10. Fallout raw. Ch. 11. Light. Ch. 12. Shelter saw. Ch. 13. Surviving. Ch. 14. Expedient. Ch. 15. Improvised. Ch. 16. Minimum PR. Ch. 17. Permanent. Ch. 18. Trans-Pachi. App. Instructio. App. 8.1. Door COV. App. 8.2. Pole COV. App. 8.3. Small PO. App. 8.4. Abovegrow. App. 8.5. Aboveground, ridgepole shelter. App. 8.6. Above GR. App. B. How to mock. App. C. A. Homemade. App. D. Expedient. App. E. How to mock. App. F. Providing. Selected references. Selected index. Graphics. Nuclear War Survival Skills. Mail Home. App. 8.5. Above ground, ridgepole shelter. Protection provided against fallout radiation. B. Useful tools and materia. Top previous next. Protection provided against fallout radiation. Protection factor 300 PF 300, if covered with 24 in of earth. A person in the open outside this shelter would receive about 300 times more fallout radiation than if he were inside. See the accompanying drawing at the end of Appendix 8.5. Against blast. Better protection than most homes. Blast tests have indicated that this shelter would be undamaged at least up to the 5 psi overpressure range from large explosions. Without blast doors, the shelter's occupants could be injured at this overpressure range, although probably not fatally. Against fire. Good, if the shelter is sufficiently distant from fires producing carbon monoxide and toxic smoke. Where practical. In many wooded areas and wherever enough poles are available. In locations where below-ground expedient shelters are impractical because the water table or rock is too close to the surface for a covered trench shelter. For whom practical? For a family or other group with 5 or more members able to work hard for most of 48 hours, with at least one member able to saw and fit poles and use the hand tools listed on the following page. A group of rural Florida families, with 12 of the 15 members able to work, completed a shelter like this 23 hours and 40 minutes after receiving the step-by-step, well-illustrated instructions 12 miles from the wooded building site. They used only muscle-powered tools, and moved over 50 tons of sandy shielding earth. Capacity. The shelter illustrated in Figure 8.5 is the minimum length for 5 persons. For each additional person, add 1 foot to the length of the ridgepole and shelter room. If more than about 15 persons are to be sheltered, build 2 or more separate shelters. Building instructions. 1. Before beginning work, study Figure 8.5 and read all of the following instructions. 2. Divide the work. Check off each step when completed. 3. By the time the shelter is finished, plan to have completed a ventilating pump, a cap 20 in wide and 26 in high, essential for this shelter except in cool weather, and the storage of at least 15 gallons of water per occupant. See Appendix B in Chapter 8. 4. Start to assemble the materials. For the illustrated 5-person shelter, these are essential materials and tools. Degree poles. Fresh cut, green poles are best, sound, untreated poles are satisfactory. See the following list for the number of poles required for a 5-person shelter. Book page 182. Use pole length minimum diameter of small end. Number of poles required width when all are laid on the ground. For main room. Ridgepole 4 feet 9 in. 6 in. 1 column posts 4 feet 3 in. 5 in. 2. Footing log 8 feet 0 in. 6 in. 1 cross braces 6 feet 2 in. 3 in. 2. Roof poles 9 feet 0 in. 4 in. 5 feet of vertical end wall poles 5 feet 0 in. 3-1/2 in. 14 feet B slanting end wall poles and extras. 6 feet 6 in. 3-1/2 in. 18 feet B. For outer sections of entryways. Horizontal poles 8 feet 0 in. 3-1/2 in. 4 cross braces material for 16, 5 feet 0 in. 3.5 in. 6 wall poles 3 feet 4 in. 3 in. 32 feet B roof poles 2 feet 8 in. 2-1/2 in. 12 feet B. For inner sections of entryways. Long, sloping poles 14 featuring 0 in. 4 in. 4. Cross braces 1 foot 8 in. C. 4 in. 8. Vertical support poles 4 feet 0 in. C. 4 in. 8. Roof poles 3 feet 0 in. 2-1/2 in. 13 feet B. This width equals the distance measured across the tops of a single layer of poles when a sufficient number of poles are laid on the ground side by side with all the same ends in a straight line and touching. These poles will be placed butt ends down to form the walls of the shelter room. B. This width equals the distance measured across a single layer of poles when a sufficient number of poles are laid on the ground side by side and touching, with large ends and small ends alternating so to cover a rectangular area. C. To be cut into the various lengths needed to close the ends of the main room and also to close a part of each entryway. Degree a saw and an axe or hatchet, to cut green poles. A bow saw or crosscut saw serves well and often is more dependable than a chainsaw. Having an extra blade for a bow saw may be essential. Degree 2 shovels, 1 shovel for each 2 workers is desirable. A pick will also be needed, if the earth is hard. Degree large buckets, cans, or pots with bale handles in which to carry earth, and later to store water or wastes. Degree a knife. Degree a hammer and at least 80 nails, 3 in or longer. If these are not at hand, rope, wire, or strips of cloth can be used to lash poles together. At least 200 featuring of rope or strong wire will be needed, or 2 additional bed sheets for each person to be sheltered. Other fabric of equal strength can be used. The cloth can be cut or torn into foot-wide strips and twisted slightly to make rope. Degree 3 double bed sheets for the illustrated 5-person shelter or a piece of strong fabric or plastic of about the same size. 1 additional sheet for each additional 2 occupants. If sufficient sheets or other material are not available, use many sticks and small poles, placed across the 9 featuring side poles. Degree at least 2 square yards per person of rainproofing material, shower curtains, plastic tablecloths, plastic mattress covers, or the like, essential in rainy, cold weather. Degree materials for building a ventilating pump, a cap 20 in wide and 26 in high. See Appendix B. Degree containers for storing 15 gallons of water per occupant. See Chapter 8. Top previous next. B. Useful tools and materials. Degree additional saws, axes, hatchets, shovels, and large buckets or cans. Book page 183. Degree a chainsaw if there is a person in the group who is skilled at operating one. Degree kerosene, turpentine, or oil to keep a handsaw from sticking in green, gummy wood. Degree a measuring tape, yardstick, or ruler. Degree 1 bed sheet for each person to be sheltered, or a piece of strong fabric or plastic of about the same size. Degree a total of 40 square yards of rainproofing materials for the illustrated 5-person shelter and 3-1/2 square yards for each additional person. Even thin plastic will serve for the buried roof. 5. To save time and work, sharpen all tools and keep them sharp. 6. Wear gloves from the start. Even tough hands can blister after hours of digging and chopping and can become painful and infected. 7. Select a shelter location where there is little chance of the ground being covered with water if it rains hard. If you are sure the water table will not rise to cover the floor of a shallow excavation, you can save work by first lowering the area of the planned main room by a foot or 2. After the shelter is roofed, the excavated earth can be shoveled back to help cover the completed pole roof. To avoid the extra work of cutting roots when excavating earth, select a site at least as far away from a tree as the tree is tall. 8. For a shelter that is completely above ground, clear grass, weeds, etc. from the area where the shelter is to be built. This reduces the possible problem of chiggers, ticks, etc. Do not remove any earth at this stage. 9. Stake out the entire shelter. Check the squareness of the shelter room by making its diagonals equal. Then drive 2 lines of stakes to mark the outside edges of the completed earth covering. Place these stakes 4 feet outside the future positions of the lower ends of the roof poles. 10. Check the squareness of the future floor area inside the 2 lines marking where the 2 V-shaped, 4 in deep trenches will be dug, to secure the lower ends of the sloping side poles of the room. These 2 parallel lines are 14 featuring 6 in apart. When the 2 diagonals joining the ends of these 2 parallel lines are equal in length, the area between them has square corners. 11. While some persons are staking out the shelters, others should be cutting green poles and hauling them to the site. Cut poles that have tops with diameters, excluding bark, no smaller than the diameters specified on the illustration for each type of pole. 12. To make the hauling and handling of the longer poles easier, select poles with top diameters no more than 50% larger than the specified minimum diameters. 13. Sort the poles by length and diameter and lay all poles of each size together, near the excavation. 14. As soon as poles are brought to the site, some workers should start building the 4 ladderlike horizontal braces for the entryways to avoid delays later. Study the drawing. Then construct these braces on smooth ground near the excavation. Place 2 straight poles, each 8 feet long, with small end diameters of 3-1/2 in. On smooth ground, parallel and so that their outer sides are 3 feet apart. Hold these poles securely so that their outer sides are exactly 3 feet apart, by driving 2 pairs of stakes into the ground so that they just touch the outsides of the 2 long poles. Each of the 4 stakes should be located about 1 foot from the end of a pole. To keep the 8 featuring poles from being rotated during the next step, nail 2 boards or small poles across them perpendicularly, as temporary braces, about 4 feet apart. Then with an axe or hatchet, Slightly flatten the inner sides of the two poles at the spots where the ends of the 4 cross brace poles will be nailed. Next, saw each cross brace pole to the length required to fit snugly into its place. Finally, toenail each cross brace pole in place, preferably with 2 large nails in each end. 15. If more than 5 persons are to be sheltered, use 3 column posts for 6 to 9 persons, and 4 column posts for 10 to 14 persons. 16. For each additional person beyond 5, make the ridgepole and the footing log each 1 foot longer than shown in Figure 8.5. Book page 184. 17. After notching the footing log, see drawing, place it in a trench dug deep enough so that the bottoms of its notches are about 4 inches below the surface of the ground. 18. Carefully dig the 4 in deep, V-shaped, straight trenches in which the lower ends of the 9 featuring wall poles will rest. Dig each of these 2 parallel trenches 7 feet 3 in from the center line of the footing log. 19. Carefully notch A, B, only about 1/4 in deep in the top of each of the 2 outer column posts. Then saw off the other ends so that each is 4 feet 3 in long. When they are placed on the notched footing log and the ridgepole is placed on them, the upper side of the ridgepole will be about 4 feet 4 in above the ground. 20. Place the 2 outer column posts in their notches in the footing log, and secure the base of each column post against sideways movement by placing 2 small diameter, 4 featuring horizontal poles just below the ground level on both sides, as illustrated. Then temporarily place and brace the ridgepole in position. 21. For shelters sized for more than 5 occupants, make and place the inner column post, or posts. To avoid cutting A, B, notched column post too short, first carefully, B, notch each remaining column post, cut it about 1 in too long, and trim it off to fit in its final position under the ridgepole. 22. If nails at least 4 in long are available, nail sloping cross braces to the inner sides of the column posts. If nails are not available, notch slightly bowed cross braces and the column post as illustrated, then lash or wire them in position. Strips of ordinary bed sheets, torn about a foot wide and twisted together slightly, can be made to serve as lashing rope. To hold the tops of the column posts securely against the upper ends of the cross braces, a tightened rope loop that encircles the tops of the column posts can be used. 23. Next put 4 of the larger diameter 9 ft roof poles in position, with the outsides of the outermost 2 roof poles each only about 1 in from an end of the ridge pole. 24. Place the rest of the 9 featuring roof poles in position, making sure that all their small ends are uppermost, and that they are pressed together and overlap on the ridgepole at least as far as illustrated. Pack earth between their lower ends. If the earth is clay, put small spacers of wood between the ends. 25. At each end of the shelter room, build extra shelter space and an entryway. First position 2 14 featuring poles with their upper ends resting on the outermost wall poles. Study Figure 8.5. Place the 2 14 featuring poles 20 in apart, parallel, and equally distant from the centerline of the ridgepole. Nail 4 20 in long spacer poles between each pair of 14 featuring poles, as illustrated. To make sure that the upper ends do not move before earth pressure holds them in place, tie the upper ends of the 4 featuring poles together. Drive a stake against the lower end of each 14 featuring pole, to keep it from slipping outward. Under the center of each 14 featuring pole, place 2 supporting, vertical posts. 26. Dig 4 in deep trenches for the lower ends of the sloping end wall poles of the main room. These poles must be cut to length so that their upper ends will be about 4 in above the outermost 9 featuring roof pole against which they lean. Dig narrow, vertical trenches, about 8 in deep, for all vertical wall poles that do not press against horizontal brace poles near the ground. 27. Start placing the sloping end wall poles. First place the longest pole, then the shorter poles all touching. 28. Across the open spaces between the 9 featuring roof poles, place limbs or sticks roughly horizontally, as shown in the lower left-hand drawing. Be sure to use limbs or sticks that have diameters of at least 1/2 in. And put them no farther apart than 6 in. Leave needles and leaves on the limbs. Do not leave sharp ends sticking upward. Do not place more than a 6-in thick mass of limbs and leaves over the side poles. The thickness of the earth cover necessary for excellent fallout protection might be unintentionally reduced by making the limb cover too thick. 29. Place bed sheets or 4 mm thick polyethylene film or equally sturdy material over the limbs and sticks to keep earth from falling through the roof. 30. To prevent sand or dry earth from falling between the cracks where the poles are side by side, cover these parts of the roof with cloth, plastic, or paper. If these materials are not available, use sticks, leaves, and grass. In tick or chigger season, avoid using grass or leaves from on or near the ground. Book page 185. 31. After the entryways are completed, begin to cover the shelter with earth. Starting from the ground up, put on a full L featuring thickness of earth cover. First raise its height about a foot on one side or end of the shelter, and then on the other repeatedly. This is to prevent unequal loading from tipping the shelter or pushing it over. Do not excavate any earth closer than 3 feet to the line of stakes marking the final outer edge of the completed 2ft thick earth cover. 32. Fill the spaces between the entryways and the main room only with earth. An equal thickness of wood or other light material provides much less protection against radiation. 33. Before placing the rainproofing material for the buried roof, smooth the surface of the L featuring thick earth cover. This will prevent sharp rocks or sticks from puncturing the plastic or other rainproofing material. If you do not have sufficient waterproofing materials to cover the whole roof, use what is available to rainproof the central part, on both sides of the ridgepole. 34. To prevent rainwater on the ground outside from running into the entryways, make mounds of packed earth about 4 inches high across the entryway floors, about 2 feet from their outer ends. Dig a shallow drainage ditch completely around the earth mounded over the shelter. 35. Unless the weather is cold, install your shelter ventilating cap in the entry into which you can feel air moving naturally. If short of time or materials, make a small directional fan. 36. Complete the storage of water and other essentials. 37. To prevent fallout or rain from falling onto the floor of the outer entryways, place a small awning, not illustrated, over each opening. 38. Fill all available water containers, including pits which have been dug and lined with plastic, then roofed with available materials. If possible, disinfect all water stored in expedient containers, using 1 scant teaspoon of a chlorine bleach, such as Clorox, for each 10 gallons of water. Even if only muddy water is available, store it. If you do not have a disinfectant, it may be possible to boil water when needed. 39. Put all of your emergency tools inside your shelter. 40. As time and materials permit, continue to improve your chances of surviving by doing as many of the following things as possible. 1. Make a homemade fallout meter, as described in Appendix C, and expedient lights. Prudent people will have made these extremely useful items well ahead of time. 2. Make and hang expedient bedsheet hammocks. 3. Install screens or mosquito netting over the 2 openings, if mosquitoes or flies are a problem. Remember, however, that screen or netting reduces the air flow through a shelter even when the air is pumped through with a cap. 4. Dig a stand-up hole near the far end of the shelter. Make the hole about 15 in diameter and deep enough to permit the tallest of the shelter occupants to stand erect occasionally. Book page 186. Figure 5. A. Above ground, ridgepole shelter. Book page 187. Copyright 2000 Nuclear War Survival Skills. Also see the new Expedient Shelter book. Requires the DJVU plugin. NWSS Contents. Cover. Addition Notes. Table of Contents Book Order Form Forward. About the Author Acknowledgements Introduction. Ch. 1. The Dangers. Ch. 2. Warnings and Ch. 3. Psychologic. Ch. 4. Evacuation. Ch. 5. Shelter. Ch. 6. Ventilation. Ch. 7. Protection. Ch. 8. Water. Ch. 9. Food. ch. 10. Fallout raw, ch. 11. Light, ch. 12. Shelter saw, ch. 13. Surviving, ch. 14. Expedient, ch. 15. Improvised, ch. 16. Minimum PR, ch. 17. Permanent, ch. 18. Transpachi, app, Instructio, app, 8.1. Door COV, app, 8.2. Pole COV, app, 8.3. Small PO, app, 8.4. Abovegrow, app, 8.5. Abovegrow, app, 8.6. Above ground, crib walled shelter app. B. How to mock, app. C. A. Homemade, app. D. Expedient, app. E. How to mock, app. F. Providing. Selected references. Selected index. Graphics. Nuclear War Survival Skills. Mail Home, app. 8.6. Above ground, crib walled shelter. Protection provided against fallout radiation. 7. Permanently tie together the pair of vertical center brace poles. Top previous next. Protection provided against fallout radiation. Protection factor 200. PF 200 if the earth-filled cribs are built to the full width of 3 feet, as illustrated in Figure 8.6 at the end of these instructions. A person in the open outside this shelter would receive about 200 times as much fallout radiation as he would if inside. If earth is mounted to the top of the walls and 3 feet deep over the roof, the protection factor can be raised to PF 500 or better. See the accompanying drawing at the end of Appendix 8.6. Against blast. Better protection than most homes. Without blast doors, occupants could be injured, although probably not fatally, at lower overpressure ranges than those that would destroy this shelter. Against fire. Poor, if the shelter is built as illustrated. The cloth and outer poles would be unprotected from thermal pulse and other possible sources of intense heat. However, if earth is mounted around the walls so as to cover all exposed cloth and wood, good fire protection would be provided. Where practical. The crib-walled shelter is practical in many wooded areas and whenever enough poles are available, or in locations where below-ground expedient shelters are impractical because the water table or rock is too close to the surface for a covered trench shelter. For whom practical? For a family or group with 3 or more members able to work very hard for most of 48 hours. An unskilled family with an axe or saw and materials found in most American homes can build this shelter. No nails are required. Groups with the nails, tools, skill, and the number of workers required to build a ridgepole shelter are advised to do so. A crib-walled shelter requires almost twice the total length of poles and more work to provide shelter for a given number of persons. Capacity. The shelter illustrated in Figure 6. 1 is the minimum length for 5 persons. For each additional person, add 1-1/2 a foot to the length of the room. If more than about 12 persons are to be sheltered, build 2 or more separate shelters. Building instructions. 1. Before beginning work, study the drawing and read all of the following instructions. 2. Divide the work. Check off each step when completed. 3. By the time the shelter is finished, plan to have completed a ventilating pump, a cap 20 in wide and 26 in high, essential for this shelter except in cool weather, and the storage of at least 15 gallons of water per occupant. See Appendix B in Chapter 8. 4. Start to assemble materials and tools. Essential materials and tools. Degree poles. Fresh cut, green poles are best. Sound, untreated poles are satisfactory. For the illustrated 5-person shelter, the required poles are listed on the following page. Book page 188. Use pole length minimum diameter of small end. Number of poles required width when all are laid on the ground. Sides of longest crib 12-1/2 a foot 3 in. 7 feet sides of middle-sized crib 10 feet 3 in. 7 feet sides of shortest crib 7 feet 3 in. 7 feet. Ends of all cribs 3-1/2 a foot 3 in. 21 feet vertical poles at the corners of all cribs. 3-1/2 a foot 2 in. 56. Main roof 9 feet 3-1/2 in. 12 feet entryway roofs 5 feet. 2-1/2 in. 22 feet. This width is the distance measured across a single layer laid on the ground side by side and touching, with large ends of poles when a sufficient number of them are and small ends alternating so as to cover a rectangular area. Degree: a saw, preferably a bow saw with an extra blade, or a crosscut saw, or an axe for cutting green poles. Degree: containers for storing 15 gallons of water per occupant. See Chapter 8. Degree: a shovel, one for each 2 workers is desirable. Degree: a pick, if the ground is very hard. Degree: 2 to 5 large cans, buckets, or pots with bale handles, in which to carry earth and to store water or wastes later. Degree: a knife. Degree: a minimum of 300 feet of wire at least as strong as clothesline wire. Second choice would be 300 feet of rope, or third choice, 8 double bed sheets that could be torn into one featuring wide strips and twisted slightly to serve as rope. For each additional person beyond 5, supply 20 feet of wire or rope or half a double bed sheet. Degree: rainproof roofing materials at least 2 square yards per person. Such materials as plastic film, shower curtains, plastic tablecloths or plastic mattress covers can be used. These materials are essential for prolonged shelter occupancy in rainy, cold weather. Degree: 15 double bed sheets, or equal square yardage of other strong cloth or plastic. Degree: materials for building a ventilating pump, a cap 20 inches wide and 30 in high. See Appendix B. B. Useful materials and tools. Degree: additional saws and shovels, chain saw, pick, mattock, hammer, hatchet. Degree: kerosene, turpentine, or oil to keep a hand saw from sticking in gummy wood. Degree: a file. Degree: 2 additional double bed sheets per person, or equivalent square yardage of other equally strong fabric or plastic. Degree: a measuring tape, yardstick, or ruler. Degree: old newspapers, about 15 pounds. Degree: a total of 30 square yards of rainproofing materials for the illustrated 5-person shelter, and 3 square yards for each additional person to be sheltered. Even thin plastic will serve to make a rainproof, buried roof. 5. To save time and work, sharpen all tools and keep them sharp. 6. Wear gloves from the start. Even tough hands can blister and become painful and infected after hours of digging and chopping. 7. Select a shelter location where there is little or no chance of the ground being covered with water by a hard rain. Book page 189. 8. If the building site is near the edge of a woods, pick a site at least 40 feet from the nearest trees to avoid roots. 9. Clear off grass, weeds, etc. from the area where you plan to build the shelter. This also will help to avoid chiggers or ticks. Do not remove any earth. 10. Stake out the entire shelter, locating the 6 required cribs. Be sure to make the inside length of the main room equal to the number of persons to be sheltered multiplied by 1-1/2 featuring. The illustrated shelter is sized for 5 persons, and the poles listed are those required for this 5-person shelter. 11. While some persons are staking out the shelter, others should be cutting green poles and hauling them to the site. Cut poles with tops no smaller than the diameters specified. Note: the specified diameters do not include bark. 12. Select poles with small end diameters no more than 50% larger than the specified minimum diameters, to make handling of the long wall and roof poles easier. 13. Sort the poles by length and diameter and lay all poles of each size together, near the excavation. 14. Use larger trees and poles, up to 6 in diameter, to make the 3-1/2 ft long end poles of the cribs, figure 8.6. Do not use poles with small end diameters of less than 3 in. For the side wall poles of the cribs. For vertical brace poles, use poles with diameters of at least 2 in. Cut off at the height of the upper side of the uppermost horizontal poles against which they are tied. 15. Be sure to cut off all limbs so that the poles are quite smooth. Usually it is easier to drag smooth poles to the building site before cutting them into the required lengths. Pull them by the small, lighter ends. 16. Determine if there are enough long poles to make the side poles of the two cribs forming the sides of the shelter room without splicing two shorter poles together. If the shelter is being built for more than 7 persons, it will require side poles that are longer than 15-1/2 featuring. Therefore, if a shelter for more than 7 persons is being built, it would be best to use 2 cribs placed end to end on each side of the shelter room, instead of a single crib as illustrated by figure 8.6. 17. Place the lowermost 4 poles of each of the cribs in their final positions, so that all the bases of the crib walls are in position on the ground. Use the thicker, heavier poles at and near the bottom of each crib. Be sure the room is long enough to provide 1-1/2 featuring of room length for each person to be sheltered. 18. To build each crib. 1. Place 2 3-1/2 featuring end poles on the ground. Put 2 of the side poles on top of the 2 end poles so that the ends of all 4 poles extend 3 in. No more beyond where they cross. The thicker poles should be used first to add stability. 2. Stack additional pairs of end poles and city poles to form the crib, keeping each wall of the crib vertical, until the tops of the uppermost side poles are at least 42 in. Above the ground. To keep the uppermost poles of the crib about level while the crib is being raised, alternate the large ends and small ends of poles. 3. Place a pair of small, vertical brace poles in each of the 4 corners of the crib. The tops of the vertical brace poles should be no higher above the ground than the upper sides of the crib's uppermost horizontal poles. 4. Tie each pair of vertical brace poles together tightly at bottom, middle, and top. For tying, use 3 featuring lengths of strong wire, rope, or slightly twisted, foot-wide strips of cloth at least as strong as cotton bed sheeting. Square knots with backup overhand knots are best, but 3 overhand knots, one on top of the other, will hold. 5. If the crib is more than 8 feet long, place an additional pair of vertical brace poles, with one in position at the outside center of each long crib wall. Tie this pair of vertical brace poles together permanently just above the ground, but not yet in the middle or near the top of the crib. Temporarily tie each of these center vertical brace poles to the uppermost side pole of the wall it touches. 6. Line the crib with cloth or plastic film, making sure that several inches of the lining hangs over the uppermost poles. So that the lining will not be pulled down when the crib is being filled with earth, tie the upper edge of the lining to the uppermost wall pole about every 2 featuring. First, cut a small hole through which to thread a tie string or a 2-in wide tie strip of cloth. If plenty of cloth and/or plastic is available for lining the cribs, secure the lining by simply wrapping a greater width of the upper edge of the lining around the uppermost crib wall pole. Book page 190. Top previous next. 7. Permanently tie together the pair of vertical center brace poles, using horizontal ties at their centers and just below the uppermost horizontal wall poles of the crib. Use the strongest material you have for these horizontal ties across the center of the crib. 8. Excavate earth 10 feet or so beyond the outer sides of the cribs. To save work, carry it in buckets and dump it inside the cribs. 2 children can carry a heavy bucket of earth by running a strong 4 featuring stick through the bale or handle of the bucket and tying the bale to the center of the stick before lifting. Save earth closer to the cribs to put on the roof. 9. Fill the lined crib with earth from which almost all grass, roots, and the like have been removed. Avoid placing hard lumps of earth in contact with the lining. Fill the crib so that the surface of the earth inside it is about 4 in. Above the upper sides of the uppermost horizontal poles. 19. Line the narrow spaces between adjacent cribs with cloth or plastic, then fill these spaces with earth a little at a time, tamping repeatedly so as to avoid leaving air spaces. 20. Place the 9 featuring roof poles over the main room. If poles are unavailable and boards 1-1/2 in thick are available, use 2 thicknesses of boards. Use the strongest roof poles, or double thickness boards nailed together, nearest the entryways. Then put shorter, 5 or 6 featuring poles or boards over the entryways. 21. To keep earth from falling through the cracks between the roof poles, put sticks in the larger cracks and cover the roof with 2 or more thicknesses of cloth, plastic, or other material. Newspapers will do, if better materials are lacking. 22. Put earth on the roof to the depths shown for the illustrated, buried roof. Be sure to slope all sides and smooth this gently mounded earth surface so that the buried roof will shed water. 23. So that the earth cover near the outer edges of the roof will be a full 2 feet thick, make the earth cover slope steeply near the edges. Steep earth slopes can be made and kept stable by using large lumps of turf to make a steep bank, or by using earth-filled rolls of cloth or other material along the edges of a roof. 24. Put in place the waterproof material of the buried roof. 25. Pile on the rest of the earth cover, as illustrated, to at least a full 2 featuring thickness. 26. Smooth the surface of the earth cover, including the sides, so that rain will run off. Do not walk on the finished roof. 27. To prevent rainwater on the ground outside from running into the entryways, make mounds of packed earth about 4 in high across the entryway floors. Make the mounds about 2 feet from the outer ends of the floors. Dig a shallow drainage ditch completely around the shelter. 28. Unless the weather is cold, install your shelter ventilating cap in the entry into which you can feel air moving naturally. If short of time or materials, make a small directional fan. 29. To prevent fallout or rain from falling onto the floor of the outer entryways, place small awnings, not illustrated, over the openings. 30. If time and energy are available, mound earth all around the shelter. Doing so will reduce fire hazards by covering flammable materials. It also will increase fallout protection. 31. Fill all available water containers, including pits which have been dug and lined with plastic, then roofed with available materials. If possible, disinfect all water stored in expedient containers, using 1 scant teaspoon of a chlorine bleach, such as Clorox, for each 10 gallons of water. Even if only muddy water is available, store it. If you do not have a disinfectant, it may be possible to boil water when needed. 32. Put all of your emergency tools inside your shelter. 33. As time and materials permit, continue to improve your chances of surviving by doing as many of the following things as possible. 1. Make a homemade fallout meter, as described in Appendix C, and expedient lights. Prudent people will have made these extremely useful items well ahead of time. 2. Make and hang expedient bedsheet hammocks. 3. Install screens or mosquito netting over the 2 openings, if mosquitoes or flies are a problem. Remember, however, that screen or netting reduces the air flow through a shelter even when the air is pumped through with a cap. 4. Dig a stand-up hole near the far end of the shelter. Make the hole about 15 in diameter and deep enough to permit the tallest of the shelter occupants to stand erect occasionally. Book page 191. Figure 8.6. Above ground, crib walled shelter, ORNLDWG 748130R. Book page 193. Copyright 2000 Nuclear War Survival Skills. Also see the new Expedient Shelter book. Requires the DJVU plugin. NWSS Contents. Cover. Addition Notes. Table of Contents Book Order Form Forward. About the Author Acknowledgements Introduction. Ch. 1. The Dangers. Ch. 2. Warnings and Ch. 3. Psychologic. Ch. 4. Evacuation. Ch. 5. Shelter. Ch. 6. Ventilation. Ch. 7. Protection. Ch. 8. Water. Ch. 9. Food. Ch. 10. Fallout raw. Ch. 11. Light. Ch. 12. Shelter saw. Ch. 13. Surviving. Ch. 14. Expedient. Ch. 15. Improvised. Ch. 16. Minimum PR. Ch. 17. Permanent. Ch. 18. Transpachi. App. Instructio. App. 8.1. Door COV. App. 8.2. Pole COV. App. 8.3. Small PO. App. 8.4. Abovegrow. App. 8.5. Abovegrow. App. 8.6. Above GR. App. B. How to make and use a homemade shelter ventilating pump app. C. A. Homemade. App. D. Expedient. App. E. How to mock. App. F. Providing. Selected references. Selected index. Graphics. Nuclear war survival skills. Mail home. App. B. How to make and use a homemade shelter ventilating pump. I. The need for shelter. A. To form a hem along one of the 30 in. Figure 18. Improvised and quo. Ix. Solutions to special. Top previous next. I. The need for shelter air pumps. In warm weather, large volumes of outside air must be pumped through most fallout or blast shelters if they are crowded and occupied for a day or more. Otherwise, the shelter occupants' body heat and water vapor will raise the temperature-humidity conditions to dangerously high levels. If adequate volumes of outdoor air are pumped through typical below-ground shelters in hot weather, many times the number of persons could survive the heat than otherwise could survive in these same shelters without adequate forced ventilation. Even in cold weather, about 3 cubic feet per minute, 3 cfm, of outdoor air usually should be pumped through shelters, primarily to keep the carbon dioxide exhaled by shelter occupants from rising to harmful concentrations. The Kearny air pump is a practical, do-it-yourself device for pumping adequate volumes of cooling air through shelters with minimum work. The following instructions have been improved repeatedly after being used by dozens of small groups to build caps including families, pairs of housewives, and children. None of these inexpert builders had previously heard of this kind of pump, yet almost all groups succeeded in making one in less than 4 hours after assembling the materials. Their successes prove that almost anyone, if given these detailed and thoroughly tested instructions, can build a serviceable, large-volume air pump of this simple type, using only materials and tools found in most American homes. If possible, build a cap large enough to pump through your shelter at least 40 cubic feet per minute, 40 cfm, of outdoor air for each shelter occupant. If 40 cfm of outdoor air is pumped through a shelter and distributed within it as specified below, even under heat wave conditions the effective temperature of the shelter air will not be more than 20 F higher than the effective temperature outdoors. The effective temperature is a measure of air's effects on people due to its heat, humidity, and velocity. The 36-inch high by 29-inch wide cap described in these instructions, if used as specified, will pump at least 1000 cfm of outside air through a shelter that has the airflow characteristics outlined in these instructions. If more than 25 persons might be expected to occupy a shelter during hot weather, then it is advisable to build a larger cap. The 72-inch high by 29-inch wide model described can pump between 4000 and 5000 cfm. To maintain tolerable temperature-humidity conditions for people in your shelter during hot weather, you must degree pump enough outdoor air all the way through the shelter, 40 cfm for each occupant in very hot, humid weather. Degree distribute the air evenly within the shelter. If the cap that pumps air through the shelter does not create air movement that can be felt in all parts of the shelter in hot weather, one or more additional caps will be needed to circulate the air and gently fan the occupants. Degree encourage the shelter occupants to wear as little clothing as practical when they are hot. Sweat evaporates and cools best on bare skin. Book page 194. Degree supply the occupants with adequate water and salt. For prolonged shelter occupancy under heatwave conditions in a hot part of the country, about 4 quarts of drinking water and 1/3 ounce, 1 tablespoon, of salt per person are required every 24 hours, including salt in food that is eaten. Normal American meals supply about 1/4 ounce of salt daily. Salt taken in addition to that in food should be dissolved in the drinking water. Degree pump outdoor air through your shelter day and night in warm weather, so that both the occupants and the shelter are cooled off at night. Almost all of the danger from fallout is caused by radiation from visible fallout particles of heavy, sand-like or flaky material. The air does not become radioactive due to the radiation continuously given off by fallout particles. The visible fallout particles rapidly fall out of slow-moving air. The air that a cap pumps through a shelter moves at a low speed and could carry into the shelter only a very small fraction of the fallout particles that cause the radiation hazard outside. This fraction, usually not dangerous, can be further reduced if occupants take the simple precautions described in these instructions. Caution. Before anyone starts to build this unusual type of air pump, all workers should read these instructions at least up to Section B, Installation. Otherwise mistakes may be made and work may be divided inefficiently. When getting ready to build this pump, all workers should spend the first half hour studying these instructions and getting organized. Then, after materials are assembled, two inexperienced persons working together should be able to complete the 3-foot model described in the following pages in less than 4 hours. To speed up completion, divide the work. For example, one person can start making the flaps while another begins work on the pump frame. 2. How a cap works. As can be seen in Figs 1 and 2, a cap operates by being swung like a pendulum. It is hinged at the top of its swinging frame. When this air pump is pulled by a cord as illustrated, its flaps are closed by air pressure and it pushes air in front of it and sucks air in back of it. Thus a cap pumps air through the opening in which it swings. This is the power stroke. During its power stroke, the pump's flaps are closed against its flap stop wires or strings, which are fastened across the face of the frame. Figure 1. Section through the upper part of a doorway, showing operation of a cap. ORNLDWG66-123208, Figure 2. Cap in doorway, with flaps open during its return stroke. ORNLDWG66-12319A. Book page 195. When a cap swings freely back as a pendulum on its return stroke, all its flaps are opened by air pressure. The pumped air stream continues to flow in the direction in which it has been accelerated by the power stroke, while the pump itself swings in the opposite direction, see Figure 2. Thus the flaps are one-way valves that operate to force air to flow in one direction, where desired. The cap can be used 1. To supply outdoor air to a shelter, 2. To distribute air within a shelter, and/or to fan the occupants. 1. To force outdoor air through a shelter. An air supply cap usually is operated as an air intake pump by pulling it with a cord, see Figure 1. Only rarely is it necessary to operate a cap as an air exhaust pump by pushing it with a pole, as described in the last section of these instructions. 2. To distribute air within a shelter and/or to fan the occupants, air distribution caps may be hung overhead and operated as described later. 3. Instructions for building a cap. In this section, instructions are given for making a cap 36 inches high and 29 inches wide, to operate efficiently when swinging in a typical home basement doorway 30 inches wide. If your doorway or other ventilation opening is narrower or wider than 30 inches, you should make your cap 1 inch narrower than the narrowest opening in which you plan to install it. Regardless of the size of the cap you plan to build, first study the instructions for making the 36x 29 inch model. In Section 7 you will find brief instructions for making a narrower and even simpler cap, one more suitable for the narrow openings of small trench shelters and other small expedient shelters. Section 8 covers large caps, for large shelters. Materials needed for a cap 36 inches high by 29 inches wide. The preferred material is listed as first choice, and the less preferred materials are listed as second, third, and fourth choices. It is best to assemble, spread out, and check all your materials before beginning to build. 1. The pump frame and its fixed support. Degree boards for the frame. First 22 feet of 1x2 in. Boards. A nominal 1x2 in. Board actually measures about 3/4 XL minus 3/4 in. But the usual, nominal dimensions will be given throughout these instructions. Also, 6 feet of 1x1 in. Boards. Soft wood is better. Second, boards of the same length that have approximately the same dimensions as 1 by 2 inches. And 1x1 in. Lumber. Third, straight sticks or metal strips that can be cut and fitted to make a flat-faced cap frame. Degree hinges. First, door or cabinet butt hinges. Second, metal strap hinges. Third, improvised hinges made of leather, woven straps, cords, or 4 eye screws which can be joined to make 2 hinges. Screws are best for attaching hinges. If nails are used, they should go through the board and their ends should be bent over and clinched flattened against the surface of the board. Degree of board for the fixed horizontal support. First, A1x4 in. Board that is at least 1 foot longer than the width of the opening in which you plan to swing your pump. Second, a wider board. Degree small nails, at least 24. First, number 6 box nails, about 1/2 in. Longer than the thickness of the two boards, so their pointed ends can be bent over and clinched. Second, other small nails. 2. The flaps, see figs. 1, 2, 6, 7, and 8. Degree plastic film or other very light, flexible material 12 square feet in pieces that can be cut into 9 rectangular strips, each 30 x 5-1/2 in. First, polyethylene film 3 or 4 mils thick, 3 or 4/1000ths of an inch. Second, 2 mil polyethylene from large trash bags. Third, tough paper. Degree pressure sensitive waterproof tape, enough to make 30 feet of tape 3/4 in to 1 in wide, for securing the hem tunnels of the flaps. First, cloth duct tape, silver tape. Second, glass tape. Third, Scotch tape. Fourth, freezer or masking tape, or sew the hem tunnels. Do not use a tape that stretches. It may shrink afterward and cause the flaps to wrinkle. 3. The flap pivot wires. First, 30 feet of smooth wire at least as heavy and springy as coat hanger wire, that can be made into very straight pieces each 29 in. Long, 9 all-wire coat hangers will supply enough. Second, 35 feet of somewhat thinner wire, including light, flexible insulated wire. Third, 35 feet of smooth string, preferably nylon string about the diameter of coat hanger wire. Book page 196. 4. The pull cord. Degree: first, at least 10 feet of cord. Second, strong string. Third, flexible, light wire. 5. The flap stops. Degree: first, 150 feet of light string. Second, 150 feet of light, smooth wire. Third, 150 feet of very strong thread. Fourth, 600 feet of ordinary thread, to provide 4 threads for each stop flap. Degree: first, 90 tacks, not thumbtacks. Second, 90 small nails. Tacks or nails are desirable but not essential, since the flap stops can be tied to the frame. B. Tools. A hammer, saw, wire cutter pliers, screwdriver, scissors, knife, yardstick, and pencil are desirable. However, only a strong, sharp knife is essential for making some models. C. Building a cap 36 inches high by 29 inches wide. 836 x 29 in. Cap is most effective if operated in an air intake or exhaust opening about 40 in high and 30 in wide. If your shelter might have more than 25 occupants in hot weather, read all these instructions so you will understand how to build a larger pump, briefly described in Section 8. Note that the widths and thicknesses of all frame pieces are exaggerated in all illustrations. 1. The frame. A. Cut 2 pieces of 1x2 in boards, each 36 in long, and 2 pieces of 1x2 in boards, each 29 in long. Then nail them together, see Figure 3. Use nails that do not split the wood, preferably long enough to go through the boards and stick out about 1/2 in. On the other side. To nail in this manner, first put blocks under the frame so that the nail points will not strike the floor. Bend over nail points which go through. Next, cut and nail to the frame a piece of 1x1 in lumber 36 in long, for a center vertical brace. If you lack time to make or to find a 1x1 in board, use a 1x2 in board. Figure 3 shows the back side of the frame. The flap valves will be attached on the front, the opposite side. Figure 3. Cap frame, looking at the back side of the frame. ORNL 71 7003. To make the front side smooth and flat so that the flaps will close tightly, fill in the spaces as follows. Cut 2 pieces of 1x2 in boards long enough to fill in the spaces on top of the 36 in sides of the frame between the top and bottom horizontal boards, and nail these filler boards in place. Do the same thing with a 1x1 in board, or a board the size of that used for the center brace, as a filler board for the center brace, see Figure 4. If the frame is made of only one thickness of board 3/4 in to 1 in thick, it will not be sufficiently heavy to swing back far enough on its free swinging return stroke. Book page 197. 2. The hinges. Ordinary door butt hinges are best. So that the pump can swing past the horizontal position, the hinges should be screwed onto the front of the frame, at its top, in the positions shown in Figure 4. Pick one of the 29-in boards and call it the top. If you do not have a drill for drilling a screw hole, you can make a hole by driving a nail and then pulling it out. Screw the screw into the nail hole. Figure 4. Completing the frame. ORNLDWG66-12322A. 3. The pivot wires and flaps. A. Make 9 flap pivot wires. If you have smooth, straight wire as springy and thick as coat hanger wire, use it to make 9 29-in long straight lengths of wire. If not, use wire from all wire coat hangers or use strings. First cut off all of the hook portion of each coat hanger, including the twisted part. If you have only ordinary pliers, use the cutter to bite the wire all around. It will break at this point if bent there. Next, straighten each wire carefully. Straighten all the bends so that each wire is straight within 1/4 in, as compared to a straight line. Proper straightening takes 1 to 5 minutes per wire. To straighten, repeatedly grasp the bent part of the wire with pliers in slightly different spots, each time bending the wire a little with your other hand. Then cut each wire to a 29-in length. Finally, bend no more than 1/2 in of each end at a right angle and in the same plane that is, in directions so that all parts of the bent wire will lie flat against a smooth surface. The bent ends are for secure attachment later, see Figure 8. B. Make 9 polyethylene flaps that will be the hinged valves of the cap. First cut 9 strips, making each strip 30-in long by 5-1/2 in wide, see Figure 5. To cut plastic flaps quickly and accurately, cut a long strip of plastic 30-in wide. Then cut off a flap in this way. 1. Draw a cutting guideline on a wide board 5-1/2 in from an edge. 2. Place the 30-in wide plastic strip so that it lies on this board, with one of the strip's side edges just reaching the edge of the board. 3. Place a second board over the plastic on the first board, with a straight edge of this second upper board over the guideline on the lower board. And finally, 4. Cut off a flap by running a sharp knife along the straight edge of the upper board. Figure 5. ORNLDWG717004A. Book page 198. Top previous next. To form a hem along one of the 30-in sides of a 5-1/2 x 30-in rectangular strip, fold in a 1-in hem. This makes the finished flap 4-1/2 in wide. To hold the folded hem while taping it, paper clips or another pair of hands are helpful. For each hem, use 2 pieces of pressure-sensitive tape, each about 1-in wide and 16-in long. Or make the hem by sewing it very close to the cut edge to form a hem tunnel, see Figure 5. After the hem has been made, cut a notch with scissors in each hemmed corner of the flap pegs. 6 and 8. Avoid cutting the tape holding the hem. Each notch should extend downward about 1/2 in, and should extend horizontally from the outer edge of the flap to 1/4 in. Inside the inner side of the frame, when the flap is positioned on the frames as shown in Figure 6. Figure 6. Sizes of notches in flaps. ORNLDWG66-12324. Also cut a notch in the center of the flap, along the hem line, extending 1/2 in downward and extending horizontally 1/4 in beyond each of the 2 sides of the vertical brace, see Figure 6. The notch must be wider than the brace. However, if you are building a pump using wire netting for flap stops, see Figure 13, then do not cut a notch in the center of each flap. P greater than C. Take the 9 pieces of straightened wire and insert one of them into and through the hem tunnel of each flap, like a curtain rod running through the hem of a curtain. Check to see that each flap swings freely on its pivot wire, as illustrated by Figure 7. Also see Figure 8. Figure 7. End view. ORNLDWG66-12325. Figure 8. Flap. ORNLDWG717005A. Book page 199. Ruler for marking positions of flap pivot wires and flap stops D. Put aside the flaps and their pivot wires for use after you have attached the flap stops and the hinges to the frame, as described below. Using the ruler printed on the edge of this page, mark the positions of each pivot wire, the arrowheads numbered 0, 3-5/8, 7-1/4 in, and the position of each flap stop, the 4 marks between each pair of numbered arrowheads on this ruler. All of these positions should be marked both on the vertical sides of the 36-in longboards of the frame and on the vertical brace. Mark the position of the uppermost pivot wire, the 0 arrowhead on this ruler, 1/4 in, below the top board to which the hinges have been attached. See Figs 9 and 10. Figure 9. Frame 3/4 view, ORNLDWG 717006A. Figure 10. Top of frame straight on view, ORNLDWG 66123228A. 4. The flap stops. So that the flaps may swing open on only one side of the frame, on its front or face, you must attach horizontal flap stops made of strings or wires across the face of the frame. See Figs 10 and 11. Nail or tie 4 of these flap stops between the marked points where each pair of the horizontal pivot wires for the flaps will be placed. Be careful not to connect any flap stops in such a way that they cross the horizontal open spaces in which you later will attach the flap pivot wires. Fig. 11. Positions of pivot wires and flap stops. ORNLDWG 717007A. If you have tacks, not thumbtacks, or very small nails, drive 3 in a horizontal line to attach each flap stop, 1 in each of the 2 vertical 36-in sides of the frame and 1 in the vertical center brace. See Figure 11. First, drive all of these horizontal lines of tacks about 3/4 of the way into the boards. Then, to secure the flap stop string or thin wire quickly to attack, wind the string around the tack and immediately drive the tack tightly into the frame to grip the string. See Figure 11. If you have no tacks or nails, cut notches or slots where the flap stops are to be attached. Cut these notches in the edges of the vertical sides of the frame and in an edge of the center brace. Next, secure the flap stops, strings or wires, by tying each one in its notched position. This tying should include wrapping each horizontal flap stop once around the vertical center brace. The stops should be in line with, in the same plane as, the front of the frame. Do not stretch flap stops too tightly, or you may bend the frame. Book page 200. 5. Final assembly. A. Staple, nail, or tie the 9 flap pivot wires or pivot strings, each with its flap attached, in their positions at the marked 3-5/8 in spacings. Start with the lowest flap and work upward. See Figure 11. Connect each pivot wire at both ends to the 36-in vertical sides of the frame. Also connect it to the vertical brace. Be careful to nail the pivot wires only to the frame and the brace. Do not nail any plastic directly to the wood. All flaps must turn freely on their pivot wires. If any flap, when closed, overlaps the flap below it by more than 1 in, trim off the excess so that it overlaps by only 1 in. B. Screw, or nail. If screws are not available, the upper halves of the hinges onto the horizontal support board on which the cap will swing. AL in. Thick board is best, 3-1/2 in wide and at least 12 in longer than the width of the doorway or other opening in which this cap is to be installed. Be careful to attach the hinges in the unusual, out-of-line position shown in Figure 12. Cautions. Do not attach a cap's hinges directly to the door frame. If you do, the hinges will be torn loose on its return stroke or on its power stroke. If you are making a cap to fit into a rectangular opening, make its frame 4 in shorter than the height of its opening and 1 in narrower than the width of the opening. C. For this 3-featuring model, tie the pull cord to the center brace about 12-1/2 in below the hinge line, as shown in Figure 12. If you tie it lower, your arm movements will waste energy. Use small nails or wire to keep the tie end from slipping up or down on the center brace. For a more durable connection, see Figure 22. Cut a slot in the flap above the connection of the pull cord to the vertical brace, deep enough so that this flap will close completely when the cap is being pulled. Take the end and edges of the slot. Figure 12. Hinge is attached so pump can swing 180 degrees. ORNLDWG66-12330AR. IV. More rapid construction. Skip this section if you cannot easily get chicken wire and 1/4 in. Thick boards. If chicken wire and boards about 1/4 in thick are available, use the chicken wire for flap stops. By using these materials, the time required to build a given cap can be reduced by about 40%. 1-inch woven mesh is best. Hardware cloth has sharp points and is unsatisfactory. Figure 13 illustrates how the mesh wire should be stapled to the cap frame. Next, unless the cap is wider than 3 feet, the front of the whole frame, except for the center brace, should be covered with thin boards approximately 1/2 in thick, such as laths. Then the pivot wires, with their flaps on them, should be stapled onto the 1/4 in thick boards. This construction permits the flaps to turn freely in front of the chicken wire flap stops. With this design, the center of each pivot wire should not be connected to the center brace, nor should the center of the flap be notched. However, pivot wires that are attached this way must be made and held straighter than pivot wires used with flap stops made of straight strings or wires. Book page 201. Figure 13. Flaps attached 1/4 inch in front of chicken wire used for flap stops. ORNLDWG66-12333A. Note in Figure 13 that each pivot wire is held firm and straight by 2 staples securing each end. The wire used should be at least as springy as coat hanger wire. If string is used instead of wire, nylon cord about the diameter of coat hanger wire is best for the pivot strings. If the cap is wider than 3 feet, its center vertical brace should also be covered with a 1/4 in thick board, and each pivot wire should be attached to it. Furthermore, the center of each flap should be notched. V. Installation and accessories. A minimum open spaces around a cap. To pump its maximum volume, an air supply cap with good metal hinges should be installed in its opening so that it swings only about 1/2 in above the bottom of the opening and only 1/2 in to 1 in from the sides of the opening. B. Adequately large air passageways. When using a cap as an air supply pump to force air through a shelter, it is essential to provide a low-resistance air passageway all the way through the shelter structure from an outdoor air intake opening for outdoor air to a separate air exhaust opening to the outdoors. See Figure 14. Figure 14. ORNLDWG 66-12331AR2. Book page 202. A low-resistance air passageway is one that is no smaller in cross-sectional area than half the size of the cap pumping the air. For example, a 36x29 in cap should have a passageway no smaller than about 3-1/2 square. Fort. An air supply cap of this size will force at least 1,000 cubic feet per minute, 1,000 cfm, through a shelter having such openings, if it is installed as illustrated in Figure 14. If smaller air passageways or air exhaust openings are provided, the volume of air pumped will be greatly reduced. For example, if the air exhaust opening is only L-3/4 square, fort 1/4 the size of this cap, then this cap will pump only about 500 cfm. And if the air exhaust opening is only a 6x6 in exhaust duct 1/4 square, fort, then this same 36x29 in cap will pump only about 50 cubic feet per minute. This would not provide enough outdoor air for more than one shelter occupant in a well-insulated shelter under heat wave conditions in the hottest humid parts of the United States. In contrast, when the weather is freezing cold and the shelter itself is still cold enough to absorb the heat produced by the shelter occupants, this same 6x6 in exhaust duct and the air intake doorway will cause about 50 cfm of outdoor air to flow by itself through the shelter without using any pump. The reason: body heat warms the shelter air, and the warm air rises if cold air can flow in to replace it. Under these cold conditions, provided the air is distributed evenly throughout the shelter by cap or otherwise, 50 cfm is enough outdoor air for about 17 people. To provide adequately large air passageways for air supply caps used to ventilate shelters in buildings, in addition to opening and closing doors and windows, it may be necessary to build large ducts, as described below. Breaking holes in windows, ceilings, or walls is another way to make large, efficient air passageways. Figure 15 illustrates how a three-featuring cap can be used as a combined air supply and air distribution pump to adequately ventilate a small underground shelter that has an exhaust opening too small to provide enough ventilation in warm weather. A similar installation can be used to ventilate a basement room having only one opening, its doorway. Note how, by installing a divider in the doorway and entryway, the single entryway is converted into a large air intake duct and a separate, large air exhaust duct. To obtain the maximum increased volume of fresh outdoor air that can be pumped through the shelter, a total of about 1000 cfm for a 36x29 in cap, the divider should extend about 4 feet horizontally into the shelter room, as shown in Figure 15. The 6 feet at the end of the divider, the almost horizontal part under the cap, can be made of plywood, provided it is installed so that it can be taken out of the way in a few seconds. Figure 15. Ventilating a shelter when the air exhaust opening is too small. ORNLDWG 72-6630 book page 203. Note how the entry of fallout into a shelter can be minimized by covering the entryway with a roof, and by forcing the slow-moving entering air to rise over an obstruction, the wall, before it flows into the shelter. The sand-like fallout particles fall to the ground outside the wall. See adequate distribution of air within the shelter. To make sure that each shelter occupant gets a fair share of the outdoor air pumped through the shelter, air distribution caps should be used inside most large shelters. These caps are used within the shelter, separate from and in addition to air supply caps, see Figure 16. Air distribution caps can serve in place of both air distribution ducts and cooling fans. For these purposes, one or more 3 ft high caps hung overhead from the shelter ceiling are usually most practical. If caps cannot readily be hung from the ceiling, they can be supported on light frames made of boards or metal, somewhat like those used for a small child's swing. Figure 16. The use of air distribution caps. ORNLDWG 72-7547. You should make and use enough caps to cause air movement that can be felt in all parts of your shelter. Remember that if caps are installed near the floor and the shelter is fully occupied, the occupants' bodies will partially block the pumped airflow more than if the same caps were suspended overhead. As a general rule, for shelters having more than about 20 occupants, provide one 3-featuring air distribution cap for every 25 occupants. In relatively wide shelters, these interior caps should be positioned so that they produce an airflow that circulates around the shelter, preventing the air that is being pumped into the shelter from flowing directly to the exhaust opening. Figure 16 illustrates how 4 caps can be used in this way to distribute the air within a shelter and to fan the 100 occupants of a 1,000 square featuring shelter room. Avoid positioning an air distribution cap so that it pumps air in a direction greater than a right-angle turn from the direction of airflow to the location of the cap. D. Operation with a pulley. A small cap, especially one with improvised hinges or one installed at head height or higher, can be pulled most efficiently by running its pull cord over a pulley or over a greased homemade pulley, such as described in Figs 17 feet and 18. A pulley should be hung at approximately the same height as the hinges of the cap, as illustrated in Figure 15. To make Fig 17 improvised pulley from a wide-angled forked limb. ORNLDWG 71-7242 book page 204. Top previous next. Figure 18. Improvised pulley, ORNLDWG 71-7243. A comfortable handhold on which to pull downward. Tie 2 or 3 overhand knots in a strip of cloth on the end of the pull cord. Such a pulley can also be used to operate a bale bucket to remove water or wastes from some shelters, without anyone having to go outside. Quick removal brackets. The air supply cap that pumps air through your shelter is best held in its pumping position by mounting it in homemade quick removal brackets, see Figure 19, for the following reasons. A cap provided with quick removal brackets can be taken down easily and kept out of the way of persons passing through its doorway when it is not in use. It can be kept in a place where people are unlikely to damage it. By installing 2 sets of quick removal brackets in opposite shelter openings, you can quickly reverse the direction in which the cap pumps air, to take advantage of changes in the direction of natural airflow through the shelter. Figure 19. Quick removal bracket for cap. ORNLDWG7263665A. Degree: if the cap is installed on quick removal brackets, in an emergency a person standing beside the cap could grasp its frame with both hands, lift it upward a few inches to detach it, and carry it out of the way all in 3 to 5 seconds. Being able to move the cap quickly could prevent blast winds from wrecking the pump, which might also be blown into your shelter, possibly injuring occupants. In extensive areas where fallout shelters and their occupants would survive the blast effects of typical large warheads, more than 4 seconds would elapse between the time shelter occupants would see the extremely bright light from the explosion and the arrival of a blast wave strong enough to wreck a cap or other pumps left exposed in a ventilation opening. Note in Figure 19 that the KAP's fixed support board, a 3-1/2 in wide board to which its hinges are attached, is held in a bracket only 2 inches deep. To prevent too tight a fit in the bracket, be sure to place a 1/32 in shim or spacer, the cardboard back of a writing tablet will do, between 2 boards of the bracket, as illustrated. Also, make spaces about 1/16 of an inch wide between the lower inner corners of the stop blocks and the sides of the outer board. To prevent your hands from being cut, you should put tape over the exposed ends of wires near the frame's outer edges of a cap that you want to be able to remove rapidly. Book page 205. In a small expedient shelter, a small cap can be quickly jerked loose if its fixed support board is attached to the roof with only a few small nails. V. Operation and maintenance. A. Pumping. Operate your 3-foot cap by pulling it with an easy, swinging motion of your arm. To pump the maximum volume of air, you should pull the cap toward you until its frame swings out to an almost horizontal position. Then quickly move your hand so that the pull cord is kept slack during the entire free swinging return stroke. Figure 24 in Section 8, Large Caps, illustrates this necessary motion. Be sure to provide a comfortable hand hold on the pull cord, see Figure 14. Blisters can be serious under unsanitary conditions. To pull a cap via an overhead pulley with minimum effort, sit down and pull as if you were tolling a bell, except that you should raise your hand quickly with the return stroke and keep it raised long enough so that the pull cord remains slack during the entire return stroke. Or, if the pulley is not overhead, operate the cap by swinging your extended arm back and forth from the shoulder. B. Placement to take advantage of the natural direction of airflow. A cap can pump more air into a shelter if it is installed so that it pumps air through the shelter in the direction in which the air naturally flows. Since this direction can be reversed by a wind change outdoors, it is desirable to provide a way to quickly remove your pump and reposition it so that air can be pumped in the opposite direction. This can be done in several ways, including making one set of quick removal brackets for one air opening and a second set for the other. C. Maintenance. To operate your cap efficiently, keep the flaps in good repair and make sure that there is the minimum practical area of open spaces in and around the cap through which air can flow back around the pump frame, opposite to the pump direction. So keep at least some extra flap material in your shelter, along with some extra tape and the few tools you may need to make repairs. 7. Narrow caps and small caps. A. Narrow caps. To swing efficiently in an entrance or emergency exit of an expedient trench shelter that is 22 in wide, a cap is best made 20 in wide and 36 in high. One of less height is not as efficient as a 36 in high model and has to be pulled uncomfortably fast. So, when ventilation openings can be selected or made at least 38 in high, make your pump 36 in high. In a narrow trench shelter, it is best to have the pull cord run the full length of the trench, along the trench wall that occupants will face when sitting. Then each occupant can take a turn pulling the pump without having to change seats. Good metal hinges on a narrow cap allow it to swing properly if pulled with the pull cord attached to one side of the frame. Pumps with improvised hinges and large pumps must be pulled from a connection point on their center vertical brace to make them swing properly. Therefore, if you have small metal hinges and need a cap no wider than 20 inches, build a rectangular frame without a vertical center brace. Make 2 pull cord attachment points, one on each side of the frame and each 9 inches below the top of the frame. For a small cap, a satisfactory attachment point can readily be made by driving 2 nails so that their heads cross, and wiring them together. Then if a change in wind direction outside causes the direction of natural air flow in the trench to become opposite to the direction in which air is being pumped, you can move your cap to the opening at the other end of the trench. The pull cord can easily be connected to the other side of the frame, and convenient pumping can be resumed quickly. Book page 206. So that the horizontal support board can be nailed easily to the roofing poles or boards of an entry trench, it is best to use cabinet hinges. Screw them onto an edge of the support board, in the unusual, out-of-line position shown in Figure 20. This hinge connection allows the pump to swing a full 180 degrees. To facilitate moving the horizontal support board, connect it to the roof with a few small nails, so that it can be pulled loose easily and quickly. Figure 20. Roof poles. Horizontal support board. ORNLDWG78-10358B small caps. If the only available opening in which a cap can be installed is small, build a cap to fit it. Use narrower boards to make the frame and make the flaps of thinner material, such as the polyethylene of large plastic trash bags. For pumps 24 inches or less in height, make the finished flaps only 3-1/2 an inch wide and space their pivot wires 3 inches apart. The flaps should overlap no more than inch. A cap 24 inches high will pump enough outdoor air for only a few people, except in cold weather. Small, yet efficient caps can be made even if the only materials available are straight sticks about 1-1/4 of an inch in diameter, strips of cloth to tie the frame together and to make the hinges and the pull cord, polyethylene film from large trash bags for the flaps, freezer or duct tape, or needle and thread, to make the flap hems, coat hanger wire or string for the pivot wire, and string or ordinary thread for the flap stops. A sharp knife is the only essential tool. Figure 21 shows a way to easily tie sticks securely together and to attach strings or threads for stop flaps, when small nails and tacks are not available. The flap stop strings or threads should be secured by wrapping them several times around each stick to which they are attached, so they will be gripped by the out-of-line knife cuts. Figure 21. Sticks ready to be tied together to make a cap frame. ORNLDWG78-21897 book page 207. 8. Large caps. A construction. A 6ft high by 29 in. Wide model can be constructed in the same way as a 3-featuring model except that it should have both horizontal and vertical center braces, 1x2 in. Boards are best. To increase the strength of a 6-featuring cap, all parts of its double-thickness frame and its vertical center brace should be made of 2 thicknesses of 1x2 in. Softwood boards, securely held together with clinched nails. Also, to increase the distance that the pump will swing back by itself during its return stroke, it is worthwhile to attach a 6-featuring piece of 1x2 in. Board, not illustrated, to the back of each side of the frame. Do not attach weights to the bottom of the frame, this would slow down the pumping rate. This 6ft high pump requires 18 flaps, each the same size as those of the 36 in high cap. The flaps on the lower part of a large cap must withstand hard use. If 1/2 in wide strips of tape are attached along the bottom and side edges of these lower flaps, then even flaps made of ordinary 4mm polyethylene will remain serviceable for over 1,000 hours of pumping. However, the lower flaps of large caps can advantageously be made of 6mm polyethylene. The width and spacing of all flaps should be the same as those of the 36 in high model. The pull cord should be attached to the vertical center brace of a 6-featuring cap about 16-1/2 in. Below the hinge line. A 3/16 in nylon cord is ideal. To adequately ventilate and cool very large and crowded shelters in buildings, mines, or caves, caps larger than 72x29 in should be used. You can take better advantage of large doorways, elevator shaft openings, etc. by tailor-making each large air supply cap to the size of its opening, that is, by making it as large as is practical. The frame and brace members should be appropriately strengthened, and one or more bridles should be provided, as described in the section below. A 7ft high x 5-1/2 ft wide cap, with a 1/4 in diameter pull cord attached 18 in below its hinge line, and with 2 bridles for its 2 operators, pumped air at the rate of over 11,000 cubic foot per minute through a large basement shelter during tests. To make a durable connection of the pull cord to the center vertical brace, 1. Attach a wire loop, figure 22, about L6-1/2 in below the hinge line. This loop can be made of coat hanger wire and should go around the center vertical brace. This fixed loop should be kept from slipping on the center brace by bending 4 6-penny nails over it in front as illustrated, and 2 smaller nails in back. 2. Make a free turning, triple wire loop connected to the fixed loop. 3. Cover part of the free turning loop with tape and tie the pull cord to this loop. Tie the pull cord tightly over the taped part. Figure 22. Pull cord to center vertical brace, ORNLDWG 72 8204. Book page 208. B. Operation of larger caps. A larger cap can be pulled most easily by providing it with a bridle, see figure 23, attached to the end of its pull cord. Figure 23. Y bridle for pull cord on cap. ORNLDWG 71 8069. A man of average size and strength can operate a 6 feet by 29 in cap by himself, pumping over 4,000 cubic feet per minute through a typical large shelter without working hard. Tests have shown that he must deliver only about 1/20th of a horsepower. However, most people prefer to work in pairs when pulling a 6-featuring cap equipped with a bridle, when pumping over 3,000 cfm. To pump the maximum volume of air with minimum effort, study figure 24 and follow the instructions given below for operating a large cap. Figure 24. At end of its forward swing, pump should just touch tighten pull cord. ORNLDWG 72 6526. 1. Gradually start the pump swinging back and forth, moving your arms and body as illustrated and pulling mostly with your legs and body. 2. Stand at such a distance from the pump that you can pull the pump toward you until the forward swinging pump just touches the tightly stretched pull cord and at such a distance that you can keep the pull cord slack during the whole of the pump's free backswing. 3. To be sure you do not reduce the amount of air pumped, rapidly move your arms forward as soon as the forward swinging pump touches the tightened pull cord. Hold your arms forward until the pump again starts to swing toward you. Top previous next. Ix. Solutions to special problems. A. Increasing the usefulness of shelters by supplying 40 cfm per planned occupant. If a shelter is fully occupied for days during hot weather and is cooled both day and night by pumping through it and distributing at least 40 cubic feet per minute of outdoor air for each occupant more than is required to maintain tolerable temperatures at night, these advantages result. Degree the shelter occupants will be exposed to effective temperatures less than 2 degrees Fahrenheit higher than the current effective temperatures outdoors, and at night will get relief from extreme heat. Degree the floors, walls, etc. of a shelter so ventilated will be cooled at night to temperatures well below daytime temperatures. Therefore, during the day a considerable fraction of the occupant's body heat will flow into the floors, walls, and other parts of the shelter and less body heat will have to be carried out by the exhaust air during the hottest hours of the day. Thus daytime temperatures will be reduced. Degree since the shelter occupants will be cooler and will sweat less, especially at night, they will need less water than they would require if the shelter were ventilated at a rate of less than 40 cfm per occupant. If the outdoor air is very hot and desert dry, it usually is better to supply less than 40 cfm per occupant during the hottest hours of the day. Degree if the shelter were to be endangered by the entry of outside smoke, carbon monoxide or other poisonous gases, or heavy descending fallout under windy conditions, ventilation of the shelter could be temporarily restricted or stopped for a longer period than would be practical if the shelter itself were warmer at the beginning of such a crisis period. Book page 209. Degree the shelter could be occupied beyond its rated capacity without problems caused by overcrowding becoming as serious as would be the case if smaller capacity air pumps were to be installed and used. B. Pre-cooling shelters. If the shelter itself is cooler than the occupants, more of the body heat of occupants can flow into its cool walls, ceiling, and floor. Therefore, It would be advantageous to pre-cool a shelter that may soon be occupied, especially during hot weather. Caps, or other air pumps or fans, can be used to pre-cool a shelter by forcing the maximum volume of cooling outdoor air through the shelter and by distributing it within the shelter. A shelter should be pre-cooled at all times when the air temperature outdoors is lower than the air temperature inside the shelter. Then, if the pre-cooled shelter is used, the occupants will be kept cooler at a given rate of ventilation than if the shelter had not been pre-cooled, because the air will not have to carry all of their body heat out of the shelter. See increasing the effectiveness of a cap. If you want to increase the volume of air that a cap with good metal hinges can force through a shelter, install side baffles, see Figure 25. Side baffles should be rigidly fixed to form two stationary walls, one on each side of the swinging pump frame. They can be made of plywood, boards, doors, tabletops, or even well-braced plastic. A space or clearance of 1/2 to 1 in. Should be maintained between the inner side of each baffle and the outer side of the swinging frame. By installing side baffles you may be able to increase the volume of air your cap will pump by as much as 20%, if it is in good repair and the openings around it are small. Figure 25. Side baffles. ORNLDWG66-12334R. D. Operating a cap as an exhaust pump. In some shelters, a cap can be operated most effectively by using it as an exhaust pump. This can be done by pushing it with a push-pole attached to its center vertical brace. Push-pole operation is sometimes the best way to suck outdoor air into a shelter by pumping air out of the shelter in the natural direction of airflow, for example, up an elevator shaft or up a stairwell. This method is especially useful in those basement shelters in which air intake openings are impractical for installing caps. This would be the case if the air intake openings are small, exposed windows or holes broken in the ceiling of a shelter in a building. To pump a large cap most effectively with a push-pole, stand with your back to the cap and grasp the push-pole with both hands. Using mostly your leg muscles, push the cap by pulling the free end of its push-pole toward you. Book page 210. Figure 26 shows an improvised, flexible connection of a push-pole attached to the center brace of a large cap 28 in. From the top of its frame. Figure 26. Push-pole flexible connection. ORNLDWG66-12332R. E. Ventilating a shelter with only one opening. Some basement rooms that may be used as shelters have only one opening, the doorway. A cap can be used to ventilate such a shelter room if enough well-mixed and distributed air is moving just outside the doorway, or if air from outdoors can be pumped in by another cap and made to flow in a hallway or room and pass just outside this doorway. Figure 27 indicates how to ventilate such a one-opening room by operating a three-featuring cap as an air intake pump in the upper part of the doorway. Below such a doorway cap, a divider, 6 feet to 8 feet long can be installed. The divider permits exhaust air to flow out of the room without much of it being sucked back into the room by the cap swinging above it. Plywood, reinforced heavy cardboard, or even well-braced plastic can be used to make a divider. It should be installed so that, in a possible emergency, it can be jerked out of the way in a few seconds. When used with a divider, a 36x29 in cap can pump almost 1,000 cubic feet of air per minute into and out of such a shelter room. Although 1,000 cubic feet of well-distributed air is sufficient for several times as many as 25 shelter occupants under most temperate climate conditions, it is enough for only about 25 people in a one-entry room under exceptionally severe heat wave conditions. Furthermore, to make it habitable for even 25 people under such conditions, the air in this room must be kept from rising more than 20 F above the temperature outdoors. This can be done using a second air supply cap to pump enough outdoor air through the building and in some cases also using air distribution caps in spaces outside the one-entry room. The cap in the doorway of a one-entry room should supply 40 CFM per occupant of this room. In order to prevent any of the used, warmed, exhaust air from the one-entry room from being sucked by the doorway cap back into the room, a stiffened rectangular duct can be built so as to extend the exhaust opening, in the lower part of the doorway, several feet outside the room. Such a duct can be built of plastic supported by a frame of small boards. It can be used to discharge the exhaust air far enough away from the cap and downstream in the airflow outside the one opening room so that no exhausted air can be sucked back into the room. Book page 211. Figure 27. Use of a divider to ventilate a shelter with only one opening. ORNLDWG 75-8203F. Installing a cap in a steel-framed doorway. If you need to install a cap in a steel-framed doorway and it is not feasible to screw or otherwise permanently connect it to the doorway, you can attach the cap by using a few boards and some cord, as illustrated by Figs 28 and 29. The two horizontal boards shown extending across the doorway are squeezed tightly against the two sides of the wall in which the doorway is located by tightening two loops of cord, one near each side of the doorway. One loop is illustrated. A cord is first tightened around the two horizontal boards. Then the looped cord is further tightened by binding it in the center with another cord, as illustrated. Two large C clamps serve even better than two looped cords. However, secure support for a swinging cap still requires the use of a vertical support board on each side of the doorway, as illustrated. Figure 28. Steel door frame. ORNLDWG 72-6564. Book page 212. Figure 29 shows a quick removal bracket supported by two horizontal boards tightened across the upper part of a doorway by looped cords, as described above. Also, study Figure 19 and its accompanying instructions. Figure 29. Quick removal bracket on doorway, ORNLDWG 72-6617. G. Building more durable caps. If you are building caps in normal times, you may want to use materials that will make your pumps last longer, even though these materials are more difficult to obtain and are more expensive. Durability tests have shown that the cap parts that wear out first are the flaps and the pulleys. In 6 featuring caps, the lower flaps are subject to hard use. Lower flaps made of 6 Aus per square. YD clear, nylon reinforced, plied vinyl have lasted undamaged for over 1,000 hours of full-stroke pumping, without having their edges reinforced. Lower flaps made of 6 mil nylon reinforced polyethylene, without edge reinforcements, have lasted for 1,000 hours with only minor damage. The best pulley tested was a marine pulley such as that used on small sailboats, with a Delrant DuPont 2 in diameter wheel and 3/16 in stainless steel shaft. This pulley was undamaged after operating a 6 featuring cap for 324 hours. The pulley appeared to be good for hundreds of hours of further operation. The best pulley cords tested were of braided Dacron or nylon. Using air filters. To supply shelter occupants with filtered air usually would be of much less importance to their survival and health than to provide them with adequate volumes of outdoor air to maintain tolerable temperatures. However, filtering the entering air could prove worthwhile, provided your shelter is not in an area likely to be subjected to blast, or it is a blast shelter with blast doors and blast valves protecting everything inside. Work on filters is started after you have completed more essential work, including the building of a high protection factor shelter, making, installing, and testing the necessary number of caps, storing adequate water, making a homemade fallout meter, etc. You have enough low-resistance filters, such as fiberglass dust filters used in furnaces and air conditioners, and other materials for building the necessary large, supported filter in front of your cap. Your cap can pump an adequate volume of air through the filter and shelter. The filter is installed so that it can be easily removed if shelter temperatures rise too high. To prevent a filter used with a cap from causing too great a reduction in the volume of air that the cap can pump through your shelter, you must use large areas of low-resistance filter material. An example. In one ventilation test, a large basement shelter was used which had 2 ordinary doorways at its opposite ends. These served as its air intake and its air exhaust openings. A 72x29 in cap operating in one doorway pumped almost 5,000 cubic feet per minute through the shelter. But when a filter frame holding 26 square feet of L-in thick fiberglass dust filters was placed across the air intake stairwell, the cap could pump only about 3,400 CFM through this filter and the shelter. Book page 213. Copyright 2000 Nuclear War Survival Skills. Also see the New Expedient Shelter book. Requires the DJVU plugin. NWSS Contents. Cover. Addition Notes. Table of Contents Book Order Form Forward. About the Author Acknowledgements Introduction. Ch. 1. The Dangers. Ch. 2. Warnings and Ch. 3. Psychologic. Ch. 4. Evacuation. Ch. 5. Shelter. Th. Ch. 6. Ventilation. Ch. 7. Protection. Ch. 8. Water. Ch. 9. Food. Ch. 10. Fallout raw. Ch. 11. Light. Ch. 12. Shelter saw. Ch. 13. Surviving. Ch. 14. Expedient. Ch. 15. Improvised. Ch. 16. Minimum PR. Ch. 17. Permanent. Ch. 18. Transpachi. App. Instructio. App. 8.1. Door COV. App. 8.2. Pole COV. App. 8.3. Small PO. App. 8.4. AboveGrow. App. 8.5. AboveGrow. App. 8.6. AboveGR. App. B. How to Mock. App. C. A Homemade Fallout Meter. The KFM app. D. Expedient. App. E. How to Mock. App. F. Providing. Selected references. Selected index. Graphics. Nuclear War Survival Skills. Mail Home. App. C. A Homemade Fallout Meter. The KFM. How to make and use it. Following these instructions may save your life. Fig. To get a clearer idea of the construction and use of a KFM. 4. 2 plastic bags. 1. 12. Cut an 8-1/2 inch. 13. 2 ways to charge. 4. Cut 2 small hole. To control radiation exposure in this way. Top previous. Next. How to make and use it. Following these instructions may save your life. Figure, nuclear ground burst explosion, drawing. The complete KFM instructions include patterns to be cut out and used to construct the fallout meter. At the end of the instructions are extra patterns on 4 unnumbered pages. The reader is urged to use these extra patterns to make KFMs in normal peacetime and to keep the complete instructions intact for use during a recognized crisis period. If Xerox copies of the patterns are used, they should be checked against the originals in order to make sure that they are the same size as the originals. Some older copiers make copies with slightly enlarged dimensions. Even slightly enlarged copies of all the KFM patterns can be made satisfactory provided 1. On the paper pattern to wrap around KFM can. The distances between the 4 marks for the holes for STOPTHREAD are corrected, and 2. The dimensions of the finished leaf pattern are corrected. These instructions, including the heading on this page and the illustrative photos, can be photographed without additional screening and rapidly reproduced by a newspaper or printer. If you keep the KFM instructions intact, during a worsening crisis you will be able to use them to help your friends and thousands of your fellow citizens by making them available for reproduction. PG 1.1 Logo. The reverse sides of these pages are numbered to allow for the creation of booklet format of this appendix. Book page 214. The need for accurate and dependable fallout meters. If a nuclear war ever strikes the United States, survivors of the blast and fire effects would need to have reliable means of knowing when the radiation in the environment around their shelters had dropped enough to let them venture safely outside. Civil defense teams could use broadcasts of surviving radio stations to give listeners a general idea of the fallout radiation in some broadcast areas. However, the fallout radiation can vary widely from point to point and the measurements are likely to be made too far from most shelters to make them accurate enough to use safely. Therefore, each shelter should have some dependable method of measuring the changing radiation dangers in its own area. During a possible rapidly worsening nuclear crisis, or after a nuclear attack, most unprepared Americans could not buy or otherwise obtain a fallout meter, an instrument that would greatly improve their chances of surviving a nuclear war. The fact that the dangers from fallout radiation, best expressed in terms of the radiation dose rate, Roentgens per hour, R per hour, quite rapidly decrease during the first few days, and then decrease more and more slowly, makes it very important to have a fallout meter capable of accurately measuring the unseen, unfelt and changing fallout dangers. Occupants of a fallout shelter should be able to minimize the radiation doses they receive. In order to effectively minimize the radiation doses, a dependable measuring instrument is needed to determine the doses they receive while they are in the shelter and while they are outside for emergency tasks, such as going out to get badly needed water. Also, such an instrument would permit them to determine when it is safe to leave the shelter for good. Untrained families, guided only by these written instructions and using only low-cost materials and tools found in most homes, have been able to make a KFM by working 3 or 4 hours. By studying the operating sections of these instructions for about 1–1/2 hours, average untrained families have been able to successfully use this fallout meter to measure dose rates and to calculate radiation doses received, permissible times of exposure, etc. The KFM Kearny fallout meter was developed at Oak Ridge National Laboratory. It is understandable, easily repairable, and as accurate as most civil defense fallout meters. In the United States in 1986, the least expensive commercially available dose rate meter that is accurate and dependable and that measures high enough dose rates for wartime use is a British instrument that retails for $375. Comparable American instruments retail for over $1,000. 2. Survival work priorities during a crisis. Before a nuclear attack occurs is the best time to build, test and learn how to use a KFM. However, this instrument is so simple that it could be made even after fallout arrives, provided that all the materials and tools needed, see lists given in sections B, B, and 7, and a copy of these instructions have been carried into the shelter. Before building a KFM, persons expecting a nuclear attack within a few hours or days and already in the place where they intend to await attack should work with the following priorities. 1. Build or improve a high protection factor shelter, if possible, a shelter covered with 2 or 3 feet of earth and separate from flammable buildings. At the same time, make and install a CAP, a homemade shelter ventilating pump, if instructions and materials are available. If not available, at least make a directional fan. Also store at least 15 gallons of water for each shelter occupant if containers are available. 2. Assemble all materials for 1 or 2 KFMs. 3. Make and store the drying agent by healing wallboard gypsum, as later described, for both the KFM and its dry bucket. 4. Complete at least 1 KFM. 3. How to use these instructions to best advantage. 1. Read aloud all of these instructions through section 7, tools needed, before doing anything else. 2. Next assemble all of the needed materials and tools. 3. Then read aloud all of each section following section 7 before beginning to make the part described in that section. A family that fails to read aloud all of each section describing how to make a part, before beginning to make that part, will make avoidable mistakes and will waste time. 4. Have different workers, or pairs of workers, make the parts they are best qualified to make. For example, a less skilled worker should start making the drying agent, as described in section 8, before other workers start making other parts. The most skilled worker should make and install the aluminum foil leaves, sections X and 11. 5. Give workers the sections of the instructions covering the parts they are to build, so they can follow the step-by-step instructions, checking off with a pencil each step as it is completed. 6. Discuss the problems that arise. The head of the family often can give better answers if he first discusses the different possible interpretations of some instructions with other family members, especially teenagers. 7. After completing 1 KFM and learning to use it, if time permits, make a second KFM that should be a better instrument. Book page 215. IV. What a KFM is and how it works. Figure 215A. Charged KFM. A KFM is a simple electroscope ionization chamber fallout meter with which fallout radiation can be measured accurately. To use a KFM, an electrostatic charge must first be placed on its two separate aluminum foil leaves. These leaves are insulated by being suspended separately on clean, dry insulating threads. To take accurate readings, the air inside a KFM must be kept very dry by means of drying agents such as dehydrated gypsum, easily made by heating gypsum wallboard, sheetrock, or silica gel. Do not use calcium chloride or other salt. Pieces of drying agent are placed on the bottom of the ionization chamber, the housing can, of a KFM. An electrostatic charge is transferred from a homemade electrostatic charging device to the two aluminum foil leaves of a KFM by means of its charging wire. The charging wire extends out through the transparent plastic cover of the KFM. When the two KFM leaves are charged electrostatically, their like charges, both positive or both negative, cause them to be forced apart. When fallout gamma radiation, that is similar to X-rays but more energetic, strikes the air inside the ionization chamber of a KFM, it produces charged ions in this enclosed air. These charged ions cause part or all of the electrostatic charge on the aluminum foil leaves to be discharged. As a result of losing charge, the two KFM leaves move closer together. A KFM maker who wants visual proof that his instrument can be partially or wholly discharged by ionizing radiation should persuade his dentist to place the charged KFM about 20 inches directly below a typical dental X-ray machine. For example, when a typical 90 kVp machine was set at 15 mA and for a 1/20th second pulse, its columnated X-ray beam partially discharged the KFM's separated aluminum foil leaves, promptly reducing the initial reading of 15 mm to 9 mm. Other types of machines will require different settings. Many dental X-ray machines are not accurately calibrated, nor do they produce gamma rays, so such tests should not be used in an attempt to check the accuracy of a KFM. Figure 215b. How to position yourself to take a reading. To read the separation of the lower edges of the two KFM leaves with one eye, look straight down on the leaves and the scale on the clear plastic cover. Keep the reading eye 12 inches above the seat. The KFM should be resting on a horizontal surface. To be sure the reading eye is always at this exact distance, place the lower end of a 12-inch ruler on the seat, while the upper end of the ruler touches the eyebrow above the reading eye. It is best to hold the KFM can with one hand and the ruler with the other. Using a flashlight makes the reading more accurate. If a KFM is made and maintained with the specified dimensions and of the specified materials, its accuracy is automatically and permanently established by unchanging laws of nature. Unlike factory-made radiation measuring instruments, a KFM never needs to be calibrated or tested with a radiation source. A KFM is used with a watch and the following table that is based on numerous calibrations made at Oak Ridge National Laboratory. The millimeter scale is cut out and attached, see photo illustrations on the following page, to the clear plastic cover of the KFM so that its zero mark is directly above the two leaves in their discharged position when the KFM is resting on a horizontal surface. A reading of the separation of the leaves is taken by noting the number of millimeters that the lower edge of one leaf appears to be on one side of the zero mark on the scale, and almost at the same time noting the number of millimeters the lower edge of the other leaf appears to be on the other side of the zero mark. The sum of these two apparent positions of the lower edges of the two leaves is called a KFM reading. The drawing appearing after the photo illustrations shows the lower edges of the leaves of a KFM appearing to be 9 mm on the right of 0 and 10 on the left, giving a KFM reading of 19 mm. Usually the lower edges of the leaves are not at the same distance from the zero mark. As will be fully explained later, the radiation dose rate is determined by 1. Charging and reading the KFM before exposure. 2. Exposing it to radiation for a specified time in the location where measurement of the dose rate is needed when outdoors, positioning the KFM about 3 feet above the ground. 3. Reading the KFM after its exposure. 4. Calculating, by subtraction, the difference between the reading taken before exposure and the reading taken after exposure. 5. Using this table to find what the dose rate was during the exposure as will be described later. Diff in readings time. Interval of an exposure. Difference between the reading before exposure and the Reading after exposure, 8-ply standard foil leaves, 15 SEC. R.H.R. 1 minute. R.H.R. 4 minute. R.H.R. 16 minute. R.H.R. 1 hour. R.H.R. 2 mm 6.21.60.40.10.034 mm 12. 3.10.80.20.066 mm 19. 4.61.20.30.088 mm 26. 6.21.60.40.10 mm 31. 7.72.00.60.13 mm 37. 9.22.30.60.15 14 mm 43. 11.02.70.70.18. Instructions on how to use a KFM are given after those detailing how to make and charge this fallout meter. Book page 216. Top previous next. To get a clearer idea of the construction and use of a KFM, look carefully at the following photos and read their captions. An uncharged KFM. The charging wire has been pulled to one side by its adjustment thread. This photo was taken looking straight down at the upper edges of the two flat, 8-ply aluminum leaves. At this angle the leaves are barely visible, hanging vertically side by side directly under the 0 mark, touching each other and with their ends even. Their suspension threads insulate the leaves. These threads are almost parallel and touch, but do not cross, each other where they extend over the top of the rim of the can. Figure 216a, top-down view of KFM. B. Charging a KFM by a spark gap discharge from a tape that has been electrostatically charged by being unwound quickly. Note that the charged tape is moved so that its surface is perpendicular to the charging wire. The high-voltage electrostatic charge on the unwound tape, that is an insulator, jumps the spark gap between the tape and the upper end of the charging wire, and then flows down the charging wire to charge the insulated aluminum foil leaves of the KFM. Since the upper edges of the two leaves are 3/8 inch below the scale and this is a photo taken at an angle, both leaves appear to be under the right side of the scale. Figure 216b. Unwound tape by KFM to produce static charge, see a charged KFM. Note the separation of the upper edges of its two leaves. The charging wire has been raised to an almost horizontal position so that its lower end is too far above the aluminum leaves to permit electrical leakage from the leaves back up the charging wire and into the outside air. Also note the seat, a piece of pencil taped to the right side of the can, opposite the charging wire. Figure 216c. A charged KFM. D. Reading a KFM. A 12-inch ruler rests on the seat and is held vertical, while the reader's eyebrow touches the upper end of the ruler. The lower edge of the right leaf is under 8 on the scale and the lower edge of the left leaf is under 6 on the scale, giving a KFM reading of 14. For accurate radiation measurements, a KFM should be placed on an approximately horizontal surface, but the charges on its two leaves and their displacements do not have to be equal. Figure 216d. Reading a KFM. Note: in these photos, the paper scale is taped to the top of the transparent plastic film cover. It is better to tape the scale to the underside of the cover, where it is less likely to be damaged. Book page 217. KFM diagrams, inside, top, and cutaway views, V. Materials needed. A. For the KFM. In the following list, when more than one alternative material is given, the best material is listed first. 1. Any type metal can. Approximately 2-9/16 of an inch in diameter inside and 2-7/8 of an inch high inside, washed clean with soap. This is the size of a standard 8-ounce can. Since most soup cans, pop cans, and beer cans also are about 2-9/16 of an inch in diameter inside, the required size of can also can be made by cutting down the height of more widely available cans as described in section X of these instructions. 2. Standard aluminum foil 2 square feet. In 1987, 2 square feet of widely sold U.S. brands of aluminum foil weighed between 8.0 and 8.5 grams. 1 gram equals 0.035 ounce. If only heavy-duty or extra heavy-duty aluminum foil is available, make 5-ply leaves rather than 8-ply leaves of standard foil. The resultant fallout meter will be almost as accurate. 3. Doorbell wire, or other light insulated wire preferably, but not necessarily, a single strand wire inside the insulation 6 inches. 4. Any type of clean, fine thread that has not been anti-static treated will serve to suspend a KFM's leaves. Almost all kinds of sewing thread and fly tying thread manufactured in 1987 are anti-static treated, are poor insulators, and are unsatisfactory. In 1987 the best widely available excellent insulating thread is unwaxed dental floss. Floss is not anti-static treated. Most unwaxed dental floss is too thick and stiff for properly suspending KFM leaves, but, since dental floss is not a twisted thread, you can make flexible strand threads from it. Make each no more than one/4 as thick as the floss, and about 12 inches long. First separate several strands at the end of the floss outside its dispenser. Then separate strands while pulling one way on the end of the strand thread that you want and the other way on the unwanted strands. Use only a clean needle to touch and separate the strands in the middle 6 inches of the 12-inch long piece of unwaxed dental floss. A widely sold dental floss. Johnson & Johnson's Extra Fine Unwaxed, drawn out of its dispenser without splitting it, makes quite satisfactory leaf-supporting threads. However, better leaf-supporting threads can be made by first separating any dental floss into thinner, more flexible threads. Very thin monofilament fishing line or leader is an excellent insulator. The 2-pound test strength, such as DuPont's Stren monofilament fishing line, is best. Trilene 2-pound nylon leader. A monofilament manufactured by Berkeley & Company, also is excellent. A 4-pound monofilament line will serve, but is disadvantageously stiff. Some modern monofilament lines or leaders such as Trilene contain an additive that makes them pliant, but also makes them poorer insulators for the first several hours after being taken out of their dispenser and used to suspend the leaves of a KFM. However, in about 6 hours the silica gel or anhydrous drying agent in a KFM removes this additive and the monofilament becomes as good an insulator as even strands of unwaxed dental floss. To minimize the chance of using a piece of monofilament or other thread that has been soiled and thus changed into a poor insulator, always first remove and discard the outermost layer of thread on any spool that has not been kept clean in a plastic bag or other packaging after being initially unwrapped. During a worsening crisis or after an attack, neither thread that has not been anti-static treated, nor unwaxed dental floss, nor clean 2-pound or 4-pound monofilament line may be available. However, most American homes have an excellent insulator, very thin polyethylene film, especially clean dry cleaners bags. A narrow insulating strip cut only 1/16 inch wide can be used to suspend each KFM leaf, instead of an insulating thread. Installed leaves suspended on strips of thin plastic film must be handled with care. To cut 1/16 inch wide strips from very thin polyethylene film, first cut a piece about 6 by 10 inches. Tape only the two 6-inch wide ends to a piece of paper, such as a brown grocery bag, so that the film is held flat and smooth on the paper. Make 10 marks, 1/16 inch apart, on each of the two tapes that are holding the film. Place a light so that its reflection on the film enables you to see the edge of the film that you are preparing to cut. Then use a very sharp, clean knife or clean razor blade, guided by the edge of a firmly held ruler, to cut 9 strips, of which you will select the best 2. When cutting, hold the knife almost horizontal, with the plane of its blade perpendicular to the taped down film. Throughout this procedure avoid touching the center parts of the strips. 5. A piece of clear plastic film, a 6x6 inch square. Clear vinyl, 4 mils thick, used for storm-proofing windows is best, but any reasonably stout and clear plastic will serve. The strong clear plastic used to wrap pieces of cheese, if washed with hot water and soap, is good. Do not use weak plastic or cellophane. Plastic film made from cellulose, such as Flex-O-Pane, and roasting bags are too permeable to water vapor. 6. Cloth duct tape, silver tape, or masking tape, or freezer tape, or Scotch-type tape about 10 square inches. A roll of Scotch Magic transparent tape, if available, should be saved for use in charging the KFM. 7. Band-aid tape, or masking tape, or freezer tape, or Scotch transparent tape, or other thin and very flexible tapes about 2 square inches. 8. Gypsum wallboard, sheetrock, about half a square foot. Best about 1/2 inch thick, for a good homemade drying agent. Silica gel with dark blue color indicator is an even better drying agent, but is not available in most communities. Available from chemical supply firms that supply high school chemistry classes. With dark blue silica gel in the bottom of a KFM, white typing correction fluid or white ink is needed to make the lower edges of a KFM's aluminum leaves easier to see. 9. Glue not essential, but useful to replace Band-Aid and other thin tapes. 1 hour. Epoxy is best. Model airplane cement is satisfactory. 10. An ordinary wooden pencil and a small toothpick, or split a small sliver of wood. 11. 2 strong rubber bands, or string. 12. Several small, transparent plastic bags, such as sandwich bags, to cover the KFM when it is exposed where fallout particles may get on it and contaminate it. Or pieces of thin, transparent plastic film, such as that from bread bags. Also small rubber bands or string. B for the charging devices. 1. Most hard plastic rubbed on dry paper. This is the best method. A. Plexiglass and most other hard plastics, such as are used in draftsman's triangles, common smooth plastic rulers, etc. At least 6 inches long. B. Dry paper tough paper, such as clean, strong grocery bag or typing paper. Tissue paper, newspaper, or facial tissue such as Kleenex, or toilet paper are satisfactory for charging, but not as durable. 2. Scotch Magic transparent tape, 3/4 inch width is best, or Scotch transparent tape, or PVC. Polyvinyl chloride, insulating electrical tapes, or a few of the other common brands of Scotch-type tapes. Some plastic tapes do not develop sufficiently high-voltage electrostatic charges when unrolled quickly. This method cannot be used for charging a KFM inside a dry bucket, needed for charging when the air is very humid. C for determining dose rates and recording doses received. 1. A watch with a second hand. 2. A flashlight or other light, for reading the KFM in a dark shelter or at night. 3. Pencil and paper, preferably a notebook. D for the dry bucket. A KFM must be charged inside a dry bucket if the air is very humid, as it often is inside a crowded, long-occupied shelter lacking adequate forced ventilation. 1. A large bucket, pot, or can, preferably with a top diameter of at least 11 inches. 2. Clear plastic, best is 4 mm thick clear plastic used for storm windows. A square piece 5 inches wider on a side than the diameter of the bucket to be used. 3. Cloth duct tape, 1 inch wide and 8 feet long, or 4 featuring, if 2 inches wide. Or 16 featuring, of freezer tape 1 inch wide. Book page 219. Top previous next. 4. 2 plastic bags 14 to 16 inches in circumference, such as ordinary plastic bread bags. The original length of these bags should be at least 5 inches greater than the height of the bucket. 5. About 1 square foot of wallboard, sheetrock, to make anhydrite drying agent. 6. 2 1-quart mason jars or other airtight containers, one in which to store anhydrite and another in which to keep dry the KFM charging devices. 7. Strong rubber bands enough to make a loop around the bucket. Or string. V. Useful but not essential materials, which could be obtained before a crisis. 1. An airtight container, such as a large peanut butter jar, with a mouth at least 4 inches wide, in which to keep a KFM, along with some drying agent, when it is not being used. Keeping a KFM very dry greatly extends the time during which the drying agent inside the KFM remains effective. 2. Commercial anhydrite with a color indicator, such as the drying agent Dryrite. This granular form of anhydrite remains light blue as long as it is effective as a drying agent. It turns pink when it becomes ineffective. Or use silica gel with color indicator, that is dark blue when effective and that turns light pink when it becomes ineffective. Heating in a hot oven or in a can over a fire reactivates them as drying agents and restores their blue color. Obtainable from laboratory supply sources. Use enough to cover the bottom of the KFMs, can no more than 1/2 inch deep. 3. 4 square feet of aluminum foil, to make a moisture-proof cover for the dry bucket. 7. Tools needed. Small nail sharpened. Stick, or a wooden tool handle, best 2 to 2½ inch diameter and at least 12 inches long. Hammer. Pliers. Scissors. Needle, quite a large sewing needle, but less than 2½ inches long. Knife with a small blade, sharp ruler, 12 inches. Desirable but not essential tools. A file and a fine-toothed hacksaw blade. 8. Make the drying agent. The easiest part to make, but time-consuming. 1. For a KFM to measure radiation accurately, the air inside its ionization chamber must be kept very dry. An excellent drying agent, anhydrite, can be made by heating the gypsum in ordinary gypsum wallboard, sheetrock. Do not use calcium chloride. 2. Take a piece of gypsum wallboard approximately 12 inches by 6 inches, and preferably with its gypsum about 3/8 of an inch thick. Cut off the paper and glue, easiest done by first wetting the paper. Since water vapor from normal air penetrates the plastic cover of a KFM and can dampen the anhydrite and make it ineffective in as short a time as 2 days, fresh batches of anhydrite must be made before the attack and kept ready inside the shelter for replacement. The useful life of the drying agent inside a KFM can be greatly lengthened by keeping the KFM inside an airtight container, such as a peanut butter jar with a 4-inch diameter mouth, with some drying agent, when the KFM is not being used. 3. Break the white gypsum filling into small pieces and make the largest no more than 1/2 in. Across. The tops of pieces larger than this may be too close to the aluminum foil leaves. If the gypsum is dry, using a pair of pliers makes breaking it easier. Make the largest side of the largest pieces no bigger than this. Illustration: simple 1/2 in cube of gypsum. 4. Dry gypsum is not a drying agent. To drive the water out of the gypsum molecules and produce the drying agent, anhydrite, heat the gypsum in an oven at its highest temperature, which should be above 400 degrees Fahrenheit, for 1 hour. Heat the gypsum after placing the small pieces no more than 2 pieces deep in a pan. Or heat the pieces over a fire for 20 minutes or more in a pan or can heated to a dull red. 5. If sufficient aluminum foil and time are available, it is best to heat the gypsum and store the anhydrite as follows. A. So that the right amount of anhydrite can be taken quickly out of its storage jar, put enough pieces of gypsum in a can with the same diameter as the KFM, measuring out a batch of gypsum that almost covers the bottom of the can with a single layer. B. Cut a piece of aluminum foil about 8 in x 8 in square, and fold up its edges to form a bowl-like container in which to heat one batch of gypsum pieces. C. Measure out 10 or 12 such batches, and put each batch in its aluminum foil bowl. D. Heat all of these filled bowls of gypsum in hottest oven for 1 hour. E. As soon as the aluminum foil is cool enough to touch, fold and crumple the edges of each aluminum foil bowl together, to make a rough aluminum-covered ball of each batch of anhydrite. F. Promptly seal the batches in airtight jars or other airtight containers, and keep containers closed except when taking out an aluminum-covered ball. 6. Since anhydrite absorbs water from the air very rapidly, quickly put it in a dry airtight container while it is still quite hot. A mason jar is excellent. 7. To place anhydrite in a KFM, drop in the pieces one by one, being careful not to hit the leaves or the stop threads. The pieces should almost cover the bottom of the can, with no piece on top of other pieces. 8. To remove anhydrite from a KFM, use a pair of scissors or tweezers as forceps, holding them in a vertical position and not touching the leaves. X. Make the ionization chamber of the KFM. To avoid mistakes and save time, read all of this section aloud before beginning work. 1. Remove the paper label, if any, from an ordinary 8-ounce can from which the top has been smoothly cut. Wash the can with soap and water and dry it. An 8-ounce can has an inside diameter of about 2-9/16 of an inch and an inside height of about 2-7/8 of an inch. 2. Skip to step 3 if an 8-ounce can is available. If an 8-ounce can is not available, Reduce the height of any other can having an inside diameter of about 2-9/16 of an inch, such as most soup cans, most pop cans, or most beer cans. To cut off the top part of a can, first measure and mark the line on which to cut. Then, to keep from bending the can while cutting, wrap newspaper tightly around a stick or a round wooden tool handle, so that the wood is covered with 20 to 30 thicknesses of paper and the diameter, ideally, is only slightly less than the diameter of the can. One person should hold the can over the paper-covered stick while a second person cuts the can little by little along the marked cutting line. If leather gloves are available, wear them. To cut the can off smoothly, use a file, or use a hacksaw drawn backwards along the cutting line. Or cut the can with a sharp, short blade of a pocketknife by 1. Repeatedly stabbing downward vertically through the can into the paper, and 2. Repeatedly making a cut about 1/4 inch long by moving the knife into a sloping position, while keeping its points still pressed into the paper covering the stick. Next, smooth the cut edge, and cover it with small pieces of freezer tape or other flexible tape. 3. Cut out the paper pattern to wrap around KFM can. Cut one pattern out of pattern page A. Glue, or tape, this pattern to the can, starting with one of the two short sides of the pattern. Secure this starting short side directly over the side seam of the can. Wrap the pattern snugly around the can, gluing or taping it securely as it is being wrapped. If the pattern is too wide to fit flat between the rims of the can, trim a little off its lower edge. 4. Sharpen a small nail, by filing or rubbing on concrete, for use as a punch to make the 4 holes needed to install the stop threads in the ionization chamber, the can. The stop threads are insulators that stop the charged aluminum leaves from touching the can and being discharged. 5. Have one person hold the can over a horizontal stick or a round wooden tool handle, that ideally has a diameter about as large as the diameter of the can. Then a second person can use the sharpened nail and a hammer to punch 4 very small holes through the sides of the can at the points shown by the 4 crosses on the pattern. Make these holes just large enough to run a needle through them, and then move the needle in the holes so as to bend back the obstructing points of metal. Illustration: single thread threaded through 4 holes to make 2 stop threads. 6. The stop threads can be installed by using a needle to thread a single thread through all 4 holes. Use a very clean thread, preferably nylon, and do not touch the parts of this thread that will be inside the can and will serve as the insulating stop threads. Soiled threads are poor insulators. See illustrations. Book page 221. Pattern to wrap around can. Table to find dose rates, hour. Before threading the thread through the 4 holes, tie a small toggle, see the preceding sketch, to the long end of the thread. This toggle can easily be made of a very small sliver of wood cut about 3/8 in long. After the thread has been pulled through the 4 holes, attach a second toggle to the thread, about 1/2 inch from the part of the thread that comes out of the 4th hole. Then the thread can be pulled tightly down the side of the can and the second small toggle can be taped securely in place to the side of the can. If the thread is taped down without a toggle, it is likely to move under the tape. The first toggle and all of the 4 holes also should be covered with tape, to prevent air from leaking into the can after it has been covered and is being used as an ionization chamber. Make 2 separate 8-ply leaves of standard, not heavy-duty, aluminum foil. Proceed as follows to make each leaf. Figure 222A, how to fold aluminum foil -1. A for the KFM. In the following list, when 1. Cut out a piece of standard aluminum foil approximately 4 inches by 8 inches. 2. Fold the aluminum foil to make a 2-ply, equals 2 thicknesses, sheet approximately 4 inches by 4 inches. 3. Fold this 2-ply sheet to make a 4-ply sheet approximately 2 inches by 4 inches. 4. Fold this 4-ply sheet to make an 8-ply sheet, 8 sheets thick, approximately 2 inches by 2 inches, being sure that the 2 halves of the second fold edge are exactly together. This third folding makes an 8-ply aluminum foil sheet with one corner exactly square. 5. Cut out the finished leaf pattern. Found on the following pattern page B. Note that this pattern is not a square and that it is smaller than the 8-ply sheet. Flatten the 8 thicknesses of aluminum foil with the fingers until they appear to be a single thin, flat sheet. 6. Hold the finished leaf pattern on top of the 8-ply aluminum foil sheet, with the pattern's third fold edge on top of the third fold edge of the 8-ply aluminum sheet. Be sure that one lower corner of the finished leaf pattern is on top of the exactly square corner of the 8-ply aluminum sheet. Figure 222b, How to fold aluminum foil -2. Figure 222c, How to fold aluminum foil -3. 7. While holding a straight edge along the thread line of the pattern, press with a sharp pencil so as to make a shallow groove for the thread line on the 8-ply aluminum sheet. Also using a sharp pencil, trace around the top and side of the pattern, so as to indent groove the 8-ply foil. 8. Remove the pattern and cut out the 8-ply aluminum foil leaf. Then, in order to prevent possible excessive electrical discharge from overly sharp points on the lower corners of the leaf, cut about 11/16 inch triangle off each of its two lower corners. 9. While holding a straight edge along the indented thread line, lift up the open edge of the 8-ply sheet, keeping all 8 plies together, until this edge is vertical, as illustrated. Remove the straight edge, and fold the 8-ply aluminum along the thread line so as to make a flat folded hem. 10. Open the flat folded hem of the finished leaf until the 8-ply leaf is almost flat again, as shown by the pattern, from which the finished leaf pattern has already been cut. 11. Prepare to attach the aluminum foil leaf to the thread that will suspend it inside the KFM. If only heavy-duty aluminum foil, sometimes called extra heavy-duty, is available, make 5-ply leaves of the same size, and use the table for the 8-ply KFM to determine radiation dose rates. To make a 5-ply leaf, start by cutting out a piece of foil approximately 4 inches by 4 inches. Fold it to make a 4-ply sheet approximately 2 inches by 2 inches, with one corner exactly square. Next, from a single thickness of foil, cut a square approximately 2 inches by 2 inches. Slip this square into a 4-ply sheet, thus making a 5-ply sheet. Then make the 5-ply leaf, using the finished leaf pattern, etc. as described for making an 8-ply leaf. If no epoxy glue is available to hold down the hem and prevent the thread from slipping in the hem, cut 2 pieces of tape. Band-aid tape is best. Next best is masking or freezer tape. Next best, Scotch tape. After first peeling off the paper backing of Band-aid tape, cut each piece of tape 1/8 inch by 1 inch long. Attach these 2 pieces of tape to the finished 8-ply aluminum leaf with the sticky sides up, except for their ends. As shown by the pattern on the following pattern page, secure 1/8 inch of one end of a tape strip near one corner of the 8-ply aluminum foil leaf by first turning under this 1/8 inch end, that is, with this end's sticky side down. Then turn under the other 1/8 inch long end, and attach this end below the thread line. Slant each tape strip as illustrated on pattern C. Be sure you have read through step 18 before you do anything else. Top previous next. 12. Cut an 8-1/2 inch piece of fine, unwaxed, very clean thread that has not been anti-static treated. See instructions, page 6 for excellent insulating threads and substitutes. In L986 most sewing threads are anti-static treated and are too poor insulators for use in a KFM. Cut out pattern C, the guide sheet used when attaching a leaf to its suspending thread. Then tape pattern C to the top of a work table. Cover the 2 tape here rectangles on pattern C with pieces of tape, each piece the size of the rectangle. Then cut 2 other pieces of tape each the same size and use them to onto the thread onto the guide sheet, on top of the tape here rectangles. Be very careful not to touch the 2 1-inch parts of the thread next to the outline of the finished leaf, since oil and dirt even on clean fingers will reduce the electrical insulating value of the thread between the leaf and the top rim of the can. 13. With the thread still taped to the paper pattern and while slightly lifting the thread with a knife tip held under the center of the thread, slip the finished leaf under the thread and into position exactly on the top of the leaf outlined on the pattern page. Hold the leaf in this position with 2 fingers. 14. While keeping the thread straight between its 2 taped down ends, lower the thread so that it sticks to the 2 plastic strips. Then press the thread against the plastic strips. 15. With the point of the knife, hold down the center of the thread against the center of the thread line of the leaf. Then, with 2 fingers, carefully fold over the hem and press it almost flat. Be sure that the thread comes out of the corners of the hem. Remove the knife, and press the hem down completely flat against the rest of the leaf. 16. Make small marks on the thread at the 2 points shown on the pattern page. Use a ballpoint pen if available. 17. Loosen the second 2 small pieces of tape from the pattern paper, but leave these tapes stuck to the thread. 18. Cut 5 pieces of band-aid tape, each approximately 1/8 inch by 1/4 inch, this small. Figure PG 224A shows size of band-aid tape. Use 2 of these pieces of tape to secure the centers of the side edges of the leaf. Place the 5 pieces as illustrated in the side view sketch below. Or use tiny droplets of epoxy, applied with a needle, to secure the side edges and to hold down the hem. Figure PG 224 BVIEW8 Oz. Can showing the 2 leaves charged, when not charged. The leaves hang perpendicular and touching. ORNLDWG 76 6542. 19. To prevent possible partial discharge from overly sharp lower corners of the leaves, use scissors to cut about 1/16 inch L off each lower corner of the 2 leaves. Partial discharge from an overly sharp corner may prevent a KFM's leaves from being adequately charged and adequately separated. 20. To make it easier to take accurate readings. A. Make a black stripe 1/8 inch wide on the hem side of the lower edge of each leaf, if the drying agent to be used is white anhydrite made from gypsum, or light blue dryrite. It is best to use a waterproof marker, such as black Marco by Flair. B. Make a white stripe, if the drying agent to be used is dark blue silica gel. Liquid paper correction fluid, or white ink, serves well. If using epoxy or other glue, use only a very little to hold down the hem, to attach the thread securely to the leaf and to glue together any open edges of the plied foil. Most convenient is 1 hour, epoxy, applied with a toothpick. Model airplane cement requires hours to harden when applied between sheets of aluminum foil. To make sure no glue stiffens the free thread beyond the upper corners of the finished leaf, put no glue within 1/4 inch of a point where thread will go out from the folded hem of the leaf. The instructions in step 11 are for persons lacking 1 hour, epoxy or the time required to dry other types of glue. Persons using glue instead of tape to attach the leaf to its thread should make appropriate use of the pattern on the following page and of some of the procedures detailed in steps 12 through 18. Book page 225. Cover the 2 tape here rectangles with same-sized pieces of tape, in order to keep from tearing this paper when removing 2 additional pieces of tape. Then, by putting 2 other pieces of tape this same size on top of the first 2 pieces, tape the thread onto this guide sheet, and later attach a leaf to the taped down thread. Figure 225 pattern C. How to tape aluminum leaves to thread line. Cut out this guide along its border lines and tape to the top of a work table. Warning. The parts of the thread that will be inside the can and on which the leaf will be suspended must serve to insulate the high-voltage electrical charges to be placed on the leaf. Therefore, the suspended parts of the thread must be kept very clean. 11. Install the aluminum foil leaves. 1. In preparation for suspending the leaves inside the can, make 2 shallow notches in the top of the rim of the can. Make 1 notch above each of the 2 lines. Fasten threads holding aluminum leaves here, on the paper pattern attached to the outside of the can. Make flat-bottomed notches by first filing a V-shaped notch, and then using a fine-toothed hacksaw blade to make the notch rectangular. If a file and/or a hacksaw blade are not available, the leaf suspending threads can be taped to the top of the rim of the can. 2. Use the 2 small pieces of ape stuck to the ends of a leaf suspending thread to attach the thread to the outside of the can. Attach the tapes on opposite sides of the can, so as to suspend the leaf inside the can. See end view sketch. Each of the 2 marks on the attached thread must rest exactly in a notch, or on the top of the rim of the can, if you are unable to make notches. Be sure that the hem side of each of the 2 leaves will face outward. See end view sketch. 3. Position and secure the second leaf, being sure that a. The smooth sides of the 2 leaves are not wrinkled or bent and face each other, and are flush right together, when not charged. See end view sketch and study the first photo illustration, an uncharged KFM. B. The upper edges of the two leaves are suspended side by side and at the same distance below the top of the can. C. The leaf suspending threads are in their notches in the top of the rim of the can, or are taped with band-aid to the top of the rim of the can, so that putting the cover on will not move the threads. D. No parts of the leaf suspending threads inside the can are taped down to the can or otherwise restricted. E. The leaf suspending parts of the threads inside the can do not cross over, entangle or restrict each other. F. The threads come together where they go over the rim of the can, and the leaves are flat and hang together as shown in the first photo illustration, an uncharged KFM. G. The leaves look like these photographed leaves. If not, make new, better leaves and install them. 4. Cover with tape the parts of the threads that extend down the outside of the can, and also cover with more tape the small pieces of tape near the ends of the threads on the outside of the can. Or use epoxy or other waterproof glue to attach the parts of the threads on the outside of the can securely to the can. 5. To make the seat, cut a piece of a wooden pencil, or a stick, about 1 inch long and tape it securely to the side of the can along the center line marked seat on the pattern. Be sure the upper end of this piece of pencil is at the same position as the top of the location for the seat outlined on the pattern. The top of the seat is 3/4 inch below the top of the can. Be sure not to cover or make illegible any part of the table printed on the paper pattern. 6. Cut out one of the reminders for operators, and glue and/or tape it to the unused side of the KFM. Then it is best to cover all the sides of the finished KFM with clear plastic tape or varnish. This will keep sticky tape on the end of an adjustment thread or moisture from damaging the reminders, or the table. 12. Make the plastic cover. 1. Cut out the paper pattern for the cover from the pattern page B. 2. From a piece of clear, strong plastic, cut a circle approximately the same size as the paper pattern. Storm window vinyl film, 4 mils thick, is best. 3. Stretch the center of this circular piece of clear plastic over the open end of the can, and pull it down close to the sides of the can, making small tucks in the skirt, so that there are no wrinkles in the top cover. Hold the lower part of the skirt in place with a strong rubber band or piece of string. If another can having the same diameter as the KFM can is available, use it to make the cover to avoid the possibility of disturbing the leaf suspending threads. Figure 226 shows positioning of tape and rubber band to secure plastic cover on KFM. 4. Make the cover so it fits snugly, but can be taken off and replaced readily. Just below the top of the rim of the can, bind the covering plastic in place with a 1/4 inch wide piece of strong tape. Cloth duct tape is best. Use 2 thicknesses. If only freezer or masking tape is available, use 3 or 4 thicknesses. Keep vertical the small part of the tape that presses against the rim of the can while pulling the length of the tape horizontally around the can so as to bind the top of the plastic cover snugly to the rim. If this small part of the tape is kept vertical, the lower edge of the tape will not squeeze the plastic below the rim of the can to such a small circumference as to prevent the cover from being removed quite easily. Reminders for operators. Reminders for operators. The drying agent inside a KFM is okay if, when the charged KFM is not exposed to radiation, its readings decrease by 1 mm or less in 3 hours. Reading. With the reading I 12 inches vertically above the seat. Note on the tom scale the separation of the lower edges of the leaves. If the right leaf is at 10 mm and the left leaf is at 3 mm. The KFM reads 10 mm. Never take a reading while a leaf is touching a stop thread. Never use a reading that is less than 5 mm. Finding a dose rate. If before exposure a KFM reads 17 mm and if after a minute exposure it reads 5 mm. The difference in readings is 12 mm. The attached table shows the dose rate was 9.6 R/hour during the exposure. Finding a dose. If a person works outside for 3 hours where the dose rate is 2 R/hour. What is his radiation dose? Answer. 3 hour x 2 R/hour equals 6 R. Finding how long it takes to get a certain R dose. If the dose rate is 1.6 R/hour outside and a person is willing to take a 6 R dose, how long can he remain outside? Answer. 6R, 1.6 R per hour, 3.75 hour equals 3 hours and 45 minutes. Fallout radiation guides for a healthy person not previously exposed to a total radiation dose of more than 100 R during a 2-week period. 6 R per day can be tolerated for up to 2 months without losing the ability to work. 100 R in a week or less is not likely to seriously sicken. 350 R in a few days results in a 50-50 chance of dying, under post-attack conditions. 600 R in a week or less is almost certain to cause death within a few weeks. The drying agent inside a KFM is okay if, when the charged KFM is not exposed to radiation, its readings decrease by 1 mm or less in 3 hours. Reading. With the reading eye 12 inches vertically above the seat. Note on the Tom scale the separation of the lower edges of the leaves. If the right leaf is at 10 mm and the left leaf is at 3 mm. The KFM reads 10 mm. Never take a reading while a leaf is touching a stop thread. Never use a reading that is less than 5 mm. Finding a dose rate. If before exposure a KFM reads 17 mm and if after a minute exposure it reads 5 mm. The difference in readings is 12 mm. The attached table shows the dose rate was 9.6 R/hour during the exposure. Finding a dose. If a person works outside for 3 hours where the dose rate is 2 R/hour. What is his radiation dose? Answer. 3 hour x 2 R/hour equals 6 R. Finding how long it takes to get a certain R dose. If the dose rate is 1.6 R/hour outside and a person is willing to take a 6 R dose, how long can he remain outside? Answer. 6 R, 1.6 R per hour, 3.75 hour equals 3 hours and 45 minutes. Fallout radiation guides for a healthy person not previously exposed to a total radiation dose of more than 100 R during a 2-week period. 6 R per day can be tolerated for up to 2 months without losing the ability to work. 100 R in a week or less is not likely to seriously sicken. 350 R in a few days results in a 50-50 chance of dying, under post-attack conditions. 600 R in a week or less is almost certain to cause death within a few weeks. 5. With scissors, cut off the skirt of the plastic cover until it extends only about 1 inch below the top of the rim of the can. 6. Make a notch in the skirt, about 1 inch wide, where it fits over the pencil seat attached to the can. The skirt, in this notched area should be only about 5/8 of an inch long, measured down from the top of the rim of the can. 7. Remove the plastic cover, and then tape the lower edges of the skirt, inside and out, using short lengths of 1/4 inch wide tape. Before securing each short piece of tape, slightly open the tucks that are being taped shut on their edges, so that the skirt flares slightly outward and the cover can be readily removed. 8. Make the charging wire by using the full-size, exact size pattern on the right. Doorbell wire with an outside diameter of about 11/16 inches best, but any lightweight insulated wire, such as part of a lightweight 2-wire extension cord split in half, will serve. The illustrated wire is much thicker than bell wire. To stop tape from possibly slipping up or down the wire, use a very little glue. If a very thin plastic has been used for the cover, a sticky piece of tape may need to be attached to the end of the bare-ended adjustment thread, so both threads can be used to hold the charging wire in a desired position. The best tape to attach to an end of one of the adjustment threads is cloth duct tape. A square piece 3/4 inch by 3/4 inch is the sticky base. To keep this tape sticky, free of paper fibers, the paper on the can should be covered with transparent tape or varnish. A piece about 1/8 inch by 314 inch serves to stick under one end of the sticky base, to hold the adjustment thread. A 3/4 inch by 11/4 inch rectangular piece of tape is used to make the finger hold important for making adjustments inside a dry bucket. With a needle or pin, make a hole in the plastic cover 1/2 inch from the rim of the can and directly above the upper end of the center line between the two leaves. The center line is marked on the pattern wrapped around the can. Carefully push the charging wire through this hole, thus stretching the hole, until all of the charging wire below its band-aid tape stop is inside the can. 9. From the pattern page B, cut out the scale. Then take the scale to the underside of the plastic cover, in the position shown on the pattern for the cover, and also by the drawings. Preferably use transparent tape. Be careful not to cover with tape any of the division lines on the scale between 20 on the right and 20 on the left of 0. 10. Put the plastic cover on the KFM can. Figure 228, charging wire. Sticky-ended adjustment thread. Book page 229. Top previous next. 13. 2 ways to charge a KFM. When preparing to charge a KFM, be sure its anhydride is fresh. Under humid conditions, sometimes in only 2 days enough water vapor will go through the plastic cover to make the drying agent ineffective. Be sure no piece of anhydride is on top of another piece. Re-read 8.7 and 8.8. 1. Charging a KFM with hard plastic rubbed on dry paper. A. Adjust the charging wire so that its lower end is about 1/16 inch above the upper edges of the aluminum foil leaves. Use the sticky tape at the end of one adjustment thread to hold the charging wire in this position. Stick this tape approximately in line with the threads suspending the leaves, either on the side of the can or on top of the plastic cover. If the charging wire is held loosely by the cover, it may be necessary to put a piece of sticky tape on the end of each adjustment thread in order to adjust the charging wire securely. If a charging wire is not secure, its lower end may be forced up by the like charge on the leaves before the leaves can be fully charged. Figure 229A, charging a KFM. B. Select a piece of plexiglass, a draftsman's plastic triangle, a smooth plastic ruler, or other piece of hard, smooth plastic. Unfortunately, not all types of hard plastic can be used to generate a sufficient electrostatic charge. Be sure the plastic is dry. For charging a KFM, especially inside a dry bucket, cut a rectangular piece of hard plastic such as plexiglass about 1-1/2 by 6 inches. Sharp corners and edges should be smoothed. To avoid contaminating the charging end with sweaty, oily fingers, it is best to mark the other end with a piece of tape, and to hold it only by its taped end. C. Fold dry paper, a piece of clean paper bag, or other smooth, clean paper, to make an approximate square about 5 inches on a side and 15 to 20 sheets thick. This many sheets of paper lessens leakage to the fingers of the electrostatic high-voltage charges to be generated on the hard plastic and on the rubbed paper. D. Fold the square of paper in the middle, and move the hard plastic rapidly back and forth so that it in the middle of this folded square is rubbed vigorously on the paper while the outside of this folded square of paper is squeezed firmly between thumb and little finger on one side, and the ends of 3 fingers on the other. To avoid discharging the charge on the plastic to the fingers, keep them away from the edges of the paper. See sketch. Figure 229B, using plastic and paper to generate a static charge E. Move the electrostatically charged part of the rubbed plastic rather slowly past the upper end of the charging wire, while looking straight down on the KFM. Keep the hard plastic approximately perpendicular to the charging wire and about 1/4 to 1/2 inch away from its upper end. The charge jumps the spark gaps and charges the leaves of the KFM. Charge the leaves sufficiently to give a reading of at least 15 mm. F. Pull down on an insulating adjustment thread to raise the lower end of the charging wire. If the charging wire has been held in its charging position by its sticky-ended adjustment thread being stuck to the top of the clear plastic cover, to avoid possibly damaging the threads, 1. Pull down a little on the bare-ended adjustment thread, and 2. Detach, pull down on, and secure the sticky-ended adjustment thread to the side of the can, so as to raise and keep the lower end of the charging wire close to the underside of the clear plastic cover. Do not touch the charging wire, because its insulation usually is not good enough to prevent the charge from bleeding off into the fingers. G. To get the most accurate readings possible, lightly bump or shake the charged KFM, to remove any unstable part of the charge before taking the initial reading. H. If the initial reading is more than 20 mm, to get the most accurate reading possible, carefully partially discharge the leaves, by touching them with the charging wire while guiding the wire with your fingers on its insulation, to reduce to 20 mm or slightly less the initial reading that you will use. Or completely discharge, and recharge to 20 mm or slightly less. I. To keep a KFM in excellent condition and to enable its drying agent to last much longer before becoming ineffective, put the whole KFM in an airtight container, such as a large peanut butter jar, with drying agent about an inch deep on its bottom. Or at least keep the charging paper and the hard plastic charging strip dry in a sealable container, such as a mason jar, with some drying agent. 2. Charging a KFM from a quickly unwound roll of tape. Quick unwinding produces a harmless charge of several thousand volts on the tape. A. Adjust the charging wire so that its lower end is about 1/16 inch above the upper edges of the aluminum foil leaves. Use the sticky tape at the end of one adjustment thread to hold the charging wire in this position. Stick this tape approximately in line with the leaves, either on the side of the can or on the plastic cover. If the plastic cover is weak, it may be necessary to put a piece of sticky tape on the end of each adjustment thread, in order to hold the charging wire securely. If a charging wire is not secure, its lower end may be forced up by the like charge on the leaves before the leaves can be fully charged. Book page 230. B. The sketch shows the get set position, preparatory to unrolling the Scotch Magic transparent tape, PVC, electrical tape, or other tape. Be sure to first remove the roll from its dispenser. Some of the other kinds of tape will not produce a high enough voltage. Illustration: get set position. C. Quickly unroll 10 to 12 inches of tape by pulling its end with the left hand, while the right hand allows the roll to unwind while remaining in about the same get set position, only an inch or two away from the KFM. D. While holding the unwound tape tight, about perpendicular to the charging wire, and about 114 inch away from the end of the charging wire, promptly move both hands and the tape to the right rather slowly, taking about 2 seconds to move about 8 inches. The electrostatic charge on the unwound tape jumps the spark gaps from the tape to the upper end of the charging wire and from the lower end of the charging wire to the aluminum leaves, and charges the aluminum leaves. Be sure neither leaf is touching a stop thread. Try to charge the leaves enough to spread them far enough apart to give a reading of at least 15 mm, but no more than 20 mm after the KFM has been gently bumped or shaken to remove any unstable part of the charge. E. Pull down on an insulating adjustment thread to raise the lower end of the charging wire. If the charging wire has been held in charging position by its sticky-ended adjustment thread being stuck to the top of the clear plastic cover, it is best first to pull down a little on the bare-ended adjustment thread, and then to move, pull down on, and secure the sticky-ended adjustment thread to the side of the can so that the lower part of the charging wire is close to the underside of the clear plastic cover. Do not touch the charging wire. Illustration: transferring charge. F. Rewind the tape tight on its roll, for future use when other tape may not be available. Testing your KFM to learn if it can accurately measure low dose rates. Put fresh drying agent in your KFM and then charge and test the KFM in a location where it is not exposed to abnormal radiation. Take an initial reading. If after 3 hours its reading has decreased by 1 mm or less, this means that its leaf suspending threads are good insulators and that your KFM can reliably measure dose rates as low as 0.03 roentgens per hour, 30 milliroentgens per hour. By post-attack standards, 30 Mr. per hour is a low dose rate. In a whole month of continuous exposure, an impossibility, because fallout decays. 30 Mr. per hour would result in a dose of 21.9 roentgens, not enough to incapacitate. Warning. In heavy fallout areas, for the first few days after fallout deposition, the dose rates inside even most good shelters will be higher than 0.03 R/hour. Troubleshooting. If charging does not separate the two leaves sufficiently, take these corrective actions. 1. Be sure the pieces of anhydride in the bottom of the ionization chamber, the can, are in a single layer, with no piece on top of another and the top of no piece more than 1/12 inch above the bottom of the can. 2. Check to be sure that the threads suspending the leaves are not crossed. Then try to charge the KFM again. 3. If the KFM still cannot be charged, replace the used anhydride with fresh anhydride. 4. If you cannot charge a KFM when the air is very humid, charge it inside its dry bucket. 5. If you cannot charge the KFM while in an area of heavy fallout, take it to the place affording the best protection against radiation, and try to charge it there. A dose rate of several hundred R/hour will neutralize the charges on both the charging device and the instrument so rapidly that a KFM cannot be charged. If a KFM or other radiation measuring instrument gives unexpectedly high readings inside a good shelter, wipe all dust off the outside of the instrument and repeat the radiation measurements. Especially when exposing a fallout meter outdoors where there is fresh fallout, keep the instrument in a lidded pot, plastic bag, or other covering to avoid the possibility of having it contaminated with fallout particles and afterwards getting erroneously high radiation measurements. Book page 231. 14. Make and use a dry bucket. By charging a KFM while it is inside a dry bucket with a transparent plastic cover, see illustration, this fallout meter can be charged and used even if the relative humidity is 100% outside the dry bucket. The air inside the dry bucket is kept very dry by a drying agent placed on its bottom. About a cupful of anhydrite serves very well. The pieces of this dehydrated gypsum need not be as uniform in size as is best for use inside a KFM, but do not use powdered anhydrite. Figure 231a, bucket with anhydrite. A dry bucket can be readily made in about an hour by proceeding as follows. 1. Remove the handle of a large bucket, pot, or can preferably with a top diameter of at least 11 inches. A 4-gallon bucket having a top diameter of about 14 inches and a depth of about 9 inches is ideal. A plastic tub approximately this size is satisfactory. If the handle supports interfere with stretching a piece of clear plastic film across the top of the bucket, remove them, being sure no sharp points remain. 2. Cut out a circular piece of clear plastic with a diameter about 5 inches larger than the diameter of the top of the bucket. Clear vinyl 4 mils thick, used for storm windows, etc., is best. Stretch the plastic smooth across the top of the bucket, and tie it in place, preferably with strong rubber bands looped together to form a circle. 3. Make a plastic top that fits snugly but is easily removable, by taping over and around the plastic just below the top of the bucket. 1-inch wide cloth duct tape, or 1-inch wide glass reinforced strapping tape, serves well. When taping, do not permit the lower edge of the tape to be pulled inward below the rim of the bucket. Figure 231a, bucket with anhydrite enlarged view. Illustration, cutting the clear plastic cover. Book page 232. Top previous next. 4. Cut 2 small holes, about 1 inch by 2 inches, in the plastic cover, as illustrated. Then make the radial cuts, shown by dotted lines, outward from the small holes, out to the solid line outlines of the 3-inch by 4-inch hand holes, so as to form small flaps. 5. Fold the small flaps upward, so they are vertical. Then tape them on their outer sides, so they form a vertical wall, about 3/4 inch high around each hand hole. 6. Reduce the length of 2 ordinary plastic bread bags, or similar plastic bags, to a length that is 5 inches greater than the height of the bucket. Do not use rubber gloves in place of bags. Gloves so used result in much more humid outside air being unintentionally pumped into a dry bucket when it is being used while charging a KFM inside it. 7. Insert a plastic bag into each hand hole, and fold the edge of the plastic bag about 1/2 inch over the taped vertical wall, around each hand hole. 8. Strengthen the upper parts of the plastic bags by folding 2-inch pieces of tape over the top of the wall, around each hand hole. 9. Make about a quart of anhydrite by heating small pieces of wallboard gypsum, and keep this anhydrite dry in a mason jar or other airtight container with a rubber or plastic sealer. 10. Make a circular aluminum foil cover to place over the plastic cover when the dry bucket is not being used for minutes to hours. Make this cover with a diameter about 4 inches greater than the diameter of the top of the bucket, and make it fit more snugly with an encircling loop of rubber bands, or with string. Though not essential, an aluminum foil cover reduces the amount of water vapor that can reach and pass through the plastic cover, thus extending the life of the drying agent. 11. Charge a KFM inside a dry bucket by a. Taking off wristwatch and sharp-pointed rings that might tear the plastic bags. b. Placing inside the dry bucket 1. About a cup of anhydrite or silica gel. 2. The KFM, with its charging wire adjusted in its charging position, and 3. Dry, folded paper and the electrostatic charging device, best a 5-inch long piece of plexiglass with smoothed edges, to be rubbed between dry paper folded about 4 inches square and about 20 sheets thick. Unrolling a roll of tape inside a dry bucket is an impractical charging method. C. Replacing the plastic cover, that is best held in place with a loop of rubber bands. D. Charging the KFM with your hands inside the plastic bags, operating the charging device. Have another person illuminate the KFM with a flashlight. When adjusting the charging wire, move your hands very slowly. See the dry bucket photos. 12. Expose the KFM to fallout radiation either by A. Leaving the KFM inside the dry bucket while exposing it to fallout radiation for one of the listed time intervals, and reading the KFM before and after the exposure while it remains inside the dry bucket. The reading eye should be a measured 12 inches above the seat of the KFM, and a flashlight or other light should be used. B. Taking the charged KFM out of the dry bucket to read it, expose it, and read it after the exposure. If this is done repeatedly, especially in a humid shelter, the drying agent will not be effective for many KFM chargings, and will have to be replaced. 15. How to use a KFM alter a nuclear attack. A background information. If during a rapidly worsening crisis threatening nuclear war you are in the place where you plan to take shelter, postpone studying the instructions following this sentence until after you have 1. Built or improved a high protection factor shelter, if possible, a shelter covered with 2 or 3 feet of earth and separate from flammable buildings, and 2. Made a CAP, homemade shelter ventilating pump, if you have the instructions and materials, and 3. Stored at least 15 gallons of water for each shelter occupant if you can obtain containers. Having a KFM or any other dependable fallout meter and knowing how to operate it will enable you to minimize radiation injuries and possible fatalities, especially by skillfully using a high protection factor fallout shelter to control and limit exposures to radiation. By studying this section you first will learn how to measure radiation dose rates, Rontgens per hour equals R per hour, how to calculate doses, it received in different time intervals, and how to determine time intervals, hours and/or minutes, in which specified doses would be received. Then this section lists the sizes of doses, number of R, that the average person can tolerate without being sickened, that he is likely to survive, and that he is likely to be killed by. Book page 233. Most fortunately for the future of all living things, the decay of radioactivity causes the sand-like fallout particles to become less and less dangerous with the passage of time. Each fallout particle acts much like a tiny X-ray machine would if it were made so that its rays, shooting out from it like invisible light, became weaker and weaker with time. Contrary to exaggerated accounts of fallout dangers, the radiation dose rate from fallout particles when they reach the ground in the areas of the heaviest fallout will decrease quite rapidly. For example, consider the decay of fallout from a relatively nearby, large surface burst, at a place where the fallout particles are deposited on the ground 1 hour after the explosion. At this time 1 hour after the explosion, assume that the radiation dose rate, the best measure of radiation danger at a particular time, measures 2000 Rontgens per hour, 2000 R per hour outdoors. 7 hours later the dose rate is reduced to 200 R per hour by normal radioactive decay. 2 days after the explosion, the dose rate outdoors is reduced by radioactive decay to 20 R/hour. After 2 weeks, the dose rate is less than 2 R/hour. When the dose rate is 2 R per hour, people can go out of a good shelter and work outdoors for 3 hours a day, receiving a daily dose of 6 Rontgens, without being sickened. In places where fallout arrives several hours after the explosion, the radioactivity of the fallout will have gone through its time period of most rapid decay while the fallout particles were still airborne. If you are in a location so distant from the explosion that fallout arrives 8 hours after the explosion, 2 days must pass before the initial dose rate measured at your location will decay to 1/10 its initial intensity. B. Finding the dose rate. 1. Reread section IV, what a KFM is and how it works. Also reread section 13, 2 ways to charge a KFM, and actually do each step immediately after reading it. 2. Charge the KFM so that it reads at least 15 mm. Next, raise the lower end of the charging wire. Then gently bump or shake the KFM to remove any unstable part of the charge. Read the apparent separation of the lower edges of the leaves while the KFM rests on an approximately horizontal surface. If the reading is larger than 20 mm, bleed off enough charge to reduce the initial reading to 20 mm or slightly less, for maximum accuracy. Never take a reading while a leaf is touching a stop thread. 3. To prevent possible contamination of a KFM, or of any other fallout meter, with fallout particles, keep it inside a plastic bag or other covering when there is risk of fallout particles being deposited or blown onto it. An instrument contaminated with fallout particles can give too high readings, especially of the low dose rate measurements made inside a good shelter. 4. Expose the KFM to fallout radiation for one of the time intervals shown in the vertical columns of the table attached to the KFM. Study the following table. If the dose rate is not known even approximately, first expose the fully charged KFM for 1 minute. For dependable measurements outdoors, expose the charged KFM about 3 feet above the ground. The longer outdoor exposures usually are best made by attaching the KFM with 2 strong rubber hands to a stick or pole, being careful never to tilt the KFM too much. 5. Read the KFM after the exposure, while the KFM rests on an approximately horizontal surface. 6. Find the time interval that gives a dependable reading by exposing the fully charged KFM for one or more of the listed time intervals until the reading after the exposure is a. Not less than 5 mm. b. At least 2 mm less than the reading before the exposure. 7. Calculate by simple subtraction the difference in the apparent separation of the lower edges of the leaves before the exposure and after the exposure. An example. If the reading before the exposure is 18 mm and the reading after the exposure is 6 mm, the difference in readings is 18 mm, 6 mm, 12 mm. 8. If an exposure results in a difference in readings of less than 2 mm, recharge the KFM and expose it again for one of the longer time intervals listed. If there appears to be no difference in the readings taken before and after an exposure for 1 minute, this does not prove there is absolutely no fallout danger. Take a longer reading. 9. If an exposure results in the reading after the exposure being less than 5 mm, recharge the KFM and expose it again for one of the shorter time intervals listed. 10. Use the table attached to the KFM to find the dose rate, R per hour, during the time of exposure. The dose rate, R per hour, is found at the intersection of the vertical column of numbers under the time interval used and of the horizontal line of numbers that lists the calculated difference in readings at its left end. An example. If the time interval of the exposure was 1 minute, and the difference in the readings was 12 mm, the table shows that the dose rate during the time interval of the exposure was 9.2 R HR, 9.2 roentgens per hour. Another example. If the time interval of the exposure was 15 SEC, and the difference in readings was 11 mm, the table shows that the dose rate during the exposure was halfway between 31 R per hour and 37 R per hour. That is, the dose rate was 34 R hour. Book page 234. 11. Note in the table that if an exposure for one of the listed time intervals causes the difference in readings to be 2 mm or 3 mm, then an exposure 4 times as long reveals the same dose rate. An example. If a 1 minimum exposure results in a difference in readings of 2 mm, the table shows the dose rate was 1.6 R per hour. Then if the KFM is exposed for 4 minutes at this same dose rate of 1.6 R per hour, the table shows that the resultant difference in readings is 8 mm. The longer exposure results in a more accurate determination of the dose rate. 12. If the dose rate is found to be greater than 0.2 R per hour and time is available, recharge the KFM and repeat the dose rate measurement to avoid possible mistakes. See calculating the dose received. The dose of fallout radiation, that is, the amount of fallout radiation received, determines the harmful effects on men and animals. Being exposed to a high dose rate is not always dangerous provided the exposure is short enough to result in only a small dose being received. For example, if the dose rate outside an excellent fallout shelter is 1200 R per hour and a shelter occupant goes outside for 30 seconds, he would be exposed for 1/2 of 1 minute, or 1/2 of 1/60th of an hour, which equals 1/120th hour. Therefore, since the dose he would receive if he stayed outside for 1 hour would be 1200 R, in 30 seconds he would receive 1/120th of 1200, which equals 10 R. 1200 R divided by 120 equals 10 R. A total daily dose of 10 R 10 Roentgens will not cause any symptoms if it is not repeated day after day for a week or more. In contrast, if the average dose rate of an area were found to be 12 R per hour and if a person remained exposed in that particular area for 24 hours, he would receive a dose of 288 R. 12 R per hour by 24 hour equals 288 R. Even assuming that this person had been exposed previously to very little radiation, there would still be a serious risk that this 288 R dose would be fatal under the difficult conditions that would follow a heavy nuclear attack. Another example. Assume that 3 days after an attack the occupants of a dry, hot cave giving almost complete protection against fallout are in desperate need of water. The dose rate outside is found to be 20 R/hour. To backpack water from a source 3 miles away is estimated to take 2-1/2 hour. The cave occupants estimate that the water backpackers will receive a dose in 2-1/2 hour of 50 R, 2.5 hour x 20 R per hour equals 50 R. A dose of 50 R will cause only mild symptoms, nausea in about 10% of persons receiving a 50 R dose, for persons who previously have received only very small doses. Therefore, one of the cave occupants makes a rapid radiation survey for about 1-1/2 mile along the proposed route, stopping to charge and read a KFM about every quarter of a mile. He finds no dose rates much higher than 20 R/hour. So, the cave occupants decide the risk is small enough to justify some of them leaving shelter for about 2-1/2 hour to get water. De-estimating the dangers from different radiation doses. Fortunately, the human body if given enough time can repair most of the damage caused by radiation. An historic example. A healthy man accidentally received a daily dose of 9.3 R, or somewhat more, of fallout-type radiation each day for a period of 106 days. His total accumulated dose was at least 1000 R. A dose of 1000 Roentgens, if received in a few days, is almost 3 times the dose likely to kill the average man if he receives the whole dose in a few days and after a nuclear attack cannot get medical treatment, adequate rest, etc. However, the only symptom this man noted was serious fatigue. The occupants of a high protection factor shelter, such as a trench shelter covered with 2 or 3 feet of earth and having crawlway entrances, would receive less than 1/200th of the radiation dose they would receive outside. Even in most areas of very heavy fallout, persons who remain continuously in such a shelter would receive a total accumulated dose of less than 25 R in the first day after the attack, and less than 100 R in the first 2 weeks. At the end of the first 2 weeks, such shelter occupants could start working outside for an increasing length of time each day, receiving a daily dose of no more than 6 R for up to 2 months without being sickened. Book page 235. Top previous next. To control radiation exposure in this way, each shelter must have a fallout meter, and a daily record must be kept to the approximate total dose received each day by every shelter occupant both while inside and outside the shelter. The long-term penalty which would result from a dose of 100 R received within a few weeks is much less than many Americans fear. If 100 average persons received an external dose of 100 R during and shortly after a nuclear attack, the studies of the Japanese bomb survivors indicate that no more than one of them is likely to die during the following 30 years as a result of this 100 R radiation dose. These delayed radiation deaths would be due to leukemia and other cancers. In the desperate crisis period following a major nuclear attack, such a relatively small shortening of life expectancy during the following 30 years should not keep people from starting recovery work to save themselves and their fellow citizens from death due to lack of food and other essentials. A healthy person who previously has received a total accumulated dose of no more than 100 R distributed over a 2-week period should realize that 100 R, even if all received in a day or less, is unlikely to require medical care provided during the next 2 weeks. A total additional dose of no more than a few R is received. 350 are received in a few days or less results in a 50-50 chance of being fatal after a large nuclear attack when few survivors could get medical care, sanitary surroundings, a well-balanced diet, or adequate rest. 600 are received in a few days or less is almost certain to cause death within a few days. Finding the protection factor of a shelter. To avoid the necessity of repeatedly going outside a shelter to determine the changing dose rates outside, find the shelter's protection factor (PF) by measuring the dose rate inside the shelter as soon as it becomes high enough to be reliably measured. Then promptly measure the dose rate outside. The uncontaminated shelter's PF equals dose rate inside, dose rate inside. An example. If the dose rate inside is found to be 0.2 R per hour and the dose rate outside is 31 R per hour, the shelter's PF equals 31 R per hour, 0.2 R per hour equals 155. Then at future times the approximate dose rate outside can be found by measuring the dose rate inside and multiplying it by 155. Approximate dose rate outside equals dose rate inside x PF. F using a KFM to reduce radiation doses received. If a charged KFM is discharged and reads 0 within a second or two after being taken outside a good shelter, this means that the dose rate outside is hundreds of roentgens per hour. Get back inside. Also remember that a 15-second reading is not as accurate as are readings made in longer specified exposure times. Inside most shelters, the dose received by an occupant varies considerably, depending on the occupant's location. For example, inside an expedient-covered trench shelter the dose rate is higher near the entrance than in the middle of the trench. In a typical basement shelter the best protection is found in one corner. Especially during the first several hours after the arrival of fallout, when the dose rates and doses received are highest, shelter occupants should use their fallout meters to determine where to place themselves to minimize the doses they receive. They should use available tools and materials to reduce the doses they receive, especially during the first day, by digging deeper, if practical, and reducing the size of openings by partially blocking them with earth, water containers, etc. While maintaining adequate ventilation. To greatly reduce the slight risk of fallout particles entering the body through nose or mouth, shelter occupants should cover nose and mouth with a towel or other cloth while the fallout is being deposited outside their shelter, if at the same time ventilating air is being blown or pumped through their shelter. The air inside an occupied shelter often becomes very humid. If a good flow of outdoor air is flowing into a shelter, especially if pumped by briefly operating a cap or other ventilating pump, a KFM usually can be charged at the air intake of the shelter room without putting it inside a dry bucket. However, if the air to which a KFM is exposed has a relative humidity of 90% or higher, the instrument cannot be charged, even by quickly unrolling a roll of tape. In extensive areas of heavy fallout, the occupants of most home basements, that provide inadequate shielding against heavy fallout radiation, would be in deadly danger. By using a dependable fallout meter, occupants would find that persons lying on the floor in certain locations would receive the smallest doses, and that, if they improvise additional shielding in these locations, the doses received could be greatly reduced. Additional shielding can be provided by making a very small shelter inside the basement where the dose rate is found to be lowest. Furniture, boxes, etc. can be used for walls, doors for the roof, and water containers, books, and other heavy objects for shielding, especially on the roof. Or, if tools are available, breaking through the basement floor and digging a shelter trench will greatly increase available protection against radiation. If a second expedient ventilating pump, a cap, or a small directional fan, is made and used as a fan, such an extremely cramped shelter inside a shelter usually can be occupied by several times as many persons as can occupy it without forced ventilation. End of instructions. Book page 236. Pattern A. Book page 237. Pattern B. Book page 238. Pattern C. Cut out this guide along its borderlines and tape to the top of a work table. Warning. The parts of the thread that will be inside the can and on which the leaf will be suspended must serve to insulate the high-voltage electrical charges to be placed on the leaf. Therefore, the suspended parts of the thread must be kept very clean. Book page 239. Reminders for operators. Reminders for operators. The drying agent inside a KFM is OK if, when the charged KFM is not exposed to radiation, its readings decrease by 1 mm or less in 3 hours. Reading. With the reading I 12 inches vertically above the seat. Note on the Tom scale the separation of the lower edges of the leaves. If the right leaf is at 10 mm and the left leaf is at 3 mm. The KFM reads 10 mm. Never take a reading while a leaf is touching a stop thread. Never use a reading that is less than 5 mm. Finding a dose rate. If before exposure a KFM reads 17 mm and if after a minute exposure it reads 5 mm. The difference in readings is 12 mm. The attached table shows the dose rate was 9.6 R/hour during the exposure. Finding a dose. If a person works outside for 3 hours where the dose rate is 2 R/hour. What is his radiation dose? Answer. 3 hour x 2 R/hour equals 6 R. Finding how long it takes to get a certain R dose. If the dose rate is 1.6 R/hour outside and a person is willing to take a 6 R dose, how long can he remain outside? Answer. 6 R, 1.6 R per hour 3.75 hour equals 3 hours and 45 minutes. Fallout radiation guides for a healthy person not previously exposed to a total radiation dose of more than 100 R during a 2-week period. 6 R per day can be tolerated for up to 2 months without losing the ability to work. 100 R in a week or less is not likely to seriously sicken. 350 R in a few days results in a 50-50 chance of dying, under post-attack conditions. 600 R in a week or less is almost certain to cause death within a few weeks. The drying agent inside a KFM is OK if, when the charged KFM is not exposed to radiation, its readings decrease by 1 mm or less in 3 hours. Reading. With the reading I 12 inches vertically above the seat. Note on the Tom scale the separation of the lower edges of the leaves. If the right leaf is at 10 mm and the left leaf is at 3 mm. The KFM reads 10 mm. Never take a reading while a leaf is touching a stop thread. Never use a reading that is less than 5 mm. Finding a dose rate. If before exposure a KFM reads 17 mm and if after a minute exposure it reads 5 mm. The difference in readings is 12 mm. The attached table shows the dose rate was 9.6 R/hour during the exposure. Finding a dose. If a person works outside for 3 hours where the dose rate is 2 R/hour. What is his radiation dose? Answer. 3 hour x 2 R/hour equals 6 R. Finding how long it takes to get a certain R dose. If the dose rate is 1.6 R/hour outside and a person is willing to take a 6 R dose, how long can he remain outside? Answer. 6 R, 1.6 R per hour 3.75 hour equals 3 hours and 45 minutes. Fallout radiation guides for a healthy person not previously exposed to a total radiation dose of more than 100 R during a 2-week period. 6 R per day can be tolerated for up to 2 months without losing the ability to work. 100 R in a week or less is not likely to seriously sicken. 350 R in a few days results in a 50-50 chance of dying, under post-attack conditions. 600 R in a week or less is almost certain to cause death within a few weeks. Book page 241. Instructions. A. Instructions for persons concerned with reproducing the KFM instructions. The KFM instruction pages are printed so that they can be readily cut out and pasted up, using the layout for 1-2 PAGE tabloid, given on page 242, to expedite rapid reproduction preparatory to mass distribution. No authorization is required to reproduce this survival information. All of the paste-ups should be photo-reduced to fit your size newspaper, except 4 cutouts paste-ups 15, 18, 21, and 24, and 1 drawing paste-up 26. Should remain at 100%. To make the instruction pages fully camera-ready for paste-up and photographing, it is necessary 1. To cut off each page's title and number, such as Instructions, page 2, and 2L4. 2. To use a camera invisible blue pencil to copy the numbers on the back of each page onto the front of that page, writing them in a blank space nearest to the approximate original position of the numbers. 3. To cut out each of the 40 paste-ups. On the back of each paste-up are the number of the tabloid page to which the paste-up is to be attached and, in parentheses, the number of the paste-up itself. For example, on the back of Instructions, page 2 inches are printed the following: PG1 2 and PG1 3. Thus, this page contains 2 paste-ups, both of which should be attached to page 1 of the tabloid paste-up. The positions in which they should be attached to page 1 are shown in the layout sketch on page 242. Timed field tests by 2 newspapers have shown that less than 40 minutes is required to begin printing a KFM tabloid. Each test began when the newspaper was given only written instructions like this page and the following layout page, along with KFM instructions like those in this book, except that the index numbers were already printed in camera invisible blue on each half page of the instructions. The camera-ready copy is for use with a straight lens, 100% horizontal and 100% vertical reproduction. Figure PG 241 tabloid layout sheet and centerfold of A12 PAGE tabloid, indicating tabloid page 6 and page 7. All photographs are 85-line screen. The following layout sketch for a 12-page tabloid indicates where each of the numbered paste-ups 1, 2, 40 should be pasted up and what spaces should be left blank. This positioning of the paste-ups is necessary to permit a KFM maker to cut out the patterns without destroying any instructions printed on opposite sides of the 12 tabloid pages. Figure PG 232 Instructions B, for photographer printer book page 243. Copyright 2000 Nuclear War Survival Skills. Also see the New Expedient Shelter book. Requires the DJVU plugin. NWSS Contents. Cover. Addition Notes. Table of Contents Book Order Form Forward. About the Author Acknowledgements Introduction. Ch. 1. The Dangers. Ch. 2. Warnings and Ch. 3. Psychologic. Ch. 4. Evacuation. Ch. 5. Shelter. Th. Ch. 6. Ventilation. Ch. 7. Protection. Ch. 8. Water. Ch. 9. Food. Ch. 10. Fallout raw. Ch. 11. Light. Ch. 12. Shelter saw. Ch. 13. Surviving. Ch. 14. Expedient. Ch. 15. Improvised. Ch. 16. Minimum PR. Ch. 17. Permanent. Ch. 18. Trans-Pachi. App. Instructio. App. A.1. Door COV. App. A.2. Pole COV. App. A.3. Small PO. App. A.4. Abovegrow. App. A.5. Abovegrow. App. A.6. Above GR. App. B. How to mock. App. C. A. Homemade. App. D. Expedient blast shelters. App. E. How to mock. App. F. Providing. Selected references. Selected index. Graphics. Nuclear War Survival Skills. Mail Home. App. D. Expedient blast shelters. Increasing importance. The majority of urban and suburban Americans would need blast shelters to avoid death or injury if they did not evacuate before an all-out nuclear attack. Most homes would be severely damaged by the 3 psi blast effects from a 1 megaton or larger weapon. Figure D.15. Tire strip hin. Degree made with the roof PO. Top previous next. Increasing importance. The majority of urban and suburban Americans would need blast shelters to avoid death or injury if they did not evacuate before an all-out nuclear attack. As nuclear arsenals continue to grow, an increasing majority would need the protection of blast shelters. In an attack on militarily relevant targets, as much as 5% of the total area of the 48 states could be subjected to blast damage severe enough to destroy or damage homes depending on the number of warheads assigned to each hard target, weapon reliability, etc. If blast shelters affording protection up to the 15 pounds per square inch, 15 psi, overpressure range were available to everybody and were occupied at the time of attack, the great majority of the occupants would survive all blast, fire, and radiation effects in the blast areas subjected to less than 15 psi blast effects. 15 psi blast shelters will survive as close as about 1.5 miles from ground zero of a 1 megaton surface burst, and about 2.3 miles from ground zero or a 1 megaton air burst. Except in high-density urban areas where the air supply openings and exits of shelters are all too likely to be covered with blast-hurled debris, the area in which people inside good earth-covered 15 psi blast shelters would be killed would be only about 1/6 as large as the area in which most people sheltered in typical American homes probably would die from blast and fire effects alone. Blast tests have indicated that the small pole shelter, the most blast-resistant of the earth-covered expedient shelters described in Appendix A, should enable its occupants to survive up to the 50 psi overpressure range if built with the blast-resistant and radiation-protective features described in following sections, and if located outside an urban area. Calculations show that this earth-covered expedient blast shelter also would give adequate protection at the 50 psi blast overpressure range against the intense initial nuclear radiation that is emitted from the fireball of a 1 megaton explosion. However, to make this shelter, see page 258, provide adequate protection against the even more intense initial nuclear radiation that would reach the 50 psi overpressure range from the fireball of a 500 kiloton or smaller explosion, it should have at least 6 feet of earth cover and additional cans of water should be kept ready to be placed in the horizontal parts of the entryways promptly after the shelter is occupied. The life-saving potential of well-designed, well-built blast shelters is a demonstrated fact. Millions of Americans living in high-risk areas would be able to build expedient blast shelters within only a few days provided they were given field-tested instructions, had made some preparations before the crisis arose, had a few days of recognized warning, and during the crisis were motivated by the president. The following information is given in the hope of encouraging more Americans to make preparations for blast protection. Also, it may serve to increase the number who realize the need for permanent blast shelters in high-risk blast areas. Some informed citizens, particularly those who live near large cities or in their outer suburbs, may choose to build earth-covered expedient blast shelters in their backyards, rather than to evacuate. Going into a strange area and trying to build or find good shelter and other essentials of life would entail risks that many people might hesitate to take, particularly if they live outside the probable areas of severe blast damage. For such citizens, the best decision might be to stay at home, build earth-covered expedient blast shelters, supply them with the essentials for long occupancy, and remain with their possessions. The following descriptions of the characteristics and components of expedient blast shelters should enable many readers to use locally available materials to provide at least 15 psi blast protection. Pre-crisis preparations are essential, as well as the ability to work very hard for 2 to 4 days. Field-tested instructions are not yet available. To date, only workers who were supervised have built expedient blast shelters. 5. Practicality of expedient blast shelters. At Hiroshima and Nagasaki, simple wood-framed shelters with about 3 feet of earth over wooden roofs were undamaged by blast effects in areas where substantial buildings were demolished. 4 Book page 244. Figure D1 shows a Hiroshima shelter that people with hand tools could build in a day, if poles or timber were available. This shelter withstood blast and fire at an overpressure range of about 65 psi. Its narrow room and a 3-foot thick earth cover brought about effective earth arching. This kept its yielding wooden frame from being broken. Figure D1. A small, earth-covered backyard shelter with a crude wooden frame undamaged, although only 300 yards from ground zero at Hiroshima. Although the shelter itself was undamaged, its occupants would have been fatally injured because the shelter had no blast door. The combined effect of blast waves, excessive pressure, blast wind, and burns from extremely hot dust blown into the shelter, the popcorning effect, and from the heated air would have killed the occupants. For people to survive in areas of severe blast, their shelters must have strong blast doors. In nuclear weapons tests in the Nevada desert, box-like shelters built of lumber and covered with sandy earth were structurally undamaged by 10 to 15 psi blast effects. However, None had blast doors, so occupants of these open shelters would have been injured by blast effects and burned as a result of the popcorning effect. Furthermore, blast winds blew away much of the dry, sandy earth mounded over the shelters for shielding. This resulted in inadequate protection against fallout radiation. 12 different types of expedient shelters were blast tested by Oak Ridge National Laboratory during 3 of Defense Nuclear Agency's blast tests. 52 of these tests each involved the detonation of 1 million pounds or more of conventional explosive. Air blast effects equivalent to those from a 1 kiloton nuclear surface burst were produced by these chemical explosions. Several of these shelters had expedient blast doors which were closed during the tests. Figure D2 shows the undamaged interior of the best expedient blast shelter tested prior to 1978, an improved version of the small pole shelter described in Appendix A. Its 2 heavy plywood blast doors excluded practically all blast effects. The pressure inside rose only to 1.5 psi and overpressure not nearly high enough to break eardrums. The only damage was to the expedient shelter ventilating pump, a cap, in the stoop-in entryway. 2 men worked about 5 minutes to replace the 4 flap valves that were blown loose. Figure D.2. Undamaged interior of a small pole shelter after blast testing at the 53 psi. Overpressure range. Large buildings would have been completely demolished. Book page 245. When blast tested at 5 psi overpressure, not even the weakest covered trench shelters with unsupported earth walls, described in Appendix A, were damaged structurally. However, if the covering earth were sandy and dry and if it were exposed to the blast winds of a megaton explosion at the 5 psi overpressure range, so much earth would be blown away that the shelter would give insufficient protection against fallout radiation. Much of the dry, shielding earth mounded over some of the above-ground shelters was, in fact, removed by the blast winds of these relatively small test explosions, even at the lower overpressure ranges at which homes would be wrecked. In contrast, in blast tests where the steeply mounded earth was damp, little blast wind erosion resulted. The reader should remember that even if shelters without blast doors are undamaged, the occupants are likely to suffer injuries. Construction principles. Millions of Americans, if given good instructions, strong motivation, and several days to work, should be able to build blast shelters with materials found in many rural areas and suburban neighborhoods. During a crisis, yard trees could be cut down for poles and sticks, and a garage or part of a house could be torn down for lumber. Many average citizens could build expedient blast shelters if they learned to utilize earth arching by making a yielding shelter. The remarkable protection that earth arching gives to those parts of a shelter designed to use it is illustrated by Figure D.3. Figure D.3. Effective earth arching in the earth covering of this 4 ft wide pole-covered trench shelter prevented a single pole from being broken by blast forces that exerted a downward force of 53 psi, over 3-half a ton per square foot, on the overlying earth. This picture shows the unbroken roof of a 4-foot-wide pole-covered trench shelter that was built in rock-like soil and blast-tested where the blast pressure outside was 53 psi. Its strong blast doors prevented the blast wave from entering. Without the protection of earth arching that developed in the 5 feet of earth cover over the yielding roof poles, the poles would have been broken like straws. In contrast, the ground shock and earth pressure produced by 1 kiloton blast effects almost completely collapsed the unsupported, rock-like earth walls. Figure D.4. Post-blast interior of an above-ground, door-covered shelter that survived. 1 kiloton blast effects at the 5.8 psi overpressure range. The shelter walls were made of bedsheets containing earth, as described in Appendix A. Figure D4 also indicates the effectiveness of earth arching. This photo shows the roof of a small, earth-covered fallout shelter, as it appeared after surviving blast effects severe enough to demolish most homes. The roof was made of light, hollow core, interior doors and looks as though it had been completely broken. In fact, only the lower sheets of 1/8-inch thick veneer of the hollow core interior doors were broken. These breaks were caused by a faulty construction procedure. A front-end loader had dumped several tons of earth onto the uncovered doors. The upper 1/8-inch thick sheets of veneer were bowed downward, unbroken, until an earth arch formed in the 2-foot thick earth covering and prevented the thin sheets from being broken. Earth arching also prevented this roof from being smashed in by blast overpressure that exerted a pressure of 5.8 psi, 835 pounds per square foot, on the surface of the earth mounted over this open shelter. See Appendix A for details of construction. Book page 246. Degree make shelters with the minimum practical ceiling height and width. Most of the narrow-covered trench shelters used by tens of thousands of Londoners during the World War II Blitz were built with only 4-1/2 foot ceilings, to maximize blast protection and minimize high water table problems. These shelters were found to be among the safest for protection against nearby explosions. The Chinese also have a good understanding of this design principle and skillfully utilize the protection provided by earth arching. A Chinese civil defense handbook states, the height and width of tunnel shelters should be kept to the minimum required to accommodate the sheltering requirements, and the thicker the protective layer of earth, the greater the ability to resist blast waves. 21. Degree sure earth walls to prevent their caving in as a result of ground shock and earth pressure. Most unshored, that is, unsupported, earth walls are partially collapsed by ground shock at much lower blast overpressures than those at which a flexible roof protected by earth arching is damaged. Figure D5 is a picture of a seated dummy taken by a high-speed movie camera mounted inside an unshored, polycovered trench shelter of the Russian type tested at the 20 psi range. A second dummy was obscured by blast-torn curtains made of blankets. The shelter had an open stairway entryway, positioned at right angles to the stand-up height trench and facing away from the targeted city, so as to minimize the entry of blast waves and blast wind. Figure D.5. A dummy in an unshored pole-covered trench shelter as it is struck by collapsing rock-like earth walls. The photo also shows the shelter's blanket curtains as they are torn and blown into the shelter by the 180 mph blast wind. Immediately after this photo was taken, the dummies were hit by the airborne blast wave and blast wind. Outside, the blast wind peaked at about 490 miles per hour. Figure D6 is a post-blast view of the essentially undamaged earth-covered roof poles and the disastrously collapsed, unshored shelter walls of the Russian shelter tested at 20 psi.21. Russian civil defense books state that unshored fallout shelters do not survive closer to the blast than the 7 psi overpressure range. This limitation was confirmed by an identical shelter tested at 7 psi. Parts of its unshored walls were quite badly collapsed by the ground shock from an explosion, producing merely 1 kiloton blast effects. Figure D.6. Dummies after ground shock from 1 kiloton blast effects at the 20 psi range had collapsed the rock-like walls of a hardened desert soil called caliche. The dummies' steel, bones, and joints prevented them from being knocked down and buried. The fallen caliche all around them kept them from being blown over by the air blast wave and 180 mph blast wind that followed. Unsupported earth walls should be sloped as much as practical. The length and strength of available roofing material should be considered and, in order to attain effective earth arching, the thickness of the earth cover should be at least half as great as the distance between the edges of the trench. The stability of the earth determines the proper method for shoring the walls of a trench shelter. Book page 247. Methods for shoring both loose, unstable earth and firm, stable earth are described below. In loose, unstable earth such as sand, the walls of all underground shelters must be shored. First, an oversized trench must be dug with gently sloping sides. Next, the shoring is built, often as a freestanding, roofless structure. Then earth must be backfilled around the shoring to a level a few inches higher than the uppermost parts of the shoring, as in figure D.7. Finally, the roof poles or planks must be placed so that they are supported only by the backfilled earth. Blast tests have indicated that a pole-covered trench shelter thus proportioned and lightly shored should protect its occupants against disastrous collapse of its walls at overpressure ranges up to 15 psi. In firm, stable earth, it is best first to dig a trench a few inches wider than 7 feet, the length of the roof poles, and 1 foot deep. Next, dig the part to be shored, down the center of this shallow trench, using the dimensions given for the shoring in figure D.7. The trench walls should be sloped and smoothed quite accurately, so that the shoring can be tightened against the earth. If the shoring does not press tightly against the trench walls, large wedges of earth may be jarred loose, hit the shoring, and cause it to collapse. A different, comparatively simple way to tighten shoring is indicated by figure D.8. This sketch shows a 4-pole frame designed to be installed every 2-1/2 foot along a trench in stable earth and to be tightened against trench wall shoring with the same dimensions as those shown in figure D.7. Note that the 2 horizontal brace poles have shallow V notches sawed in both ends. Figure D.7. An illustration of several ways to shore a trench in unstable earth, using various materials. A 4-piece frame consisting of 4 poles, or 4 boards, installed as shown above, should be installed every 2-1/2 foot along the length of the trench, including the horizontal parts of the entryways. All parts of the shoring should be at least 2 inches below the roof poles, so that the downward forces on the roof will press only on the earth. ORNLDWG 78-14430R, book page 248. Figure D.8. A 4-pole frame designed so that it can be tightened against the shoring materials that must press firmly against the walls of a trench dug in stable earth. In this sketch, the middle sections of 3 poles have been removed, so that the upper brace pole may be seen more clearly. ORNLDWG 78-17246R. If these brace poles are driven downward when positioned as shown, the 2 wall poles are forced outward against the shoring materials placed between them and the earth walls. An upper brace pole should be cut to the length needed to make it approximately the same height as the roof poles on each side of it, no higher, after the shoring is tightened. Finally, each V-notched end should be nailed to its wall pole. Light, yielding poles can serve simultaneously both to roof and to shore a shelter. A good example is the Chinese man shelter illustrated in figure D.9, requiring comparatively few poles to build. 21 This shelter is too cramped for long occupancy, and its unshored, lower earth walls can be squeezed in by blast pressure. Therefore, it is not recommended if sufficient materials are available for building a well-shored, covered trench shelter. It is described here primarily to help the reader understand the construction of similarly designed entryways, outlined later in this appendix. The room and the horizontal entryway of the model tested were made of 6-1/2 foot poles averaging only 3 inches in diameter. It had 2 vertical, triangular entries of ORNL design. Each was protected by an expedient triangular blast door made of poles. In figure D.9, note the 2 small horizontal poles at the top of the triangle, one tied inside and the other tied outside the triangle, to hold the wall poles together. Before covering this shelter with earth, a 6-inch thick covering of small limbs was placed horizontally across the approximately 3-inch wide spaces between the 6-1/2 foot wall poles. The limbs were then covered with bed sheets. Figure D.9. Chinese man shelter tested at 20 psi, and undamaged because the thin poles yielded and were protected by earth arching. This drawing was taken from a Chinese civil defense manual. The dimensions are in centimeters. When blast tested in loose, unstable soil, the unsupported earth walls of the trench below the wall poles were squeezed in. The 12-inch width of the foot trench was reduced to as little as 4 inches by the short-duration forces produced by 0.2 kiloton blast effects at 50 psi. The much longer duration forces of a megaton explosion would be far more damaging to the shelter at lower overpressure ranges, due to destabilizing and squeezing in unshored earth at depths many feet below ground level. Calculations based on blast test findings indicate that the unsupported earth walls of a shelter are likely to fail if the above-ground maximum overpressure is greater than 5 to 7 psi and this overpressure is caused by an explosion that is a megaton or more. Book page 249. Top previous next. Most homes would be severely damaged by the 3 psi blast effects from a 1 megaton or larger weapon. This damage would result 1 mile closer to ground zero of a 1 megaton surface burst than the distance at which the unshored earth walls of some shelters would be collapsed. For a 20 megaton surface burst, the corresponding reduction in distance would be about 2.7 miles. Build sufficiently long and strong entryways. Blast shelters need longer horizontal entryways, taller vertical entryways, and thicker earth cover than do most fallout shelters. These are needed primarily for increased protection against high levels of initial nuclear radiation. The entryways of the small pole shelter described in Appendix A.3, with the improvements for increased blast protection outlined in the following section of this appendix, afford protection against both blast and radiation up to the 50 psi overpressure range. However, these entryways require straight poles 14 feet long. These may be difficult to find or transport. In contrast, both the horizontal and the vertical parts of the triangular entry pictured in Figs. D.10, D.11, and D.12 require only small diameter, short poles. Triangular entries of this type were undamaged by 1 kiloton blast effects at the 20 psi overpressure range 5 and by 0.2 kiloton blast effects at 50 psi. This type of entry and its blast door, also triangular and made of short poles, can be used with a wide variety of expedient blast shelters and should withstand megaton blast effects at 25 psi. Therefore, their construction is described in considerable detail. The horizontal part of a triangular entry. If the Chinese man shelter shown in Figure D9 is made without excavating the unshored lower trench that forms its earth seats, it will serve as a horizontal, shored crawlway entry affording blast protection up to at least the 25 psi overpressure range. 2 horizontal entries, one at each end of the shelter, should be provided. Each entry should be 10 feet long. This length is needed to reduce the amount of initial nuclear radiation reaching the blast shelter room while assuring adequate through ventilation. The outer part of such a horizontal entry is pictured in the background of Figure D.10. The vertical part of a triangular entry. The lower section of the vertical part is made in a similar manner to the horizontal shelter shown in Figure D.9. Figure D.10 shows 4-1/2 foot horizontal poles, one forming A, B, with one end of each pole laid on top of the adjacent lower pole. The other ends of these poles, 1, are pressed against the 2 pairs of vertical posts 2. After this photo was taken, the tops of these 2 pairs of vertical posts were sawed off as shown in Figure D.11. The 4-1/2 foot horizontal poles, 1, were kept level by the short spacer poles, 3, that were wired or nailed in place. Figure D10. Uncompleted lower section of a vertical triangular entry. Photo 295477R, book page 250. Figure D11. Lower part of a vertical triangular entry, showing its connection to the horizontal part of the shelter entry. ORNLDWG78-14675. Book page 251. Figure D12. Completed frame of Chinese man shelter showing its 2 ORNL designed entryways, one at each end, and triangular blast doors made of poles. Before covering the triangular vertical entries with earth, tree branches were placed vertically over the sides. The branches then were covered with bed sheets. Horizontal branches, also covered with bed sheets, were laid over the rest of the shelter frame. After being covered with earth, this shelter was subjected to 1 kiloton blast effects. Multiple earth arching over and around this yielding structure prevented both the small poles and the bedsheets from being damaged at 20 psi. Each pair of vertical posts, 2, was securely wired together at top and bottom. The 2 pairs were held apart at top and bottom by 2 horizontal brace poles toenailed in place to frame the rectangular 30x 30-inch crawlway, doorway, between the vertical entry and the horizontal entry. Only the upper pole, 4, of these 2 30-inch long horizontal brace poles is shown. The 2 pairs of vertical posts, 2, were positioned so that they pressed against 2 7-1/2 foot horizontal poles, 5, only the uppermost is shown. These in turn pressed against the outermost 2 poles, 6, of the horizontal entry and against the earth in 2 slot trenches dug in the sidewalls of the excavation. These 2 7-1/2 foot poles, 5, should be at least 6 inches in diameter. Additional details of the lower section of this vertical triangular entry are given in Figure D.11. If horizontal poles considerably larger in diameter than those illustrated are used, fewer poles are required and strength is increased. However, the space inside the entry is decreased unless the larger diameter horizontal poles that form the V are made longer than 4-1/2 featuring. As shown on the left in Figure D.10, a small, vertical pole, 7, was placed in the small, V, between the outer ends of the horizontal poles that form the lower section of the vertical entry. After this photo was taken, a second small, vertical pole was positioned in the adjacent large, V, inside the entry. These two poles, 7, were then tightly wired together so as to make a strong, somewhat yielding, outer corner connection of the horizontal poles, 1, in the same way that the tops of the side wall poles of the Chinese man shelter are bound together. The upper section of the vertical part of this entry, the section above the tops of the two pairs of vertical posts shown in Figure D.10 and Figure D.11, is made by overlapping the ends of its nearly horizontal poles, Figure D.12. These poles, marked with a 1 in Figure D.10, were each 4 feet 6 inches long and varied uniformly in diameter from about 2-1/2 an inch just above the two pairs of wired together posts, to 4-inch diameters just below the triangular door frame of poles. The triangular-shaped blast door was hinged to and closed against this door frame. The hinges were strips cut from worn auto tires, to be described shortly. Book page 252. The upper section is formed by laying poles in a triangular pattern, ends crossing at the angles, with large ends and small ends placed so that the poles are as nearly horizontal as is practical. Each of its 3 corners is held together by strong wires that tightly bind an outside and an inside small vertical pole, in the same manner as the top of the Chinese man shelter, shown in Figure D.9, is secured. Instead of number 9 soft steel wire, rope or twisted strips of strong fabric could be used. Before starting to install the upper section of a vertical triangular entry, the 3 outermost of the 6 small vertical poles that will hold the 3 corners together should be connected temporarily with 3 small horizontal poles. Connect them at the height of the door frame planned for the triangular blast door, and space them so as to be the same size as this door frame. Next, all the horizontal poles should be laid out on the ground in the order of their increasing diameters. The triangular entry then should be started with the smallest poles at the base, with increasingly large diameter poles used toward the top so that the 3 pairs of small vertical poles will press securely against all the horizontal side poles of the entry. To prevent the negative overpressure, suction, phase of the blast from yanking out and carrying away the blast door and the upper part of the vertical entry to which it is hinged, the uppermost 4 or 5 horizontal poles of each of the 3 sides of the vertical entry should be wired or tied securely together. Rope or strips of strong cloth can be used if strong wire is not available. Before placing earth around this lightly constructed blast protective entry, the vertical walls must be covered to a thickness of about 6 inches with a yielding, crushable covering of limbs, brush, or innerspring mattresses. Limbs or brush should be placed in 3 layers, with the innermost layer at right angles to the underlying poles. The yielding thickness then is covered with strong cloth, such as 50% Dacron bedsheets, or 2 thicknesses of 4 mil polyethylene film. This outermost covering keeps loose earth or sand from filling spaces inside the yielding layer or running into the entry. Thus protected, this vertical entry should be undamaged by 25 psi blast effects of megaton weapons. A vertical blast protective entry can also be made like a strong box, using 2-inch thick boards. Such entries afford blast protection up to 50 psi if made as small as shown here and protected with yielding materials such as a 6-inch thick layer of brush covered with strong cloth. Figure PG 252A vertical blast protective entry. 22 in x 28 in. Degree install blast doors to keep out airborne blast waves, blast wind, overpressure, blast-borne debris, burning hot dust and air, and fallout. A fast-rising overpressure of as little as 5 psi will break some people's eardrums. At overpressures of 15 to 20 psi, 50% of the people who are exposed will have their eardrums broken. However, persons near a shelter wall may have their eardrums broken by somewhat less than half of these unreflected overpressures. Any wall may reflect blast waves and greatly increase overpressures near it. Broken eardrums are not serious in normal times, but after a nuclear attack this injury is likely to be far more dangerous to persons in crowded shelters without effective medical treatment. Lung damage, that can result from overpressures as low as 10 to 12 psi, would also be more serious under post-attack conditions. A blast door must withstand blast waves and overpressure. Not only must the door itself be sufficiently strong to withstand forces at least as great as those which the shelter will survive, but in addition the door frame and the entranceway walls must be equally as strong. The expedient blast door pictured in figure D13 was made of rough boards, each a full 2 inches thick. It had a continuous row of hinges made of 18-inch long strips cut from the treads of worn car tires. Book page 253. Figure D.13. Blast door surrounded by 4 blast protector logs that were notched and nailed together. The wet, mounded soil had been compacted by the blast but not blown away. The strips were nailed to the vertical poles on one side of the vertical entry. These and other details of construction are shown in figure D14. Although the 2 center boards were badly cracked by the shock wave and overpressure at the 17 psi range, the door pictured in figure D.13 afforded good protection against all blast effects from a surface explosion of 1 million pounds of TNT. In figure D.14, note the essential, strong tie-down attachment of the wires at the bottom of the vertical entry, to prevent the blast door from being yanked open by the negative pressure, suction, that follows the overpressure. Blast doors must be protected against reflected pressures from blast waves that could strike an edge of an unprotected door and tear it off its hinges. Note the blast protector logs installed around the door pictured in figure D14. When the door was closed, the tops of these 4 logs were about 2 inches higher than the door, thus protecting its edges on all sides. The closed door must be prevented from rebounding like a spring and opening a fraction of a second after being bowed down by overpressure, or from being opened and perhaps torn off its hinges by the partial vacuum, suction, that follows the overpressure phase. Figure D14 gives the details of such a hold-down system for a blast door. Note that near the bottom of the vertical entry the 6 strong wires must encircle a horizontal pole that is flattened on one side and nailed to the vertical wall poles with at least a dozen 6-inch, 60-penny nails. Blast tests up to the 53 psi overpressure range have proved that this hold-down system works. 5. Figure D15 shows a blast door made of 5 thicknesses of 3/4 inch exterior plywood, well glued and nailed together with 4-1/2 in nails at 4 in spacings. This door was protected by 4 blast protector logs, each 8 feet long and about 8 inches in diameter. The logs were notched, nailed together, and surrounded with earth. For protection against ignition by the thermal pulse from an explosion, exposed wood and rubber should be coated with thick whitewash, slaked lime, or mud, or covered with aluminum foil. An equally strong blast door and the door base upon which it closes can be made of poles. If poles are fresh cut, they are easy to work with axe and saw. Figure D.16 shows the best blast-tested design. This door also had a continuous row of hinges made from worn auto tire treads. The pole to which the hinges were attached was 7 inches in diameter after peeling and had been flattened on its top and outer sides. The 2 other poles of the equal-sided triangle were 8 inches in diameter and had been flattened with an axe on the bottom, top, and inner sides. The 3 poles were each 55 inches long. They were notched and spiked together with 60-penny nails so that the door would close snugly on its similarly constructed base made of 3 stout poles. Other poles, at least 7 inches in diameter before being hewn so that they would fit together snugly, were nailed side by side on top of the 3 outer poles. Many Americans have axes and would be able to cut poles, but not many know how to use an axe to hew flat, square sides on a pole or log. This easily acquired skill is illustrated by figure D.17. The worker should first fasten the pole down by nailing 2 small poles to it and 2 other logs on the ground. Figure D17 shows a pole thus secured. When hewing a flat side, the worker stands with his legs spread far apart, and repeatedly moves his feet so that he can look almost straight down at where his axe head strikes. First, vertical cuts with a sharp axe are made about 3 or 4 inches apart and at angles of about 45 degrees to the surface of the pole, for the length of the pole. These multiple cuts should be made almost as deep as is needed to produce a flat side of the desired width. Then the worker, again beginning at the starting end, should cut off long strips, producing a flat side. Book page 254. Figure D.14. Expedient blast door that can be closed and secured in 4 seconds. 4 seconds would be too little time if the shelter is at the 15 psi overpressure range from a 550 kiloton or smaller warhead typical of the 1987 Soviet ICBM arsenal. See the last paragraph on page 255. However, this door closure is still the best blast-tested expedient means to secure a closed blast door. ORNLDWG 731063. Book page 255. Top previous next. Figure D.15. Tire strip hinges nailed to an expedient, 4-inch thick blast door made of plywood, designed to withstand 50 psi blast effects of very large weapons and undamaged by blast at the 53 psi range. Figure D.16. Blast-tested triangular blast door made of hand-hewn pine poles, notched and nailed together. This door closed on a triangular pole base that is concealed in this photo by 2 of the 3 blast protector logs that also withstood 53 psi blast effects. Figure D.17. Hewing flat sides on a pole with a sharp axe. To hew a second flat side at right angles to the first side, rotate the pole 900, secure it again, and repeat as pictured in figure D.17. Degree provide blast closures for an adequate ventilation system. The following 2 expedient closure systems permit adequate volumes of ventilating air to be pumped through a shelter. 1. Install 2 blast doors, one on each end of the shelter, designed to be left open until the extremely bright light from a large blast is seen. Figure D14 shows a door held open by a prop stick that can be yanked away by the attached pull cord. While propped open, one blast door serves as an extremely low resistance air intake opening, and the other serves as an air exhaust opening. A large cap can pump air at the rate of several thousand cubic feet per minute through such open doors. When an attack is expected, each pull cord should be held by a shelter occupant who stays ready at all times to yank out the prop stick as soon as he sees the light of an explosion. After the door has fallen closed, the loop at the end of its wire bridle is close to the upper hook of the load binder and at the same height, figure D.14. The person who closes the door should quickly hook the upper hook of the load binder into the wire loop and pull down on the handle of the load binder. The door will then be tightly shut. Sources during an emergency would be the millions of load binders owned by truckers and farmers. At distances from a large explosion where blast wave and overpressure effects are not destructive enough to smash most good expedient blast shelters, there is enough time between the instant the light of the explosion is seen and the arrival of its blast wave for an alert person to shut and securely fasten a well-designed blast door. The smaller the explosion and the greater the overpressure range, the shorter the warning time. Thus at the 15 psi overpressure range from a 1 megaton surface burst, 1.5 miles, the blast wave arrives about 2.8 seconds after the light, whereas at the 10 psi overpressure range from a 1 megaton surface burst, 1.9 miles, the blast wave arrives about 4.5 seconds after the light. For a 20 megaton surface burst, the warning time at the 15 psi range is about 8 seconds, and at the 30 psi overpressure range, about 4 seconds. Experiments have shown that even people who react quite slowly can close and secure this door within 4 seconds after seeing a spotlight shine on the door without warning. Book page 256. 2. Build a vertical air shaft next to the outermost side of each vertical entry, with an overlapping flaps blast valve, see figure D18, connecting each entry to its air shaft, as shown in figure D19. These air shafts and blast valves permit forced ventilation to be maintained when the 2 blast doors are closed. Figure D18 illustrates the construction of a fast-closing expedient blast valve, a design that was undamaged by the 65 psi shock wave and other effects produced by the explosion of 1 million pounds of TNT. When blast tested in a shock tube at 100 psi, the flaps were undamaged. They closed in 6/1000ths of a second, 0.006 seconds. This is as fast as the best factory-made blast valves close. Figure D.18. Overlapping flaps blast valve, made of boards, plywood, and strips cut from the treads of worn car tires. ORNLDWG 732229A, to withstand 50 psi, the load-bearing, 2-inch, boards, actually 1-1/2 inch thick, of the valve should be at least 6 inches wide, if the 1 in high air openings are each made 12 in wide. measured between two vertical poles of a shelter entry. See figure D.19. That gives the dimensions of a valve that has been blast tested. 5 Note that there are 5 inches of solid wood at each end of each 1 in high air opening. If there are 5 such air openings to a valve, a properly installed cap, Appendix B, can pump air at about 125 cubic feet per minute, 125 cfm, through a shelter equipped with such valves. This ventilation rate is ample for at least 40 people in cold weather. Except in hot and humid weather, a constant air supply of about 10 cfm per shelter occupant is enough to maintain tolerable conditions during continuous shelter occupancy for many days. Figure D.19. Installation of a 50 psi overlapping flaps blast valve in such a way that it will not be blown into a shelter by the blast overpressure, nor pulled out by the following negative pressure, suction, phase. ORNLDWG78-14429R. If a factory-made blower capable of pumping more than 100 cfm is available, use it. Such a hand-operated blower can pump against much higher air flow resistances than a cap can. It can pump its full rated volume of outdoor air through a shelter equipped with 2 overlapping flaps blast valves, one at each end of the shelter and each with only 2 air openings, providing a total of 24 square inches of openings per valve. Equally or more effective is a home-makeable plywood doubly action piston pump, made and operated as described in Appendix E. Book page 257. Remember that a pressure of 7,200 pounds pushes against each square foot of the exposed face of a blast valve when it is subjected to a 50 psi blast overpressure. Also keep in mind that the suction that follows can exert an outwardly directed force of up to 700 pounds per square foot on the valve face and can yank it out of position unless it is securely installed. Figure D19 shows how to securely install a blast valve. Merely nailing a blast valve in its opening will not enable it to withstand severe blast forces. Note in figure D19 that an opening is shown between the back edge of the uppermost board of the overlapping flaps blast valve and the adjacent horizontal pole of the vertical entry. Both this opening and the similar opening next to the lowermost board of the blast valve should be closed off with a stout board, to prevent blast from going through these openings and on into a vertical entry in the shelter room. The top of an air shaft should be a few inches higher than the earth piled around it, as are the tops of the vertical entries of the small pole shelter illustrated in figure 8.3.1 on page 174. To minimize the amount of rain that may fall into an air shaft, a shed-like, open-sided miniature roof should be placed over it, a few inches above its top. The roof can be lightly constructed, since it will be blown away by a severe blast. Minimize above-ground construction and the mounting of shielding earth. At high overpressure ranges, the shock wave and the blast wind drag can wreck an above-ground shelter entry. For example, the 5ft high earth mound over a shelter built with its pole roof at ground level was moved enough by 1 kiloton air blast effects at the 53 psi overpressure range to break one of the poles of a blast door frame. The forces of a 1 megaton explosion at the same overpressure range would have operated 10 times as long, and probably would have smashed the vertical entryways of this shelter. Whenever practical, a blast shelter should be built far enough below ground so that the top of its shielding earth cover is at ground level. Avoiding above-ground construction and earth mounds also greatly reduces the chances of damage from blast-hurled, heavy debris, such as tree trunks and pieces of buildings. Dry earth, steeply mounded over a shelter which is subjected to blast winds from a big explosion, will be mostly blown away. However, blast wind, scouring, of wet earth is negligible. The blast winds from a 1 kiloton explosion at the 31 psi overpressure range scoured away 17 inches of dry, sandy soil mounded at a slope of 32 degrees. If it is impractical to build a blast shelter with its roof below ground, good projection can be attained by mounding even dry earth at slopes not steeper than 10 degrees. Provide adequate shielding against initial nuclear radiation. Good expedient blast shelters require a greater thickness of earth cover than is needed on good fallout shelters, for these reasons. Blast shelters should also protect against initial nuclear radiation emitted by the fireball. This radiation is reduced by half when it penetrates about 5 inches of packed earth, as compared to a having thickness of only about 3–1/2 inch of earth against radiation from fallout. The initial radiation, in some areas where good blast shelters will survive, can be much greater than the fallout radiation is likely to be. Initial nuclear radiation that comes through entryways is more difficult to attenuate, reduce, than fallout radiation. Therefore, longer entryways or additional right-angle turns must be provided. For these reasons, good blast shelters should be covered with at least 4 feet of well-packed, average weight earth, or 5 feet of unpacked or light earth. A3 featuring thickness gives excellent protection against radiation from fallout. A5 0 psi small pole shelter. This expedient blast shelter is described in detail to enable the reader to build this model. The details will help him better understand the design principles of other expedient blast shelters that are capable of preventing injuries from blast effects severe enough to destroy all ordinary buildings and kill the occupants. Blast tests and calculations have indicated that the small pole shelter described and illustrated in Appendix A.3 will afford protection against all weapon effects at overpressure ranges up to 50 psi that are produced by an explosion of 1 megaton, or larger, provided the shelter is degree made with horizontal entryways each with ceilings no higher than 7 feet, 2 in, no wider than 3 feet, and each at least 10 feet long to lessen the radiation coming through the entries, see Fig. D.20. Lower and narrower entryways would give better protection but would increase the time required for entry. Degree constructed with a floor of poles that are 4 in, or more in diameter, laid side by side, with the wall poles resting on the floor poles. The ground shock and earth pressures at a depth of 10 feet or more resulting from an overpressure on the surface of more than about 35 psi, if caused by a large explosion, may destabilize and squeeze earth upward into the shelter through an unprotected earth floor. The small pole shelter described in Appendix A.3 has an earth floor. Degree installed in an excavation about 13 feet deep, with the shelter's vertical entrances appropriately increased in height so that the blast doors are only about 1 foot above the original ground level. To prevent possibly life-endangering caving of the 13-foot deep trench that was dug for the blast testing of this model shelter, the trench walls were sloped about 45 degrees. The shelter was built as a braced, freestanding structure, and then covered. During a crisis it would be impractical to safely excavate a deep trench with steeply sloping walls and then safely build a shelter in it. A 13-foot deep trench is usually too deep to dig by hand, especially since to dig it with safely sloping walls requires the removal of a large amount of earth. Book page 258. ORNLDWG78-18835. Figure D.20. Entryway of small pole blast shelter shielded against initial nuclear radiation. This sketch is a simplified vertical section through the centerline of one end of the shelter. Degree made with 4 rectangular horizontal braces in each vertical entry, in addition to the ends of the 2 long, ladder-like braces. The detailed drawings in Appendix A show such braces. The lowest rectangular brace should be positioned 3-1/2 a foot above the flooring at the bottom of the vertical entry, see Figure D.20. Degree equipped with blast doors each made of 5 sheets of 3/4 inch exterior plywood, see Figure D.15, bonded with resin glue and nailed together with 4-1/2 in nails. The nails should be driven on 4 in spacings and their protruding ends should be clinched, bent over. The blast doors must be secured against being yanked open by negative pressure, suction, by securing them with a strong wire bridle, see Fig. D.14, and with the lower, fixed wire strongly connected near the bottom of the entry to all of the vertical poles on one side, as shown in Figure D.14. Degree provided with an adequate ventilation pump and with ventilation openings protected against blast by expedient blast valves, Figure D.18, installed in the vertical entries as shown in Figure D.19, to protect the air intake and the air exhaust openings. Ventilation openings should be as far as practical from buildings and combustible materials. Manually closed ventilation openings are not effective at the 50 psi overpressure range of most weapons, because there is insufficient time to close them between the arrival of the warning light from the explosion and the arrival of the blast wave. Book page 259. Top previous next. Degree made with the roof poles covered by a yielding layer of brush or limbs about 6 inches thick, or of inner spring mattresses. This yielding layer in turn should be covered with bedsheets or other strong cloth, to increase the effectiveness of protective earth arching. Brush or limbs should be laid in 3 layers with sticks of the middle layer perpendicular to those of the other 2 layers. Degree covered with 5 feet of earth, sloped no steeper than 10 degrees. Degree provided with additional shielding materials in the entryways, as shown in Figure D.20. Such shielding would be needed to prevent occupants from receiving possibly incapacitating or fatal doses of initial nuclear radiation through the entryways at the 50 psi overpressure range, if the shelter is subjected to the effects of a weapon that is 1 megaton, or larger, in explosive yield. Damp earth serves better for neutron shielding material than dry earth and can be substituted for water as shielding material if sufficient water containers are not available. At the 50 psi overpressure range from explosions smaller than 1 megaton, the entry and shielding shown in Figure D.20 may not provide adequate protection against initial nuclear radiation. When the shelter is readied for rapid occupancy, the shelter ventilating cap is secured against the ceiling, and the bags of earth in the doorway, under the cap, are removed. Persons entering the shelter would stoop to go under the platform adjacent to the vertical entry. This platform is attached to vertical wall poles of the horizontal entry and supports shielding water and earth. When all except the person who will shut and secure the blast door are inside the shelter room, occupants should quickly begin to place bags of earth in the doorway. When the attack has begun, the whole doorway can be closed with bags of earth or other dense objects until ventilation is necessary. The entries of other types of blast shelters can be shielded in similar ways. Degree protected against fire by being built sufficiently distant from buildings and flammable vegetation and by having its exposed wood covered. For maximum expedient protection against ignition by the thermal radiation from a large explosion, all exposed wood should be free of bark, coated with wet mud or damp slaked lime, whitewash, and covered with aluminum sheet metal or foil to reflect heat. Most of the thermal radiation from an explosion that was 1 megaton or larger would reach the 50 psi overpressure range after the blast wave had arrived and had torn the expedient protective coverings from the wood. However, as has been observed in megaton nuclear weapon tests, the dust cloud first produced by the popcorning effect and later by the blast winds would screen solid wood near the ground so effectively against thermal radiation that it would not be ignited, provided it had been initially protected as described above. Precautions for occupants of blast shelters. Although a well-constructed blast shelter may be undamaged at quite high overpressure ranges, its occupants may be injured or killed as a result of rapid ground motions that move the whole shelter several inches in a few thousandths of a second. Rapid ground motions are not likely to cause serious injuries unless the shelter is in an area subjected to 30 psi or greater blast effects. To prevent possible injury, when the occupants of high-protection blast shelters are expecting attack, they should avoid degree having their heads close to the ceiling. The air slap of the air blast wave may push down the earth and an undamaged shelter much more rapidly than a person can fall. If one's head were to be only a few inches from the ceiling, a fractured skull could result. Degree leaning against a wall, because it may move very rapidly, horizontally as well as vertically. Degree sitting or standing on the floor, because ground shock may cause the whole shelter, including the floor, to rise very fast and injure persons sitting or standing on the floor. The safest thing to do is to sit or lie in a securely suspended, strong hammock or chair, or on thick foam rubber such as that of a mattress, or on a pile of small branches. In dry areas or in a dry expedient shelter, ground shock may produce choking dust. Therefore, shelter occupants should be prepared to cover their faces with towels or other cloth, or put on a mask. If an attack is expected, they should keep such protective items within easy reach. Book page 261. Copyright 2000 Nuclear War Survival Skills. Also see the New Expedient Shelter book. Requires the DJVU plugin. NWSS Contents. Cover. Addition Notes. Table of Contents Book Order Form Forward. About the Author Acknowledgements Introduction. Ch. 1. The Dangers. Ch. 2. Warnings and Ch. 3. Psychologic. Ch. 4. Evacuation. Ch. 5. Shelter. Ch. 6. Ventilation. ch. 7. Protection, ch. 8. Water, ch. 9. Food, ch. 10. Fallout raw, ch. 11. Light, ch. 12. Shelter saw, ch. 13. Surviving, ch. 14. Expedient, ch. 15. Improvised, ch. 16. Minimum PR, ch. 17. Permanent, ch. 18. Transpachi, app, Instructio, app, A.1. Door COV, app, A.2. Poll COV, app, A.3. Small Po, app, A.4. Abovegrow, app, A.5. Abovegrow, app, A.6. Above GR, app, B. How to mock, app, C. A. Homemade, app, D. Expedient, app, E. How to make a homemade piston pump app, F. Providing selected references, selected index. Graphics. Nuclear war survival skills. Mail home, app, E. How to make a homemade piston pump. How to make and use a homemade plywood double action piston pump. The need ventilating pumps, mostly centrifugal blowers capable of operating against quite high resistance to airflow, are used to force outdoor air through most high protection factor fallout shelters and through almost all permanent blast shelters. Table 1. Comparison of PLYW. Cutting out the plywood parts 1. Permanently attached T. Operating the pump 1. Top previous next. How to make and use a homemade plywood double action piston pump. The need. Ventilating pumps, mostly centrifugal blowers capable of operating against quite high resistance to airflow, are used to force outdoor air through most high protection factor fallout shelters and through almost all permanent blast shelters. Low pressure ventilating devices, including ordinary bladed fans and homemade air pumps such as caps and directional fans, cannot force enough air through a permanent shelter's usual air supply system consisting of pipes, or of pipes with a blast valve, a filter, and the valves needed to maintain a positive pressure within the shelter. Manually cranked centrifugal blowers, or blowers that can either be powered by an electric motor or be hand cranked, are the preferred means of ventilating permanent shelters from Switzerland to China. The main disadvantages of efficient centrifugal blowers are: 1. They are quite expensive. For example, in 1985 a good American hand-cranked blower, that pumps only about 50 cubic feet per minute, 50 CFM, through a shelter's pipes, blast valve and filter, retails for around $250. An excellent foreign blower that enables one man to pump somewhat larger volumes sells for about twice as much. 2. Not enough centrifugal blowers could be manufactured quickly enough to equip all shelters likely to be built during a recognized crisis threatening nuclear attack, and lasting for weeks to several months. Therefore, there is need for an efficient, manually operated, low-cost ventilating pump that 3. Can pump adequate volumes of outdoor air through shelter ventilating systems that have quite high resistances up to several inches water gauge pressure differential. 4. Will be serviceable after at least several weeks of continuous use. 5. Can be built at low cost in home workshops by many Americans, using only materials available in most towns. 6. Could be made by the millions and thousands of shops all over the U.S., for mass production during a recognized prolonged crisis, using only plywood and other widely available materials. To produce such a shelter ventilating pump, during the past 20 years I have worked intermittently designing and building several types of homemade air pumps. However, until I was traveling in China as an official guest in October 1982 and saw a wooden doubly action piston pump being used, I did not conceive or come across a design that I was able to develop into a shelter ventilating pump that meets all of the requirements outlined above. Now I have made and tested a simple homemade plywood double action piston pump, described below, that satisfies these requirements. 3 other persons have used successively improved versions of these instructions to make this model, and several others have contributed improvements. How a plywood double action piston pump works. Figure 1 pictures the box-like test model described in these instructions. Figure 1. Plywood double-action piston pump, with manometer attached for tests. Figure 2 illustrates a vertical section through a slightly improved model, and shows the 12x12 in plywood piston being pushed from right to left, causing air from the outdoors to be sucked down the open air supply duct in the top of the pump, then down to the right through the open valve in the airtight frame, that is above and near the right end of the partition, and on down into the lower pressure area behind the leftward moving piston. Because the air to the right of the leftward moving piston is at a lower pressure than the air in the shelter room, the exhaust valves in the front end, the handle end, of the pump are held closed. During this half of the pumping cycle, the higher pressure air in the part of the pump's square cylinder to the left of the leftward moving piston opens the air exhaust valves in the back end of the pump, and fresh air is forced out into the shelter room. The higher pressure air to the left of the valve in the airtight frame, that is above the left end of the partition, keeps this valve closed, while the lower pressure air to the right of this valve helps keep it closed. When the piston is pulled to the right, all of the valves shown closed are quickly opened, and all shown open are quickly closed. Then fresh air is forced into the shelter room through the opened exhaust valves in the front end of the pump. Figure 2. Vertical section of the double-action piston pump showing its square piston being pushed to the left. Book page 262. Performance tests. The volumetric and durability tests summarized below are proof that this homemade plywood double-action piston pump is better than most hand-cranked centrifugal blowers for supplying a shelter with outdoor air through typical air intake and exhaust pipes, especially when the ventilation system contains a filter and/or blast valves. The filters that give the best protection, chemical, biological, radiological (CBR) filters, have quite high resistance to airflow, as do commercial blast valves that close quickly enough to protect filters. 1. Volumetric tests. Because the rapidly pulsating airflows into and out of a piston pump are very hard to measure accurately with an air velocity meter, I made an inflatable cylindrical bag of 2 ml, 0.002-inch polyethylene film. The fully inflated volume of this bag was 256 cubic feet. The bag was suspended on a horizontal strong cord running through its length. A short tube 62 inches in circumference connected the back end of the pump, that is opposite the operator's end, to the suspended bag. Bag and pump were in a below-ground shelter that normally has essentially motionless air. See Figure 1. Since this type of pump exhausts equal volumes of air from each of its two ends, the total cubic feet per minute (CFM) that it pumps equals twice the CFM that it exhausts into the shelter from one of its ends. See Figure 1. That shows the pump attached with clamps to a small steel table and being used to pump air into the 256 cubic foot suspended bag. I measured the pressure differences against which the pump was operated. In a shelter, these differences typically are caused by the resistance to airflow in pipes, valves, and a filter. I measured pressure differences in inches water gauge, 1 in W. G. 0.036 psi, with the small tube manometer attached to the side of the pump. To produce various pressure differences for several tests, I nailed a piece of plywood over the top of the air intake duct, so as to produce different sized openings. In most tests I placed different layers of filter materials in a filter box that was fitted airtight over the 6x6 in air supply duct on the top of the pump. See Figure 3. This low-resistance filter removes practically all fallout particles of wartime concern, and also most infective aerosols that may be used in biological warfare. C. Making and Using a Homemade Filter Box and Filter, by Cresson Kearny, October 1985. Figure 3. Pump with homemade filter, 20x 8 inches inside dimensions, connected airtight on top of the pump's 6x6-inch air intake duct. The best centrifugal blowers that I have seen or heard about are those manufactured by a Finnish company, Temet Oy. I cranked a Temet Oy blower in an Israeli shelter used for testing ventilation equipment. The Finnish centrifugal blower was better than Swiss, German and captured Russian blowers also undergoing tests. Therefore, in Table 1 a few of the volumetric tests of my best model plywood double-action piston pump, powered by 1 and 2 men, are compared with performance data furnished by Temet Oy for its centrifugal blower when cranked by 2 men. I have converted Temet Oy's metric units into the common American units. In Table 1, the pressure difference of 4.3 inches water gauge is the resistance to airflow that Temet Oy realistically gives is typical of a well-designed shelter ventilation system of pipes, valves and blower plus a chemical biological radiological CBR filter. Temet Oy gives 2.0 inches water gauge is typical of the same ventilation system with only a low-resistance dust filter. The much larger volume pumped by the double-action piston pump when a CBR filter is used, as compared to the CFM pumped by this very good centrifugal blower, is typical of the reduced effectiveness of even the best centrifugal blowers at high pressure differences. In areas devastated by a nuclear explosion, the typical very dusty conditions are likely to result in filters soon becoming dirty and higher in resistance to airflow. Then the greater effectiveness of a piston pump for ventilating a shelter with a high-resistance air supply system will be even more important than when its filter is clean. Top previous next. Table 1. Comparison of plywood double-action piston pump with Temet Oy centrifugal blower. Type of pump pres. Diff. In. W. G. Cubic feet per minute horsepower. Double action. Piston pump. 1 man 4.9 134. 2 men 4.3 182. Temet Oy. Centrifugal blower. 2 men 4.390 0.15 double action. Piston pump. 1 man 2. 3172. 2 men 2. 3208. Temet Oy. Centrifugal blower. 2 men 2300 0.18. The horsepower requirements of my pump have not yet been measured. However, based on the calculated air pressure on the 12x12 in piston of 22.3 pounds, when the pressure difference was 4.3 in W. G. 0.155 psi, when two pumpers were making 52 strokes, cycles, per minute while pumping 182 cfm, the horsepower delivered was about 0.14 HP without allowing for friction and the losses of power due to reversals in the directions of piston movements. I estimate that the actual horsepower delivered by the two pumpers, a 69-year-old with a stiff back in 1983, and a 15-year-old boy, was somewhat less than 0.2 HP. A man in good condition can work for hours delivering 0.1 HP. When comparing machines powered by human muscles, what muscles are used and how they are used are often as important as are the horsepower requirements. Leg muscles are more efficient and are much stronger than arm muscles. Arm muscles are used much more in cranking a blower than in pushing and pulling the piston of a properly designed reciprocating piston pump back and forth horizontally. See Figure 3. If this double-action piston pump is placed at a height above the floor so that its handle is approximately at the height of a standing operator's elbows, then the operator can do most of the work with his legs. See Figure 3. He efficiently moves his body back and forth for over a foot, while moving his hands and forearms horizontally for slightly less than a foot relative to his body. To deliver the same horsepower by cranking a blower uses less efficient muscles inefficiently, and is much more tiring. As shown in Table 2, the volumetric efficiency of my best model is good for a shelter ventilating pump. The volumetric efficiency of a piston pump, a positive displacement pump, is found by dividing the CFM actually pumped by the theoretical maximum CFM at the same pumping rate and the same pressure difference, assuming all piston strokes are full length, that all valves open and close instantaneously, and that there is no leakage. Table 2 shows that the greater the pressure difference, the lower the efficiency as one would expect, because of increased leakage. Pres. Diff. In. W. G. Strokes per minute. CFM efficiency. 436,122, 84.0% to 645,160, 89.0% 0. 751,188, 92.0% 0. 454,202, 94.0% 0. 255,208, 94.5%. Table 2. Volumetric efficiencies of double-action piston pump operated by one man. Book page 263. 2. Durability tests. Finding a home-makeable method to seal the moving piston so as to assure at least 1 month of continuous efficient pumping was the most difficult problem. Various rubber seals attached to the edges of the piston were unsatisfactory, and aluminum sheet metal strips, shaped and attached like the galvanized steel sheet metal strips used in this model, wore out in less than a week, even when oiled every 24 hours. To save money during weeks of continuous durability testing, the pump was operated by an electric motor that powered a pulley drive that turned a 2-foot diameter pulley having an attached 40-in. long steel pitman with a hinged connection to a horizontally sliding bar connected to the handle of the pump's wooden piston rod. See Figure 4. After pumping for 380 hours, 15.83 days, at 44 strokes per minute against a pressure difference of 2.3 in G, the worst worn spot on any of the 30-gauge steel sheet metal sealing strips on the piston was reduced in thickness from its original 0.0155 in to 0.0145 in. This worst spot wear of 0.001 in is only about a 6% reduction in thickness. The flap valves functioned as well as when new, and appeared unworn. I conclude that this pump would be serviceable after several months of continuous use provided it is lubricated after every 24 hours of actual use, as in this durability test. In this test I lubricated the piston, its cylinders, 4 walls, and its rod with lubriplate Na. 105, the original white-o grease. This non-sticky, grease-type lubricant is used extensively, especially to lubricate internal combustion engines before first starting up. Another builder of this model pump found Silu White Lube, an all-purpose lithium grease, the best of the lubricants that he tested. Judging from my prior durability tests, a very light oil applied daily serves reasonably well. Ordinary bearing grease is unsatisfactory. Materials. The following materials, that cost about $65. Retail in 1985, are needed to make and operate the best model of this pump. Plywood, 3/4 in. Exterior, 1/4x8 featuring sheet finished on one side, unwarped. Plywood, 3/8 in. Exterior, 1/4 of a 4x8 featuring sheet finished on one side, unwarped. Second choice, 1/4 in. Exterior plywood. Oak board, 3/4 x 1-3/4 in. Straight, well seasoned, 4 feet long, to make the piston rod. If oak or other very strong wood is not available, use a straight fir or pine board. Fir or pine board, about 3/4 x 1-3/4 in. 8 feet long, to make the piston rod handle, etc. 28-gauge or lighter galvanized steel flashing, sold by lumber yards for roofers, no thicker than 0.016 in. Or galvanized steel or flashing no thinner than 0.012 in. Or 30-gauge galvanized steel sheet metal available in some sheet metal shops. Sheet metal thicker than 0.016 is not springy enough for making this pump's near equivalent of piston rings. Best to go to a sheet metal shop and have 3 strips cut, each 3 in wide and about 30 in long. Screws, round-headed, zinc-plated wood screws. 22 each of number 12, 2 in long, 12 32 in dia, with flat washers 10 each of number 10, 1-1/2 in long, with flat washers. 15 each of number 6, 3/4 in long, with flat washers. Nails, 4 penny, 1-1/2 in. Best cement coated, 1/4 lb. Nails, 3 penny, 1-1/4 in smiley face, galvanized, 1/4 lb. Staples, if an oak board for the piston rod is not available, number 17, 3/4 in. Galvanized, 1/4 lb. Tacks, number 6 upholstery, 1/2 in. Long, a small container. Tacks, number 3 upholstery, 3/8 in. Long, a small container. Felt, weather stripping, 5/8 high. Wide, 10 feet. Tape, silver duct tape, 2 in. Wide, a small roll. Tape, masking tape, 3/4 in. Wide, a small roll. Adhesive, waterproof, liquid nails, or other all-purpose construction adhesive, 1 approximately 11 Oz. Tube, for use in caulking gun. Epoxy, 5-minute, 2 tubes. Rubber cement, a small tube. Sealer, such as polyurethane clear finish, To reduce absorption of oil or other lubricant of the cylinder, 1/2 pint. Plastic film, transparent storm window type, such as 4 mil flexoglass, by Warp Bros. 3 square. Fort. Grease-type lubricant, an all-purpose motor brake and lithium grease such as Silu White Lube, or Lubriplate No. 5 space-age lubricant, 2 approximately 10 ounces. Tubes. Inner tube rubber, heavy truck or auto, cut from an old tube, 1 square. Fort. Functional relations of parts. Look at Figs. 2, 5, and 6. In Figs. Sand 6, the lower, fixed part of the front end is pictured below the piston rod. The piston rod slides back and forth on the center of the fixed part of the front end, as indicated more clearly in Figure 7, and in the notch in the removable part of the front end. Figure 4. Mechanized drive used in weeks-long durability tests. Figure 5. Front end of the durability test pump, showing the lower fixed part below piston rod, and the upper removable part, that is held by 6 screws with flat washers. Felt weather stripping makes the removable part airtight. Book page 264. Figure 6. Pump built by Dale Huber, of Lake City, Florida in his home workshop, while guided only by the second draft of these repeatedly improved instructions. The removable part of the front end has been taken off, to insert the piston into the 12x12 in cylinder, under the partition. The plastic flaps of this pump's flap valves are black. Transparent plastic film is preferred. Note that a single plastic film flap covers each pair of 2x4 in valve holes, and that, as shown in Figure 2, that gives a side view of all 6 flaps. All flaps open away from the vertical center plane of the pump. In Figure 5, the removable upper part of the front end is shown in place, secured by 6 round head screws with flat washers. In Figure 7, note the pair of 2x4 in flap valve holes above the piston rod. In Figure 6, the removable part of the front end has been removed, exposing the 26 in long, horizontal partition that serves as the top of the 12x12 in cylinder, in which the piston can make a 24 in maximum length stroke. Also see Figs 2 and 7. Figure 6 also shows the piston while it is being removed and one of the 2 rubber bumpers, made of inner tube rubber, on its piston rod. The back end of the box is made of one piece of plywood, as shown in Figure 8. The 2 plastic flaps of its exhaust valves each cover 2 2x4 in valve holes, that are positioned the same as the 4 valve holes in the front end. Figure 7. Front end, operator's end, of plywood double-action piston pump. The 2 4x12 in valve frames are shown by dashed lines, as is the 12x26 in partition. T-owned the same as the 4 valve holes in the front end. Figure 8. Back end. Only the plywood is shown. Book page 265. Top previous next. Cutting out the plywood parts. 1. The 4 parts of the cylinder, its bottom, 2 sides, and the partition, see Figure 7, should be made with the wood grain of the plywood running in the same direction as the lengths of these parts. This reduces piston friction. 2. Outline on a sheet of exterior 3/4 in plywood all of the plywood parts except for the 12x12 in piston and the 2 12x12 in construction forms, which are made of 3/8 in exterior plywood. If 3/8 in plywood is not available, use 1/4 in. Do not assume that the corners of a sheet of plywood are truly square. Also check the width of the socket of the saw to be used, and allow for this width when drawing adjacent outlines of parts on the plywood. Be sure to make all corners square. 3. If you do not have a table saw that saws accurately, or a heavy-duty saber saw, you will do well to pay a professional carpenter or cabinet maker to saw out the plywood parts and also the piston rod if you are making it out of an oak board. A professional can accurately saw out all of the plywood parts and the 10 valve holes in about 2 hours, provided you have accurately outlined all saw lines. 4. Make the following plywood rectangles with tolerances of plus or 1/32 in partition, 12x26 in 2 sides, each 16-3/4 x 32 in. If your 3/4 in plywood actually is less than 11/16 in thick. Make the height of each of your sides 16 minus 3/4 in. Less the difference between 3/4 in and the actual thickness of your plywood. See Fig. 7. Bottom, 17 minus 1/2 x 32 in. Top, 13 minus 1/2 x 32 in. 2 valve frames, each 4 x 12 in. Piston, 12 x 12 in. Of 3/8 in. Plywood. 2 construction forms, each 12 x 12 in. Of 3/8 in. Plywood. 5. Make the following plywood rectangles with tolerances of plus or 1/16 in. Back end, 13 minus 1/2 x 17 minus 1/4 in. See Figure 8. Removable upper part of front end, 13 minus 1/2 x 10 minus 7/8 in. See Figs. 7 and 9. Fixed lower part of front end, 13 minus 1/2 x 6 minus 3/8 in. See Figs. 7 and 10. The 4 parts of the air intake duct, 2 each 6 minus 1/2 x 6 in. 2 each 6 minus 1/2 x 7 minus 1/2 in. 2 spacers to be nailed to the bottom, each 3/4 by 3/4 x 32 in. 6. Saw out the 10 valve holes. A tolerance of plus or 1/8 in. Is good enough. See Figs. 7, 8, 9, and 10. 7. Saw a square 6x6 in. Hole in the center of the top, as shown in Figure 2 if you are going to install the homemade filter, described in separate instructions, directly on top of your pump. To connect your pump to a round air intake pipe, cut an appropriate round hole in the top. 8. Sandpaper the finished sides of the partition, the 2 sides, and the bottom, to reduce friction on the reciprocating piston. Use fine sandpaper. 9. Make and attach the 6 valve flaps, to complete the flap valves, that are the lowest resistance, quickest acting type tested. A. Make a 3 minus 3/4 x 5 minus 3/4 in. Cardboard template, using carbon paper to transfer lines of Figure 11 to cardboard. See Figure 11 on page 7, and note that this template outlines the right half of the 3 minus 3/4 x 11 minus 1/2 in. Plastic film flap. Also transfer the dashed tack line and mark the ends of the 4 horizontal stop string lines. Drill 8 small holes through the cardboard at the ends of the 4 stop string lines, so that you can use a pencil to mark these points on plywood. Figure 9. Removable part of front end, unfinished. Only the plywood is shown. Figure 10. Fixed part of front end, unfinished. Only the plywood is shown. B. Use your template to mark around the 2x4 in. Valve holes in plywood parts. 1. The positions of the ends of each hole's H stop strings. 2. The right side edge and the bottom edge of each flap after it is attached. And 3. The tack lines. C. Drill a 1/16 in. Diameter hole through the plywood at each point marked for an end of a stop string. D. With nylon kite string, or other nylon string about 1/16 in diameter, such as 50 lb test nylon fishing line, and a big enough needle, string the 4 stop strings across each 2x4 in hole. Use a string long enough to make 4 uncut stop strings. Start on the unfinished back side of the plywood, on the opposite side from the future valve flap. To secure the starting end, wrap the string around a half-driven tack, and then drive it in. Keep pulling the string tight as you thread it through the holes and as you wrap its finishing end around a half-driven tack. Finally, epoxy the string in all of the holes, on the back side of the plywood. An equally strong nylon string can be made by twisting together 4 pieces of waxed nylon dental floss. Stop strings also can be positioned by using number 3 upholstery tacks in place of the 1/16 in diameter holes. Drive a tack partly in, wind the string around it while pulling the string tight, and drive the tack completely in, to hold the string securely. Finally, coat the tack heads and the adjacent plywood with a smooth covering of adhesive, to provide a smooth seat for the valve flap. E. Cut out 6 plastic flaps of transparent 4 mil plastic film, each 3 minus 3/4 x 11 minus 1/2 in. The easiest way to accurately cut a flap of thin plastic film is to make a cardboard template 3 minus 3/4 x 11 minus 1/2 in. Place it on the film, and cut around it with a very sharp knife. F. In preparation for attaching a flap over each pair of 2x4 in valve holes, cover the plywood above each pair of holes with masking tape, up to the straight tack line that you already have drawn 1/2 in. Above each hole, use your cardboard template. The masking tape will prevent the adhesive that will be used to attach each valve flap from being applied too near the 2x4 in holes, where adhesive would keep a flap from opening fully. G. Position each of the 6 flaps properly, in its closed position, with its lower edge on the line that you already have used the template to draw 3/4 in. Below each flap's pair of 2x4 in holes, position its right side edge on the line already drawn 1 in. From the right side of the right hole of each pair of 2x4 in holes. Then put masking tape over the lower edge of each flap and the adjacent plywood, to hold the flap temporarily, in its closed position. H. Gently fold down the upper part of each flap, so that the plywood above its pair of 2x4 in holes is uncovered, except where you have placed the protective tape, and place small pieces of masking tape so as to hold each flap temporarily in this folded down position. I. Quickly apply a thin coat of all-purpose construction adhesive, such as liquid nails, to a 1/2 in wide plywood area above the protective masking tape that covers the plywood up to the tack line, 1/2 in above each pair of 2x4 in valve holes. Then promptly detach the small pieces of masking tape holding the flap in its folded down position, and turn the flap, the lower part of which is still being held in its proper closed position by masking tape, into the whole flap's closed position. Press the upper part firmly against the approximately 1/2 inch wide coating of adhesive, to secure the valve in its proper closed position. Allow several hours for the adhesive to harden before removing the tape and using the valve. J. Drive small tacks, number 3/3/8 in on the tack line. See template to make sure the flap stays securely attached after long use. Very small tacks are easily driven if held with tweezers or needle-nosed pliers. Book page 266. Putting the pump box together. 1. The following procedure is the best tested construction method for persons who lack experience in putting parts together so that all corners are exactly square, or who do not have the big clamps and other gluing equipment used by cabinet makers. This procedure is best carried out by 2 persons working together. 2. On the finished side of the top, draw 2 parallel lines exactly 12 in apart and parallel to the top's 32 in long edges. Each of these lines will be 3/4 in from an edge. Also draw a line 6 in from and parallel to each end of the top, to mark the positions of the 2 valve frames. See Figure 2. 3. Build the pump's box upside down. Start by placing its top on the floor, as indicated by Figure 12. Figure 12. Parts of the pump box, with dimensions in inches. The Roman numbers give the best tested order for attaching these parts to each other. 4. Attach the 2 valve frames 2 and 3 to the top eye with construction adhesive, positioning each of them 6 in from an end of the top eye. Make sure that each frame's flap valve is upside down and facing away from the center of the pump. Remove any adhesive that is on the top beyond the ends of the valve frames. When using construction adhesive to make this pump, it is best to apply a rather thin coat to only one of the 2 plywood surfaces to be joined. Then promptly rub one plywood part slightly back and forth against the other, while pressing them together, thus making sure that both surfaces are coated and in close contact. Wait until the adhesive sets and bonds adequately before attaching more parts. 5. Draw 2 parallel lines on the unfinished side of the partition, each 3 inches from one of its ends. Adhere the 2 12 in long unattached edges of the valve frames to the partition on these 2 lines, as illustrated by Figs. 2, 7 and 12. Allow time for the adhesive to set. 6. Before permanently attaching side B, position it vertically with a long edge resting on the top, and with a side edge of the partition and ends of the 2 valve frames I and 2 in contact with the finished side of side B. See Fig. 7. On the unfinished outer side of side B, draw lines showing the positions of the partition and of the 2 valve frames in contact with the finished side of side B. 7. Preparatory to attaching side B to the partition and to the 2 valve frames, drill 4 slightly oversized screw holes for your 2 in. Round head screws through side V. Drill these holes so that a screw will go into an end of each valve frame about 1 in from its adhered edge, and the other 2 screws will go into the side edge of the partition, at points above the valve frames. Next, with side V temporarily in its final position, drill with a smaller diameter drill through the 4 holes in side V, into the partition and into the 2 valve frames. Then with the 4 screws temporarily connect side V, the partition, and the 2 valve frames, and, while checking with a carpenter's square the squareness of the angle between the partition and side V, adjust the 2 pairs of screws to attain squareness, remove side V. 8. Apply adhesive to the 3/4 in wide area along the long edge of the top, and if necessary a thicker coating of adhesive than normal to unattached edges of the partition and of the 2 valve frames. Then promptly position side V, and by again screwing in and adjusting the 4 screws, make the angle between the partition and side V square. Allow the adhesive to set. 9. Use short pieces of duct tape to temporarily attach the 2 12x12 in construction forms to the partition and to side V. Before using these forms, drive 4 small nails into each form, near its corners, to serve as handles for removing them from the completed cylinder. Attach a construction form near each end of the partition. 10. Adhere the finished side of side V to the top, to the unattached side edge of the partition, and to end edges of the valve frames, while keeping side V pressed against the 2 square construction forms. To keep side V pressed against the construction forms until the adhesive sets, use small nails to temporarily nail 2 small boards horizontally across the ends of the sides, at each end of the box. 11. On the finished side of the bottom X, draw 2 parallel lines 131/2 in apart, making each line 6-3/4 in from the center line of the bottom, as shown in Fig. 7. Nail the 2 3/4 by 3/4 x 32 in spacer boards 7 and 8 to the bottom, 13-1/2 in apart. 12. To attach the bottom, first place it with its finished side down, on the exposed long edges of the sides. If you find that the bottom rests on the construction forms and is not in contact with the long edges of the sides, in effect increase the heights of the sides by coating with adhesive both the edges of the sides and the 3/4 in wide area of the bottom to which the sides will be adhered, then adhere the bottom onto the edges of the sides. Before the adhesive hardens, remove any that has been squeezed into the corner of the cylinder. Book page 268. Top previous next. Permanently attach the fixed part of the front end X, see Figure 7, 10 and 12 with adhesive and small nails to the sides and to the bottom. Be sure that its flap valve is upside down and is facing away from the center of the pump, and that a long edge of this part is level with the outer side of the bottom. Remove the construction forms. 14. Paint the interior of the cylinder with sealer after removing all adhesive that may be in its corners. 15. After the sealer dries, sandpaper the interior of the cylinder with fine sandpaper, and paint it again with the final coat of sealer. 16. To attach the removable part of the front end 11, stand the box on its completely open end and drill slightly oversized screw holes for your 2 in screws clear through the removable part of the front end, as indicated by Figure 9. With the flap valve facing outward, temporarily attach this part with a few small nails to the end of the top and to ends of the 2 sides. Then with a smaller diameter bit, drill the screw holes deep enough into the top and the sides so that the 7 screws will hold securely. 17. So that it will be unnecessary to tightly screw on the removable part of the front end in order to make its repeated temporary attachments airtight, tack felt weather stripping best 1/8 in thick and 5/8 in wide, or strips made of 2 thicknesses of flannel, to the contact edges of the top and the sides. Number 3, 3/8 in carpet tacks serve well. Then with a razor blade carefully cut the felt covering the screw holes in the edges, and remove these small pieces of covering felt. 18. Attach with screws the removable part of the front end. 19. To prevent damage to the front end valve flaps when you stand the pump on its front end, epoxy a small piece of 3/8 in plywood to the front end, near each of its 4 corners, as pictured in Figs 3 and 5. Before standing the pump on its front end, use small pieces of masking tape to temporarily secure its valve flaps in their closed positions. 20. Attach the back end 12, using only screws. See Figure 8. For repairs, the back end may have to be removed. To make the attachment of the back end airtight, coat its attachment, crack, only with rubber cement. Making the piston rod, and its handle. 1. Have a sheet metal shop cut 3/3 featuring long, 3 in, wide strips of galvanized steel sheet metal that is no more than 0.016 in, thick and no less than 0.012 in thick. Most galvanized steel valley flashing used by roofers and sold by many lumber yards is less than 0.016 in thick. 30-gauge galvanized sheet metal sold by some sheet metal shops is about 0.015 in thick. Steel sheet metal thicker than about 0.016 in is not springy enough and is unsatisfactory. 2. With a tolerance of plus or 1/32 in, cut from these strips 2 strips each 11-13/16 in long, and 2 strips each 11-3/4 in long. These 4 strips first must be bent and then tacked to the 4 sides of the plywood piston. These piston sealing strips serve rather like piston rings, by making close, sliding, low friction contact with the sides of the plywood cylinder. Steel strips resist wear and if properly lubricated make the pump serviceable for months of continuous use. 3. Preparing the 4 sheet metal sealing strips. A. Since the strips to be tacked to the top and the bottom of the piston must be bent differently from the strips to be tacked to its 2 sides, mark T or B on each of the 2 strips that are 11-13/16 in long, and mark 8 on each of the 2 strips that are 11-3/4 in long. B. On each of the 2 strips marked T or B, draw an ink line along which to make the approximately 30-degree bend, and another line for the approximately 90-degree bend. See the left half of Figure 13 for the distances from the edges of these 2 T or B strips to their bends. Also draw 2 ink lines along which to drive tacks, spaced as shown in the left half of Figure 13. Likewise draw 4 lines on each of the 2 strips marked 8, as specified in the right half of Figure 13, noting that some of these lines are spaced differently than corresponding lines on the strips marked T or B. C. Using a small sharpened nail for a punch and placing 1 strip of sheet metal at a time on a smooth board, punch 2 rows of tack holes in each strip. The tack holes should be about 1-1/2 in apart. D. From a nominal 1x2 in straight board, make 2 boards each about 3/4 by 7/8 x 12-1/4 in, for use in bending the sealing strips. E. Securely sandwich a T or B strip of sheet metal between the 2 12-1/4 in long boards placed exactly on top of each other, by tightening 2 C clamps on the ends of the 2 boards, so that the bending line 3/8 in from one side of the strip is just visible along the straight edge of a board. Then hold the 2 clamped boards in a vise so that the 3/8 in wide part of the sheet metal strip is uppermost and vertical. F. Bend the exposed part of the strip about 30 degrees off the vertical, away from the side of the strip where the holes have been indented by the punch. To bend evenly, hammer gently and repeatedly on a 3/4 by 3/4 x 18 in board held against the exposed 3/8 in wide part of the strip. Figure 13. Piston sealing strips, each made of a springy sheet metal strip 3 in wide. G. With the sheet metal strip held sandwiched between the 2 12-1/4 in long boards by the 2 C clamps and the vise, so that the bending line for the almost 90-degree bend is barely visible, bend the exposed part of the strip 90 degrees, in the same direction that the 3/8 in wide part was bent. See Figs 13 and 14. H. Bend the other T or B strip, and similarly bend each of the 2 8 strips. 4. Attach the 4 sheet metal sealing strips to the plywood piston with number 6 tacks 1/2 in long. Place on a solid metal surface the part of the plywood piston opposite the spot to which part of a strip is being tacked, so that when a tack is hammered in its point is clinched bent over, on the far side of the 3/8 in Thick plywood piston, by being hammered against the solid metal surface. A. First tack A, T or B, sheet metal strip to the top of the piston, and A, T or B, strip to its bottom. B. Then tack the 2, 8, strips to its sides. The strips should fit together so as to make square corners. If adjacent ends of 2 strips do not fit neatly together, cut bit by bit a very little off the ends of a strip so that the 2 adjacent ends fit together neatly at their C. To prevent air leakage between the ends of the ceiling strips, put rubber cement in the 4 corner cracks between strips. This was not done on the test pump's piston. Figure 14. Plywood piston with sheet metal ceiling strips attached. Book page 269. 5. For the piston rod, saw from a straight, well-seasoned oak board a 3/4 x 1-3/4 x 36-1/2 in. Board. Sandpaper it smooth. A piston rod made of well-seasoned oak is less likely to break if abused, but necessitates using screws, in place of nails and staples, for attachments. Piston rods made of nominal 1x2 in. Fir boards were undamaged in the tests. 6. To complete the piston rod. A. For the handle, use 4 pieces of a nominal 1x2 in. Board cut to the lengths shown in Figure 15. Also see Figure 16. Round all edges and corners, to minimize the chances of the operators blistering their hands. B. Paint the piston rod and its handle with sealer. When dry, sandpaper. Then apply a final coat of sealer. C. Use adhesive, screws, and nails, or adhesive and nails if your piston rod is of soft wood, in making the handle illustrated by Figure 15. Figure 15. Piston rod handle made of 3/4 x 1-3/4 in. Boards. Figure 16. The pump handle of the durability test pump, showing how one man best holds it when 2 men are pumping. D. To reduce friction on the piston rod and resultant enlargement of the piston rod hole with long use, coat with epoxy all 4 sides of the piston rod hole. See Figs 7 and 16. Be sure that the piston rod slides snugly yet freely in its hole when the removable part of the front end is screwed in place. E. From a piece of thick truck tire inner tube rubber, cut a 2-in wide strip 12 in long. To make the 2-in wide rubber bumper, see Figs 15 and 16. Connect one end of this rubber strip to the center of a 3/4 in wide side of the piston rod. Do not place any screw or staple in the strip closer than 1 in from the strip's forward edge, that may repeatedly bump into the front end. Wrap and attach the strip quite tightly around the piston rod next to the handle. If you have only a piece of passenger car inner tube rubber, then to make a 2-in wide bumper use a 4-in wide strip of this thinner rubber folded double lengthwise. 7. Attaching the piston rod to the piston. A. On the back of the 12x12-in plywood piston, mark lines to enable you to attach the piston rod as pictured in Figure 14. Note that the lower side of the piston rod is exactly 5-1/2 in above the lower edge of the plywood of the piston, and that the center line of the piston rod intersects the vertical center line of the plywood of the piston. B. To the end of the piston rod, see Figure 14, adhere and screw, or adhere and nail if your piston rod is not oak, 2 pieces of nominal 1x2 in boards each 3 in long. Each of these 2 small boards and the end of the piston rod are in contact with and securely connected to the plywood piston, and form a perfect T at the end of the piston rod. C. Connect the piston rod to the piston, best with epoxy, or adhesive, and small screws. Make sure that 1. The 4 piston sealing strips overlap the piston's plywood in the direction of the piston rod. 2. The 1-3/4 in wide sides of the piston rod are parallel to the top and bottom of the piston, and 3. The piston rod is perpendicular to the piston. See Figs 2 and 14. D. Make and attach to the piston rod a 3-in long rubber bumper, positioned close to the piston as shown in Figure 2. Top previous next. Operating the pump. 1. Check to see that the 4 sheet metal strips on the 4 sides of the piston all make even contact with the walls of the cylinder when the piston is moved back and forth. If the piston does not slide back and forth quite easily even when not lubricated, carefully bend a strip or strips so that they press less against the Cylinder, walls. If while someone is shining a flashlight through a valve opening in the other end of the pump you observe that parts of a sheet metal strip do not make close contact with a cylinder, wall, gently bend outward that part of the strip. 2. Lubricate all four walls of the cylinder, the sheet metal strips that slide against the walls, and the piston rod. Use a very thin motor brake and white lithium grease, not an ordinary bearing grease, that is too sticky. Or use a thin oil. The pump should be lubricated after no more than each 24 hours of use, and before being used again after days of disuse. 3. Install the pump at a height above the floor so that most of the persons who are going to pump can push and pull with their hands moving at about the same height that their elbows are when they are standing. See Figure 3 for an example of a pump supporting table raised to an efficient height for operators who are the height of the pumper pictured. 4. To save work and to minimize wear on the pump, usually operate it with a length of stroke a little shorter than the distance between its two rubber bumpers. To save energy, especially when pumping air through a high-resistance ventilation system, move the piston back and forth by using mostly your leg and body muscles. Prolonged storage. Wipe off all grease and other lubricants if you do not plan to use this pump for months. All lubricants, especially those on wood, tend to become gummy with time. Keep your supply of pump lubricants taped to your pump. Request. Suggestions for improving this pump and/or these instructions will be appreciated, and may contribute to improvements likely to save lives. Cresson Kearny. Copyright 1986 by Cresson Kearny. No part of this work, except brief passages that a reviewer may quote in a review, may be reproduced in any form unless the reproduction includes the following statement. Copyright 1986 by Cresson Kearny. All or part of this information on the plywood double-action piston pump may be reproduced without obtaining permission from anyone. Book page 270. Filter box and filter. Purposes. The primary shelter ventilation requirement is to supply enough outdoor air to maintain endurable heat-humidity conditions. To keep the concentration of respiratory carbon dioxide low enough for survival, very little fresh outdoor air is required. Even for an infant or an infirm person remaining in a crowded shelter for days, 3 cubic feet per minute, 3 cfm, is adequate. For a healthy adult or child, 1.5 cfm is enough. Too much carbon dioxide, not too little oxygen, is the initial cause of unendurable conditions in inadequately ventilated shelters in which the air does not get unendurably hot. In contrast, up to 25 cfm of outdoor air per occupant may be needed to maintain endurable heat-humidity conditions inside a crowded shelter occupied for days during a heat wave in a hot, humid part of the U.S. Hence the need for a large volume ventilating pump, best with a low-resistance filter. If outdoor air flows into a shelter through a hood, gooseneck pipe, or other air supply opening that causes all but tiny fallout particles to fall out before the air reaches shelter occupants, breathing this unfiltered air will not result in short-term radiation casualties. However, a very small fraction of the occupants of a shelter supplied with unfiltered air in an area of heavy fallout may contract cancer years later as a result of breathing shelter air containing tiny fallout particles that a properly designed filter could have removed. Air that has been in contact with fallout particles before being filtered is not radioactive. The homemade filter illustrated below, if used with an efficient suction pump such as the plywood double-action piston pump described separately, will remove practically all fallout particles likely to cause casualties even decades later. This filter also will remove most infective aerosols, the airborne tiny particles used in biological warfare, an unlikely type of attack on the United States. It will not remove poisonous gases, and even less likely danger to Americans if all-out war befalls us. Construction filter box. If 20x 20-inch furnace filters are available, use plywood or boards to build the filter box shown in the illustration. To make permanent connections airtight, first use waterproof construction adhesive or glue, and then tape. If only smaller filters are available, reduce the horizontal dimensions of the box accordingly, except for the top and bottom openings. Check to be sure that your filters will fit snugly in the box of the size you plan to build. The square frame on the bottom of the filter box should fit snugly over the square air intake duct on the top of your plywood double-action piston pump. Tape the cracks to make the connection airtight and to permit easy removal of the filter box. Make the illustrated four supports of the hardware cloth no thicker than 3/4 inch, thus providing enough space below the filter for low resistance airflow. Hardware cloth is a stiff, square mesh, molten-dipped galvanized wire. Make the square top of the filter box so that it covers the upper edges of the box's sides and can be easily removed. Then cut in its center a round hole slightly smaller than 4 inches in diameter. File the hole's edges so that a 4-inch diameter can, such as a coffee can with its top and bottom cut out, fits snugly in this hole. To connect the can securely and airtight, first use waterproof construction adhesive or epoxy, and then tape. If construction adhesive or epoxy is not available, cut a 2-1/2 inch diameter hole in the center of the bottom of the 4-inch diameter can. Then make radial cuts spaced about 1/2 inch apart, out to the full diameter of the can. Bend these tabs outward 180 degrees, preparatory to tacking them with small tacks to the bottom of the filter box top. Tape airtight. So that the top of the filter box can be easily removed, tape it onto its box. A roll of duct tape should be kept with the filter box and pump at all times. To connect the filter box to the shelter's air intake pipe, the best widely available air duct is the inexpensive, 4-inch diameter flexible duct used with clothes dryers. Figure P.270 homemade filter to fit on plywood double-action piston pump, and to be connected to a 4-inch diameter air intake pipe. Book page 271. Filter materials. Furnace or air conditioner dust filters, those made of oiled fiberglass fibers, will remove practically all but the very smallest fallout particles. Filters that are sold in box-like housings can easily be installed so that all the pumped air will pass through them, by taping them to the inner sides of the filter box. The illustration shows 2 plain mats of furnace filter material, each taped around its edges. If commercial dust filters are not available, bath towel cloth will serve. However, in very dusty areas a cloth filter may become overloaded, thus seriously reducing the rate of airflow much sooner than if an oiled fiber filter is used as a pre-filter. To filter out most of the tiny particles that may pass through one or more furnace filters, place 2 thicknesses of bath towel on top of the filter support made of hardware cloth, and tape them around their edges to the box. See illustration. Tests by U.S. Army specialists have shown that filtering air through 2 thicknesses of bath towel removes about 85% of even microscopic aerosols as small as 1 to 5 microns in diameter. C. Emergency Respiratory Protection Against Radiological and Biological Aerosols, by 2. G. Guyton et al. AMA Archives of Industrial Health, Volume 20, July through December 1959. This is the size of most infective aerosols used in biological warfare. In most of an area subjected to a biological attack, if 85% of this size range of infective aerosols and practically all larger particles are removed, then most persons breathing this filtered air will not receive enough infective agents to infect and sicken them. Persons who are especially desirous of protecting their shelter's occupants against biological warfare aerosols, but who cannot afford or obtain expensive high-efficiency particulate air filters, HEPA filters, should consider using disposable pleated air filters that meet official ASHRAE standards. 1-2 in. Pleated air filter, measuring 19-1/2 x 19-1/2 in, will remove over 90% of particles in the 1.0-5.0 micron range, yet when clean its resistance to an airflow of 200 cfm is only about 0.2 in. Water gauge, about 0.007 psi. Its cost is about twice that of a good ordinary furnace filter of the same size. However, it has approximately 3 times the life of a standard panel-type filter before becoming overloaded. Disposable pleated air filters are available in larger cities. Use. The illustrated homemade filter has such low resistance to airflow that, when up to about 200 cfm is being pumped through it by a plywood double-action piston pump, the air volume is decreased by only about 10%, as compared to the volume pumped with no filter in the ventilation system. With a homemade plywood double-action piston pump, up to approximately 200 cfm can be pumped through this filter even when the total difference in air pressure, caused by the ventilation pipes, a dirty filter, etc., that restrict airflow, is high, about 5 inches water gauge, 0.18 psi. Even if the United States suffers an all-out Soviet attack, only a small part of its area will be subjected to blast effects severe enough to injure the occupants of fallout shelters. Fallout shelters are not designed to withstand blast, but especially typical earth-covered ones afford consequential blast protection. In contrast, an installed filter, unless protected by an efficient blast valve, will be wrecked by a quite low-pressure blast wave that comes down its open-air intake pipe, even if the small part of the blast wave that would enter the shelter room through its open ventilation pipes is not nearly powerful enough to injure the shelter occupants. Thus, unprotected installed filters will be wrecked in an area several times as large as the area in which occupants of fallout shelters will be injured by blast. To be sure of having a filter in good condition, you can 1. Make and keep in your shelter an extra complete filter, ready to replace your installed filter if it is damaged, or if it becomes overloaded with dust and its resistance to airflow becomes too high. Furthermore, if your filter is installed in your shelter room and becomes so radioactive with retained fallout particles that it is delivering a consequential radiation dose to shelter occupants, it is advantageous to be able to remove it, pitch it out, and install a replacement filter. To be able to supply your shelter with unfiltered air in peacetime or after the end of consequential fallout danger, you should make and keep ready a duct with appropriate fittings to connect your pump directly to its air intake pipe. 2. If you have only one filter, do not install it before you need to filter the air supply. Connect your pump directly to the air intake pipe, using an appropriate duct and fittings. Then, before the attack and before the arrival of fallout, revealed by your fallout monitoring instrument, keep your shelter well ventilated with unfiltered air. Whether or not your filter is installed, stop ventilating your shelter for a few hours while heavy fallout is being deposited outside unless heat-humidity conditions become unbearable. If before shelter ventilation is stopped the shelter air does not contain an abnormally high concentration of carbon dioxide, then no outdoor air need be supplied for about 5 hours to prevent building up too high a concentration of respiratory carbon dioxide, provided there is about 70 cubic feet of shelter room volume for each occupant. An encouraging reminder. Persons making preparations to improve their chances of surviving an all-out attack should realize that if the United States is hit with warheads the sizes of those in the 1987 Soviet intercontinental arsenal, the fallout particles of critical concern will be much larger than the extremely small particles, 1 to 5 microns in diameter, which are not completely removed by this filter. Fallout particles this small produced by large nuclear explosions do not fall to the ground for many days to months after the nuclear explosions, by which time they have become much less radioactive. Essentially all of the larger particles can be removed merely by filtering the air through a few thicknesses of bath towel cloth. Book page 273. Copyright 2000 Nuclear War Survival Skills. Also see the New Expedient Shelter book. Requires the DJVU plugin. NWSS Contents. Cover. Addition Notes. Table of Contents Book Order Form Forward. About the Author Acknowledgements Introduction. Ch. 1. The Dangers. Ch. 2. Warnings and Ch. 3. Psychologic. Ch. 4. Evacuation. Ch. 5. Shelter. Ch. 6. Ventilation. Ch. 7. Protection. Ch. 8. Water. Ch. 9. Food. Ch. 10. Fallout raw. Ch. 11. Light. Ch. 12. Shelter saw. Ch. 13. Surviving. Ch. 14. Expedient. Ch. 15. Improvised. Ch. 16. Minimum PR. Ch. 17. Permanent. Ch. 18. Trans-Pachi. App. Instructio. App. 8.1. Door COV. App. 8.2. Pole COV. App. 8.3. Small PO. App. 8.4. AboveGrow. App. 8.5. AboveGrow. App. 8.6. AboveGR. App. B. How to Mock. App. C. A. Homemade. App. D. Expedient. App. E. How to mock. App. F. Providing improved ventilation and light. Selected references. Selected index. Graphics. Nuclear war survival skills. Mail home. App. F. Providing improved ventilation and light. Means for providing improved natural ventilation and daylight to a shelter with an emergency exit. The need. Survivors in areas of heavy fallout can greatly reduce the radiation doses that they will receive, and thus decrease their risks of contracting cancer, if they sleep and spend many of their non-outdoor working hours inside good shelters during the first several months after an attack. See Minimizing Excess Radiogenic Cancer Deaths After a Nuclear Attack, by Kathy S. Gant and Conrad V. Chester, Health Physics, September 1981. A permanent family shelter can serve quite well for months as a post-attack temporary home if it is designed to provide adequate natural ventilation most of the time, to have adequate and easy forced ventilation by a cap when forced ventilation is needed, and to have daylight illumination. A shelter dependent on ventilation laboriously pumped through pipes and on artificial lights even during daytime is much less practical for use as a post-attack home. The following instructions should enable a family having an earth-covered shelter with an emergency exit to make it much more livable for months-long occupancy. The means described below for providing improved ventilation and daylight illumination also will supply guidance to survivors who will build shelters post-attack to minimize continuing radiation exposures, especially to children and pregnant women. Building and using a multi-purpose emergency exit housing. Build a multi-use emergency exit housing of the design pictured in Figure F1 and detailed in Figure F.2. Size your exit housing to fit snugly over the top of your completed vertical exit shaft. This exit housing is made of 3/4 inch exterior plywood, 4 2x2x 36-inch boards, and 4 16x 16-inch window panes of 1/8 inch plexiglass. Plated screws and waterproof adhesives are used to assure sturdiness and durability. Figure F.1. Multi-use emergency exit housing installed over the square emergency exit described by Figs. 17, 1, 17.2, and 17.3. Photograph. The adjustable top of this exit housing measures 4x4 by 1 foot, and can be tilted to make different sized ventilation openings in any of 4 directions. The top also can be raised straight up to make various sized openings all the way around, or it can be completely closed as explained by Figure F.2 and the following descriptions of its uses. Book page 274. Figure F.2. Plan and side view of multi-purpose emergency exit housing. On a square emergency exit with 34x 34-inch cross-sectional outside dimensions. Diagram, Figure F.3. The top and 4 walls of the multi-purpose emergency exit housing, nested together to save storage space. Photograph. In Figs. F.2 and F.3. Note the 8 beveled plywood guides, 2 on the inside of each side of the top. These guides are needed so that the top can be tilted in the position desired, merely by using a stick to raise it from below. To hold the top in a tilted or raised position, spacer boards are placed between the raised top and the upper edges of a wall or walls, as illustrated by Figure F.4. Figure F.4. View from below the exit, looking up the multi-purpose emergency exit housing. The top is shown supported in a tilted position by 2 6-inch wide boards placed between a wall and the top. Photograph. The illustrated housing over a vertical exit provides a means to regulate shelter ventilation, and to increase natural ventilation when the wind is blowing. If, for example, the shelter's opened exit is to the north of its opened entry and a north wind is blowing, shelter airflow will blow in through the exit and out through the entry. This natural ventilating airflow, often inadequate, is increased if the adjustable top of the exit housing is not simply raised 6 inches on all 4 sides, but is tilted as shown in Figure F.1, with its south side closed and its north side tilted up 6 inches to provide a 6x 26-inch ventilation opening between the upper edge of the entry housing's north wall and its top. Then a north wind striking the north wall produces increased air pressure over and above this wall, forcing more air into the exit and on through the shelter. In contrast, if a south wind is blowing, natural airflow will go in through the shelter's entry and out through its exit. And if the adjustable top still is tilted open to the north as illustrated, then reduced air pressure over and above the downwind north wall will suck, and increased airflow out of the exit and through the shelter. The measured increases in airflows through a small shelter resulting from the top of this exit housing being tilted were only 40 to 50 cfm when an 8 to 10 mph breeze was blowing. These rather small increases in airflow, however, often would make it unnecessary to supply forced ventilation to a family shelter by intermittently operating a cap. Exclusion of rain, snow, and larger dust and fallout particles. The 412x 48-inch vertical sides of the adjustable top overhang the exit housing's walls by 6 to 12 inches. Thus the top serves as a large ventilation hood over the exit, preventing rain, snow, and larger dust and fallout particles from entering while ventilation is continuing. To prevent entry of flies and mosquitoes, an insect screen panel, made to fit over the bottom of the emergency exit, should be kept stored in the shelter until needed. A screen door for the inner entry doorway also should be stored. Remember that installing screens greatly reduces natural ventilation airflows. A reliable source of daylight. The 412x 12-inch windows of this exit housing let enough daylight into the exit shaft, that is painted white, to permit a person on the shelter floor below to read, even for several minutes after sunset. See Figure F.4. A way to observe what is going on all around the shelter, without having to go outside, and with lessened exposure to fallout radiation. Quick installation post-attack, after fallout decays sufficiently. In an installation test, dirt was dug away to expose the upper 12 inches of the emergency exit shaft. Then in just 8 minutes the author and a boy carried the 5 parts of this exit housing 80 feet, positioned its 4 walls around the already exposed upper 12 inches of the reinforced concrete emergency exit, nailed its walls together, and placed its adjustable top in the tilted position pictured in Figure F.1. Building and using an entryway cover that provides a large, protected ventilation opening. Build a shelter entryway cover that keeps out rain, snow, and the bigger dust and fallout particles while providing a large, protected ventilation opening both for natural ventilation and for easy forced ventilation by a cap when needed. Book page 275. For an example of one type of entryway cover, see Figure F.5. This photo shows a 4-piece cover that 2 men in a little less than 5 minutes carried out of this shelter and installed over the 4x 6-foot opening above the shelter's open stairway doors. Figure F.5. A quickly installable, 4-piece entryway cover that provides easy access and a large, protected ventilation opening. This cover is made of 4 pieces of 1/4-inch chipboard, each 5 feet wide, and short lengths of nailed-on 1x 2-inch boards. These 4 pieces can be tied quickly with their attached nylon cords to inner parts of the 2x 6-foot steel entryway doors, which are pictured in their opened, upright positions. The lowermost of the 4 chipboard pieces has a groove near each end. The grooves are each made of 2 nailed-on lengths of 1x 2 lumber spaced apart to fit the lower ends of the doors and hold them in their upright positions 4 feet apart. The upper edge of this lowermost piece is 8 inches below the lower raised corners of the doors, so that an 8x 48-inch ventilation opening is assured when the lower of the 2 large covering pieces, pictured being held open, rests on the doors. This step-over piece of chipboard illustrates a way to reduce the quantity of larger fallout particles that will be blown into many types of shelters, because most sand-like particles and coarse dust are blown along close to the ground. They are not blown upward and over a vertical obstruction by most winds. If an entryway has an inner, ordinary doorway, even more fallout particles can be kept out of the shelter room if an 18x 18-inch ventilation hole is cut in the door near its top. Book page 276. Then air entering the shelter room will have to rise at least 4 feet above the entryway floor, and most of the larger fallout particles will be deposited on the entryway floor. The chipboard piece attached to the upper ends of the doors also has 2 1x 2 boards nailed near each end, forming grooves into which the upper ends of the doors fit. The doors are thus held in their upright positions and rain, etc. is kept from falling or being blown through the upper end into the entryway. The uppermost of the 2 large covering pieces of chipboard, or exterior plywood, rests on the open doors and is kept from slipping down by a 1x 2-inch board nailed 4 inches from its upper end. This small board hooks over the upper edge of the piece of chipboard, or plywood, attached to the upper ends of the steel doors. See the drawing on the side of this column. This large piece of chipboard is securely tied to the doors. To keep the two large pieces from moving sideways, one 1x2-inch board is nailed near each of their side edges, spaced so as to lie against the outside of each opened, upright steel door. To strengthen the hingeline edge of the upper large covering piece, a x2-inch board is nailed along its lower edge. Figure PG 276. The lower of the two large covering pieces also has a reinforcing 1x2 nailed near its hinged edge. The most practical hinge that the author has devised is illustrated by the drawing. This flexible hinge is much less likely to be broken than our conventional hinges, and makes it easier to build the two large covering pieces to fit over the opened doors. Note that the upper edge of the lower large piece goes under the rainproofing, 6-inch wide rubber flap, which is nailed only along the lower edge of the upper large covering piece. Then the two large pieces are held and hinged together by first stretching each of two strong, 2-inch wide rubber bands, or rust-proof springs, attached by cords to the upper large covering piece, and then hooking its attached bent wire hook onto a nylon cord loop connected to the lower large covering piece. Each strong rubber band cut from a truck inner tube, and its attached hook and nylon cords is 5 inches from an open door. Thus hinged, the lower large piece can be easily raised to permit a person to step out of or into the stairway entry. When this hinged lower large piece is closed and tied down, a 2.7 square foot protected ventilation opening with a 10-inch overhang results. Other entryway covers to provide large protected openings for natural and cap ventilation. The owner of a permanent shelter with an emergency exit may be able to improvise coverings over its entry and exit after fallout decays sufficiently to permit work outdoors, provided that he understands natural ventilation and low-pressure forced ventilation requirements, and has the boards, nails, pieces of chipboard or plywood or canvas, tools, etc. needed. But if you own a permanent shelter, your pre-crisis preparations surely should include making and storing ready-to-install entryway and exit coverings of whatever designs you decide will best meet your anticipated needs for high protection factor sleeping and living quarters during weeks or months following a nuclear attack. Book page 277. Copyright 2000 Nuclear War Survival Skills. Also see the New Expedient Shelter book. Requires the DJVU plugin. NWSS Contents. Cover. Addition Notes. Table of Contents. Book Order Form. Forward. About the author. Acknowledgements. Introduction. Ch. 1. The dangers. Ch. 2. Warnings. And Ch. 3. Psychologic. Ch. 4. Evacuation. Ch. 5. Shelter. Ch. 6. Ventilation. Ch. 7. Protection. Ch. 8. Water. Ch. 9. Food. Ch. 10. Fallout raw. Ch. 11. Light. Ch. 12. Shelter saw. Ch. 13. Surviving. Ch. 14. Expedient. Ch. 15. Improvised. Ch. 16. Minimum PR. Ch. 17. Permanent. Ch. 18. Trans-Pachi. App. Instructio. App. 8.1. Door COV. App. 8.2. Pole COV. App. 8.3. Small PO. App. 8.4. Abovegrow. App. 8.5. Abovegrow. App. 8.6. Above GR. App. B. How to mock. App. C. A. Homemade. App. D. Expedient. App. E. How to mock. App. F. Providing. Selected references. Selected index. Graphics. Nuclear War Survival Skills. Mail Home. Selected references. 1. Radiobiological Factors in Manned Spaceflight. Space Radiation Study Panel of the Life Sciences Committee. Space Science Board. National Academy of Sciences. National Research Council, 1967. 2. Personal Communication with Dr. C.C. Lushbaugh, Chairman, Medical and Health Science Division, Oak Ridge Associated Universities, in June 1977. 3. The Effects of Nuclear Weapons, 1962, Samuel Glastone, Editor, Published by U.S. Atomic Energy Commission, April 1962. 4. Adequate shelters and quick reactions to warning. A Key to Civil Defense. Francis X. Lynch, Science, Volume 142, pp. 665-667, 1963. 5. Blast tests of expedient shelters in the Dice Throw event. Cresson Kearny and Conrad V. Chester. Oak Ridge National Laboratory Report No. 5347, February 1978. 6. The Effects of Nuclear Weapons. 1977. 3rd edition. Samuel Glastone and Philip J. Dolan. Editors, U.S. Department of Defense and U.S. Department of Energy, 1977. This most authoritative publication has numerous sections written for non-technical educated readers. In 1986, a cloth-bound copy can be purchased for $17 from the Superintendent of Documents, U.S. Government Printing Office, Washington, D.C. 20402. When ordering, ask for The Effects of Nuclear Weapons, 1977, stock number 008-046-00093-0. Since the price may be increased in future years, a buyer should first write requesting the current price. 7. The 900 Days, Harrison E. Salisbury, Harper Row, New York, NY, 1969. 8. Expedient Shelter Construction and Occupancy Experiments. Cresson Kearny, Oak Ridge National Laboratory Report No. 5039, March 1976. 9. Biological Tolerance to Air Blast and Related Biomedical Criteria. Clayton S. White et al. Lovelace Foundation for Medical Education and Research, Albuquerque, NM, April 1965. 10. Instrument Requirements for Radiological Defense of the U.S. Population in Community Shelters. Karsten M. Holland and Kathy S. Gant. Oak Ridge National Laboratory Report No. 5371, August 1978. 11. Field Testing and Evaluation of Expedient Shelters in Deeply Frozen Ground. Ren Reed, College of Environmental Design, University of Colorado, Denver, Cobb. July 1978. 12. Construction of Hasty Winter Shelters. Cresson Kearny. Annual Progress Report. Oak Ridge National Laboratory Report No. 4784. March 71, March 72, December 1972. 13. Shelter Occupancy Studies at the University of Georgia. Final Report, 3. A. Hammis and Thomas R. Ahern. OCD Contract No. OCDPS 66-25, 1966. 14. Environmental Physiology of Shelter Habitation. A. R. Dazzler and D. Menard. Paper presented at the ASHRAE Semi-Annual Meeting in Chicago, January 1965. 15. Studies of the Bureau of Yards and Docks Protective Shelter. NRL Report 5882. U.S. Naval Research Laboratory, Washington, D.C., December 1962. 16. Winter Ventilation Tests. Guy B. Pinero, Inc., Subcontract No. B64212, US for Office of Civil Defense, February 1965. 17. Interim Standards for Ventilating Systems and Related Equipment for Fallout Shelters, Office of Civil Defense, Washington, D.C., 1962. Book page 278. 18. Response to DCPA Questions on Fallout. DCPA Research Report No. 20, prepared by Subcommittee on Fallout, Advisory Committee on Civil Defense, National Academy of Sciences, November 1973. 19. Personnel Shelters and Protective Construction. NAVDOCKSP 81. Department of Navy, Bureau of Yards and Docks, September 1961. 20. The Destruction of Dresden. David Irving, W.M. Kimber and Company, London, May 1963. 21. Chinese Civil Defense. Excerpts from Basic Military Knowledge, Shanghai 1975, ORNL TR-4171. Edited by Conrad V. Chester and Cresson Kearny. Oak Ridge National Laboratory Translation, August 1977. 22. The Effects of Mass Fires on Personnel in Shelters. of Broido and A.W. McMasters. Technical Paper 50. Pacific Southwest Forest and Range Experiment Station. Berkeley, Calif. August 1960. 23. Civil Defense. N.I. Alabin, et al. Moscow 1970. ORNL TR-2793. Oak Ridge National Laboratory Translation. December 1973. 24. Manual of Individual Water Supply Systems. Environmental Protection Agency. Water Supply Division. Washington, D.C., 1973. 25. Solubility of Radioactive Bomb Debris. D.C. Linston, et al. Journal of American Water Work Association. 53, pp. 256-62, 1961. 26. Maintaining Nutritional Adequacy During a Prolonged Food Crisis. K.B. Franz and Cresson Kearny. Oak Ridge National Laboratory Report No. ORNL 5352, July 1979. 27. Livestock, Fallout and a Plan for Survival. W. F. Byrne and M. C. Bell. UTAEC Agricultural Research Laboratory. Oak Ridge, 10. RCD 3, April 1973. 28. Availability and shipment of grain for survival of the relocated population of the U.S. after a nuclear attack. Karsten M. Holland, American Journal of Agricultural Economics, May 1977. 29. Personal communication with Kathy S. Gant and Conrad V. Chester, January 1979. 30. Food stockpiling for emergency shelters. Food and Materials Division, Commodity Stabilization Service, U.S. Department of Agriculture, April 1961. 31. The KFM, a homemade yet accurate and dependable fallout meter. Cresson Kearny, Paul R. Barnes, Conrad V. Chester, and Margaret W. Kortner, Oak Ridge National Laboratory Report No. ORNL 5040 corrected, January 1978. 32. Where There Is No Doctor. David Werner, Hesperian Foundation, Palo Alto, Calif. 1977. 33. Personal communications from Colonel C. Blanchard Henry, M.D., Binghamton, N.Y., to Cresson Kearny in 1963. 34. Emergency Medical Treatment. TM 11-8. Federal Civil Defense Administration, U.S. Government Printing Office, April 1953. 35. The Radiation Studies Begin. Science, Volume 204, page 281, 1979. 36. Protection of the thyroid gland in the event of releases of radioiodine. National Council on Radiation Protection and Measurements, NCRP Report No. 55, Washington, D.C. 20014, August 1, 1977. 37. Accidental radioactive contamination of human and animal feeds and potassium iodide as a thyroid-blocking agent in a radiation emergency. Food and Drug Administration, Federal Register, December 15, 1978, pp. 58790-58800. 38. Civil Defense, N.I. Akimov et al. Moscow, 1969, ORNL TR-2306, Oak Ridge National Laboratory Translation, April 1971. 39. Frantic team efforts brought vital chemical to stricken plant. Robert Reinhold, New York Times, April 4, 1979, p. A16. 40. Trans-Pacific Fallout and Protective Countermeasures. Cresson Kearny, Oak Ridge National Laboratory Report No. 4900, November 1973. 41. Letter dated May 23, 1979 from William H. Wilcox, Administrator, Federal Disaster Assistance Administration, Washington, D.C. to Robert A. Levtown, Washington Representative of the American Civil Defense Association. 42. Historical Instances of Extreme Overcrowding. Bureau of Social Science Research, Inc., Report No. 354-5, March 1963. 43. After Action Report. Operation Laboratory Shelter. Headquarters U.S. Army 24th Airborne Corps, featuring Bragg, N.C., 1970. Book page 279. Copyright 2000 Nuclear War Survival Skills.